It's not, but I don't see it. Yeah.
Test. Hello. Yeah, good. We still have a minute, so. Rakesh, is this unmute? Zoom for the speaker or muted? This one is working for. This is for the live stream. Speaker, is it unmute, right? Okay, good. All right, let's get started. It's 9 a.m. Hello, everyone. Welcome to the 7th edition of Memory-Centric Computing workshop. Actually, we held this workshop last year in ICS as well. Back then it was, I think, 2nd edition. So we have held this in many places again. So I'm Ismail. I'm a PhD student in Safari Research Group under the supervision of Professor Onur Mutlu. I've been doing my PhD since February 2024, so I'm in my 3rd year now. And as you may guess, I'm interested in computer architecture, processing in memory, in general memory systems, hardware security, reliability, and safety. So you can check the agenda, you can scan the QR code for the agenda and everything to see. If there's a dynamic change, I'll let you know, because there are some delayed flights for some people, so you never know. And the materials that we are going to use today will be online soon, after I get the consent from all the speakers. Probably you will find it tomorrow or the day after. I'm just going to leave it for 5 more seconds if you would like to scan it, and then I'll move on. I think you can find it in the ICS conference website as well. So we are 4 organizers. I'm Ismail, and there's Nisa and Ataberk. Ataberk is actually holding another tutorial today in, I guess, room 6, Remulator and DRAM Vendor. And today I'm going to discuss some works that we use actually with that DRAM vendor, real DRAM chip infrastructure. And we have Professor Onur Mutlu here. So the first session, it will be this one is logistics, and then I'm going to talk about some recent works that we did in processing using DRAM. I'm going to try to first convince you why do we need memory-centric systems very quickly, and then I'm going to focus on processing using DRAM, especially processing using DRAM operations in real DRAM chips. And in the second session, we have very exciting talks. I will say first is OmniMP from Bike. And then some check PIM, percent check PIM, and then we will have an online attendee. Unfortunately, he didn't make it, as I said, due to some flight issues. And this will be, I think, a bit about different areas like LLM inference, acceleration, and zero-knowledge proofs. And then in the third session, Ataberk will give a brief talk on how do we use FPGA-based frameworks to enable fundamental better computing systems. And then we will have Daichi, he's going to talk about his recent works. Padgos is one, and there will be another. And later we will have Rakesh. He will talk about the storage aspects of it. So until now, we will probably focus on mostly DRAM and DRAM-based processing in memory architectures, but Rakesh will give an overview on the talk works about storage-centric systems. And then we will conclude with Professor Mutlu's talks, which is in general memory-centric computing, solving computing systems memory problem. So this is it. So I'm going to quickly change to the real slides that I have. Okay, so as I said, this will be about processing using memory in real DRAM chips. So, I'm going to skip this. I introduce myself. I'm Ismail again. And let me start with the problem, the fundamental problem. The computing that we're doing today is bottlenecked by data. So many important workloads such as AI, ML, genomics are all data intensive, and they require rapid and efficient processing of large amounts of data. And this data is increasing. So as you can see, this is one of the talks, screenshot of the talk from Grok. And as you can see, now it's even more. In 2 years, we needed more than 1,000 times more compute, just in 2 years. And now this was GPT-3. It was 175 billion. Now we have trillions of parameters in, for example, in LLM, and it's increasing even more. And it's not just LLM, it's also the genomics and the data that we would like to process to understand some of the diseases, some genomics related issues. We need to actually process a lot of data. And as you can see here, it shows from the trend from 2014 to 2017. And again, it's almost 10x. So the problem really is data access is the major performance and energy bottleneck. And our current design principle calls great energy waste due to this data being only computed in CPU or the XPU. And it has a great performance loss because we need to move the data a lot. So what is this data movement bottleneck? So we have this data movement bottleneck because of today's computing systems are processor-centric. So all data, as I said, processed in the processor. So as you can see, for example, in order to do a computation on the data, we need to first get the data, do the computation, and then we need to write it back. And in this scenario, the main memory is just doing nothing. It's just serving, load, and store accesses. And a recent work showed that this movement only causes more than 60% of the total energy. And this is not just energy, it's also a performance. So this is a good, beautiful paper from Google back in 2015, published in ISCA. And here, this is the Google's data center workloads. And as you can see, the green is the retiring, what processor should do. And in the remaining parts, as you can see, the red parts are bottlenecked by the waiting for the data. So processor is doing its job only 10% or 20% of the workload. And to even further motivate this is, I think, Bill Daly's high-peak talk from 2015. So as you can see, the 64 bits of double precision operations are just 20 picojoules. But in order to get the data, you see the DRAM read-write consumes 16 nanojoule. So it's more than 100 and 1,000 times. And to have like a graph to show the relative even better, you can see a memory accesses consumes 6,400 times the energy of a simple integer addition. And there are papers about showing the Google workload spending 62.7% of total energy time spent on data movement. And in some neural networks, in large ML models, this was back in 2021, more than 90% of the total energy is spent on the memory. So the fundamental problem is the processing of the data is performed far away from the data. And we need a paradigm shift, processor-centric paradigm to memory-centric paradigm to enable computation with minimal data movements. And we should compute where it makes sense, where data resides, and make computing architectures more data-centric. So this is the Apple's M1 Ultra system. As you can see, this is the colorful part is the processor and a lot of SRAM caches. And there is even bigger part of its DRAM. And there's even bigger, larger part of the darkness of storage here. And there's even sensors. So we can actually do many computations in DRAM storage, even in sensors. But what we are doing is that we're just getting this large parts of data, large parts of residence to the processing unit. Here it's in, let's say, M1 Ultra system, which is very small compared to others, and do the computation there. And we need to move a lot of data there. And one other thing that what we can do is to enable this memory-centric computing paradigm is that we can think of that it's like a conventional accelerator at first. And we can put some sort of specialized computation capability near memory or inside memory, which I'm gonna discuss more. But even doing that will be challenging because we will be touching a lot of parts in the stack, starting from the devices and up to the algorithms or even problems. For example, what about the software hardware interfaces? What about system software? How should we compile this? What about the languages that we're going to use? And the algorithms and theoretical foundations. For example, everything that we're doing is optimized for processor-centric systems. But maybe some of the workloads kernels, we need some sort of different perspective to make it memory-centric. So in that sense, I think this is also very interesting to think about in terms of algorithms and theories. And this is not a new idea. This is one of the first papers that's from Kautz called Cellular Logic in Memory Arrays, which is published in 1969. They were thinking of adding some sort of logic inside the SRAM arrays so that we will be doing some sort of computation. And another one, which is from Stone, and this is from 1970s, called a logic in memory computer. So back then they were thinking about adding, so because of this was a CMOS process, they were thinking of adding some sort of gates inside the SRAM cells. So in this, let's say, talk, I'm gonna focus on processing in memory, but we categorize processing in memory in two types. First is processing near memory, where you add logic to the same dies as memory or to the logic layer of 3D stack memory. So you're adding some sort of capability near the memory array. You're not using the cells or etc. But the processing using memory uses the operational principles of memory cells, the circuitry to perform computation. For example, you will be really just using the cells to perform some computation and with some minimal additions, but not really a digital component such as AND unit or AND. So as I said, the focus will be on processing using DRAM. And today, we can actually natively support in DRAM bulk bitwise copy operation, initialization, zeroing, bulk bitwise Boolean operations, and or not, majority nor NAND. And we can do security primitives through random number generation, physical unclonable functions, and we can do more complex computation using lookup tables. And at low cost, we can use analog computational capability of DRAM. And the key idea is actually activating multiple rows to perform such computations, such processing. And even the very interesting part is that commodity off-the-shelf DRAM chips, today what we have in our phones, laptops, everywhere, they can perform some sort of operations without any change to the DRAM chips, only some sort of changes to the memory controller itself. And this can bring us 30 to 250 times more performance and energy improvements. And there are papers that I'm going to talk about for this end-to-end execution or showing the improvements. So before delving into more processing using DRAM, I would like to give you some sort of background, a quick background. Let's start with the DRAM organization. So here we see a DRAM module consists of many black boxes, which is a DRAM chip. And inside the DRAM chip, we have multiple DRAM banks. For example, in DDR4, we have 16, in DDR5, we have 32. And inside the bank, we have many subarrays and sense amplifiers. And within each subarray, we have two-dimensional array of DRAM cells. And a row of DRAM cell called DRAM row, and they are connected through word line. And a column of DRAM cells are connected to sense amplifiers via bit lines. So in this talk, we're going to focus on some major DRAM operations, not all of them. The first one is activate, which will activate the row, fetch the row's content into sense amplifiers. After that, we can issue read and write operations to the DRAM. And then, in order to perform another data accesses to another row in the same bank, we need to issue per charge. So let's take a closer look to a DRAM cell, how these operations work. So here we have a capacitor which stores the data as electrical charge. You can think of that this is now full, it stores as logic 1. If it's empty, it stores as logic 0. And we have word line, bit line, an access transistor, and sense amplifier. So what will happen when we issue activation? So let's say this is the initial phase. Now the bit lines are pre-charged to VDD over 2, which is what modern DRAM does. And now the word line and sense amplifier enabled signal is disabled. So when we issue activation, DRAM first find the word line that is needed to be activated, and then it will raise the voltage in the word line, which will connect to the cell to the bit line through the access transistor. The word line enabled will activate the access transistor and enable the connection between the DRAM cell, the capacitor, and the bit line. And then, since there will be a charge sharing through capacitor to bit line, now the cell will lose its charge through the bit line. And then this will perturb the bit line, creates a deviation in the bit line voltage. So this was full logic 1, right? And this deviation is plus here. So afterwards, after a successful, let's say, a charge sharing operation, now we will enable sense amplifier. After we enable sense amplifier, now sense amplifier will compare its bit lines. So on top, we have a VDD over 2 plus epsilon, and on the bottom, we have VDD over 2. Since it's higher than, so let's say the above part is plus epsilon, now it will sense that difference and amplify the difference to VDD, and the other part will be 0. And we will wait long enough, some manufacturer recommended timing, so that it will serve the VDD through the cell, so that cell regains its charge. And now we have the VDD on the bit line. Now we can issue read and write comments. So this is how activation works. And then, for example, if you want to go to another row, you'll need to issue per charge, which will disable word line, sense amplifier, and pre-charge the bit lines to VDD over 2 for another activation. So this is how, let's say, an activation works in a cell level. So let's start simple with the processing using their operations, data copy and initialization. So in that ISCA paper that Google showed that memory movement and the memory copy, mem copy, consumes 5% cycles in the workloads. And this makes sense because there are a lot of use for the copy operation or initialization, such as forking, reinitialization, checkpointing, cloning, page migrations, and many more. So in current systems, if we, in a simplified way, we have a CPU And we have a cache hierarchy L1, L2, L3, and we have a memory controller MC there, and which will connect to the DRAM, the main memory. And in order to do a copy operation, what we do is that we get the CPU, every data, and then we will write it back to just perform the mem move or mem copy. And we will be trashing the cache hierarchy a lot. And now what we can do is actually, if you think about it, it's just copying one region to another region, right? So why not just copying from there? And there are many, let's say, ways to do that. And if we can do this, some sort of operation, now we will have low latency. We don't need to pay for the data movement. And we don't need to use the bandwidth, the off-chip bandwidth between the processing unit and memory. And as such, we will have low bandwidth utilization, and now other processes can use this bandwidth. And we will not have any cache pollution. Now, in order to do that, we will need to get everything to the CPU, and which will evict some data from the caches. And now think about that we need to write back, and it will consume some other parts of the cache as well. And then we will not have any data movement, moving the data from memory to CPU, CPU to memory, and which normally consumes 3.6 microjoule to now it consumes 0.04 microjoule, and it takes much less time. So how do we do that? So there's a paper called row clone in Micro 2013. The key idea is to copying one row to another row from sense amplifiers. So basically copying source row to the sense amplifier, and then destination will be overwritten. Let's see how would that work. So you remember this sketch, right? So now we have two cells. The above is source cell, the below is destination cell. So what we're going to do is that we're going to activate the source, which will share its charge. And then since it has 1, so in the beginning, the source cell has 1, the destination has 0, as you can see. Since we open the source, now we have a positive perturbation on the bit line. And then after we enable sense amplifiers, now we have VDD here, and then we wait, and source cell has 1. This now we turn back to the initial state, but the bit line has VDD now, which is the source cell's data. So, and then we're going to activate destination and deactivate the source cell. So what's going to happen is that, is it as if we're restoring the charge back to the destination, because sense amplifier is enabled, it's strong, and it will feed the destination cell like a normal operation, DRAM operation does. And then now we were able to copy the source cell to destination cell without doing any changes, right? What we did is that we changed the minimal things that normally in order to do another activation, we need to precharge everything. But if we just precharge the word line, but not precharge the sense amplifier or bit line, now we can just copy. So, and then data here gets copied. So the benefits are good, very good. If you think about the latency, it's more than 10 times. If you think about energy, more than 70 times. So this was row clone. This is, I guess, one of the first papers about this, and in 2013, Micro. And this was data copy. Now let's take a look at how we can perform Boolean bitwise operations. So, and we're going to focus on the key fundamental thing that we are still using today for this processing using DRAM operations, which is a majority function. Now we have 3 cells, 0, 1, and 1, respectively here. And now they're all disabled, right? So the key idea is to activate them at the same time, all 3 cells simultaneously. What happens is that now each tree will share its charge with the bit line, right? So the fascinating thing is that due to the charge sharing principles, now it's like you can think of that you have 3 glasses and you're pouring it to some sort of bigger glass. And now since 2 of them are 1, 1 of them is 0, the average is higher than 1/2, right? It's 2/3. So it will create a positive perturbation on the bit line. So you can think of in another way is that we have 0, which will try to pull down the voltage, which we have 2 other positive charge, which will try to pull up the voltage. Since we have a majority of 2 over there, they will win, and they will have a positive perturbation on the bit line. And as a result, now we will enable the sense amplifier, and since we have the positive perturbation, now we have the VDD result here, which is the majority tree of 1, 1, 0. The result is 1 here. And then we will wait, and then they will restore the charges back. And then actually using this majority tree, which is basically, think about ABC here. The output is majority ABC. We can actually control the C value or any other value here, one value here, to implement AND and OR operations. Now with this primitive, if you set C as 0, now you have A and B. If you set C to 1, you have A or B. So now we have 3 Boolean primitives, right? Majority, AND, and OR operation. And this can be useful for many database queries back and then. This was a paper published in 2017. Now it shows that in the database operation, the bit viewing, it can provide 4 to 12 times performance improvement compared to the processor-centric baseline. And there are more things on Mbed. It also shows how we can enable NOT operation with some adding some access transistors. Because if you remember that we have in the sense amplifier, we have 1 2-bit lines, right, connected. And if one of them is VDD, the other one is 0. So in the Mbed paper, they route that the other bit line, which is supposed to call bit line bar, to perform the NOT operation. So this was Mbed. And later, there's another paper show SIM-DRAM, using these primitives to enable processing using DRAM to end-to-end workloads. The key idea is that, for example, you have a workload, right, or kernel. So you can use the majority and NOT gate because only to perform these operations, because majority and NOT is functionally complete. So if you have majority, if you have NOT, now you can implement any sort of operations that you want. So what they're doing is that actually they're creating a majority inverted graph and for a given an operation. So for example, you have an addition, 8-bit addition. You will feed it as a user input, and then it will generate the majority not inverted logic. And it will, what it's going to do is that it will generate DRAM commands. Basically, let's activate 3 rows, let's perform NOT operation as activate, precharge, etc. And then it's inside the memory controller. And then it will have some sort of, let's say, similar to simple processing units to feed the operations to the DRAM. And then you can actually implement arbitrary operations directly using this framework. So I talked about all of this. So, and then they did some end-to-end workload evaluations, kernels as well. So compared to the back then in 2021, they show large improvements over CPU and high-end GPU. So for example, throughput can be, let's say, 6 times more throughput than GPU, or much less energy consumed compared to CPU and GPU. And there are more things on SIM-DRAM you can find over there. And I'll make the slides online, as I say, tomorrow, so you can take a look and everything from here. And this was SIM-DRAM. Now, there is another paper in HPC 2124. Now we are getting more and more close to the current state. So this is MIM-DRAM. It uses maths, which I didn't talk about before. So what happens is that, so you remember subarray, right? There's a 2-dimensional array of cells inside a subarray. So actually, there's one more layer between the DRAM cell and a subarray called mat. So this is basically a subarray that for, let's say, small arrays, which we call each of them mats. So normally, when we issue activation, we activate all mats concurrently, feeding the global word line to some small local word lines to perform this operation. And what MIM-DRAM does is that, so there's already a connection here, right? And usually mats, for example, you can think of that 512 rows of cells, 512 columns. So it's very good for 5 and 12 bits operations if you have some sort of isolation. What MIM-DRAM says is that, so normally you access all the maths at the same time, right? And this actually consumes a lot of energy. There are prior papers show that you can have actually fine-grained accesses. Instead of activating the whole row, you can activate just the math. For example, you want to just get one cache line, right? Like 5 and 12 bits. Why do you need to activate the 8 kilobyte wide DRAM row? There are other reasons to that, but you can actually gain some sort of energy and performance improvements. So MIM-DRAM leverages this fine-grained DRAM idea, which is shown in many papers, and the latest one is secured DRAM. So they're segmenting this, they're isolating each math. So whenever you want to perform a processing using the RAM operation, you're not using all the row, but you're using just part of the row, just for example, a single math here. So why? It will improve the utilization. So what happens is that actually in real workloads, you don't need to have 8 kilobyte wide vectors. They usually are optimized to, for example, AVX 512. They're optimized to 512, let's say, bit operations. So if you actually use a single math, it will fit, let's say, very well to those operations. And it will improve SMD operation, basically, single instruction, multiple data. So you can actually perform multiple operations in many different maths at the same time. So, and then it will enable low-cost interconnection. So normally we don't have a way to move the data from one column to another column. We have a way to move the data from one row to another row. So if you have this some sort of connection, now you can move the data from one column to another column. And it will ease the programmability, as I said, because of the vector ISA's SMD bit, usually 5 and 12 bits. Now you can use them and you can program your processing using them substrate easily. So in the SIM-DRAM, it actually shows it implements 3 different LLVM passes targeting a PUD execution using like first identifies the code and then using data scheduling graphs and it will and the mapping. It will create, let's say, an optimal way of performing such processing using DRAM operations using this compiler support. And then it shows that you can actually get, for example, compared to performance per watt, energy efficiency, you will be 10 times more energy, 10,000 times more energy efficient than GPU, for example. So this was actually showing until now, we see everything was modified DRAM chips. We needed to modify some sort of operations to perform, some sort of components to perform such operations. But existing DRAM chips are already quite capable. So a paper from Princeton University back in 2019 showed that if you violate some DRAM timings, you can actually mimic what the row clone and M-bit shows. So basically, you can perform a copy operation and you can perform a majority tree operation. So, and then the PyDRAM showed that actually, if you, by using this row clone and multiple row activation, you can implement end-to-end row clone and TRNG in off-the-shelf DRAM chips. So this is the one setup that we use. This is an FPGA port, as you can see. And inside the FPGA, which is under the fan, which Ataberk will talk about even more, I think, after the lunch. So we will have some sort of RISC-V system there, and we have a soft memory controller. Now, it's by changing many things, let's say the libraries, OS, and hardwares, the CPU, we can actually perform end-to-end row clone and TRNG operations. And this is open source. If you have the FPGA that we use, you can actually implement this and you can actually extend this to other operations. This was, as I said, only shown for row clone, but you can implement end-to-end kernels. And there are more things on PyDRAM, and as I said, Ataberk will discuss this after the lunch. So here, this was all the things that I wanted to cover until now, and I'm going to focus on these three works right now. And first two is we'll be talking about the computational capabilities on real DRAM chips, more further things that we observed from the prior works, and the last one will give a brief warning about, like, yeah, we have this capability, but at what cost? What is the reliability? It will generate any reliability issues. So we're gonna show that it has effects, but we will be optimistic. We will provide some sort of, let's say, hope that we can actually overcome these issues as well. So let's start with the first one, which is called functionally complete Boolean in real DRAM chips and experimental characterization and analysis. But before I start, do you have any questions for the previous part? Yes.
This is all referring to unique circuit language.
Yes.
This is not copying any inputs to any address. Inside the DRAM area, you have to all parameters. You can copy only to certain locations, all those operations, copy of the
Exactly. So to be more specific, you need to be in the same subarray as DRAM. Basically, it's usually consists of 1024 rows. There are more works actually showing this. If you add some excess transistors and some lines, wires, you can actually copy one row in any other row, but it will cost you more latency, blah, blah. But inherently, DRAM supports copying from one row to another row in the same subarray. Yes. Yes. Maybe there's a mic there. Rakesh, can you fetch it? Ah. It should be if it's not working, I think it's fine, but
Okay.
yeah.
Is there any between error many server class DRAMs?
Error correction capabilities of processing using.
So does ECC can work with such works or not? There, the research doesn't have a lot of lack.
So for ECC, you cannot use processing using DRAM operations directly with ECC because you're, for example, performing majority tree, right? What will be the ECC of majority tree operation? That's arithmetic. So you will need some sort of homomorphic operation. So actually, Mbits also argues that. So for row clone, it's easy. The data is the same. You're copying the data. You can copy the ECC, and it's already there. But for processing using DRAM operations such as AND or, think about you will have A, you have B. You need to have the ECC of A and B as well. So that requires a homomorphic function that you need to perform the data over the ECC as well. So as far as I know, that's an open research challenge still. And there are papers, some sort of, actually last year ICCD, I guess some sort of checking, some check actually, PIM-some, I think, but it's not, let's say, for all arbitrary, it's just some sort of pop counts. So I think that's still an open research problem, and it's very important research problem right now. Any other questions? Okay, then I'm gonna move to the first bit. So let me start with an executive summary to give you roughly the idea. So the motivation, that's the same that I was trying to motivate you. We can alleviate data movement bottlenecks using processing using DRAM. And the prior works, as I showed you, for example, compute DRAM, show that existing DRAM chips can perform 3-input majority and 2-input and then all operations. But the problem is, these operations do not provide any functionally complete operations. So there's no NOT until this, or NAND or no. They had only majority and or row copy operations. So they're not functionally complete. For example, you cannot implement XOR without having NOT or not NAND or not. And as I said, they don't have NOT operation, and they're limited to 2 inputs at a given time. So you can perform AND and OR operation with 2 inputs because of the measured tree. So they show that you can activate 3 rows at the same time only. So in this study, we test a total of 256 DDR4 chips from 2 major manufacturers. And we observed that off-the-shelf DRAM chips can perform NOT operation and 2, 4, 8, and 16 input AND, NAND, or an OR operation with a relatively high reliability. I'm going to discuss the reliability metric later. And data pattern and temperature only slightly affect the reliability of such operations. So you remember this is the DRAM, but I'm going to give, I wanted to give you one more quick background about DRAM. So the DRAM arrays architecture, which is called open bitline architecture. So to achieve high density DRAM chips, this open bitline architecture is widely adopted in modern DRAM chips to further scale DRAM even more. I guess the previous one called folded bitline architecture, it stopped at 80 or 70 nanometers. To further scale the DRAM, the process node, we needed, let's say, more compact operation. And right now, as you can see, one sense amplifier is shared by, consumes 2 cells area, as you can see here. So because we shrink the cell a lot more, but for sense amplifiers to have a robust operation, we couldn't shrink that much. And then they convert to 6S square geometry, which enables this open bitline architecture. So in this architecture, what we're gonna use it is that this, as I said, they share a common component, sense amplifier. So these are different subarrays. And now since there's a connection between the subarrays called sense amplifier here. So bitline is on the top and bitline bar is on the bottom subarray. So whenever we activate a row in, for example, top bitline, now the bottom bitline will not activate it, as you can see, and it will serve as the reference for the sense amplifier. Remember, I was explaining you, there's a positive perturbation, VDD over 2 plus epsilon. And it was comparing the bitline bar, which is always VDD over 2. And then after successful activation, now because of the NOT gate operation, when bitline has VDD, you have a 0 on the bitline bar. So we're going to leverage this connection, this NOT gate over there in the sense amplifier to perform NOT operation. So I'm going to skip this DRAM operations. And to sum up, we demonstrate that we can simultaneously activate up to 48 rows in 2 neighboring subarrays. Until now, it was 4. And we can perform NOT operation with up to 32 output operands, and we can perform up to 16 input AND, NAND, or an OR operation. So how do we perform these operations in real DRAM chips? So we use an FPGA-based infrastructure called DRAM Bender. So we have an FPGA board. It has some sort of very 3-stage pipeline, simple design, but it has a soft memory controller that we can issue these activations and precharge whenever we want. So normally, if you have a, let's say, end user system with a, let's say, this laptop, your memory, you can only issue load or store in some sense, right? But with this soft memory controller, we can control the memory PHY and the DRAM, and we can issue the operations with the fine granularity. So for example, we can issue whatever DRAM command we want in every 1.5 nanoseconds. And with this temperature, now we can control the DRAM chip temperature as well. So that now we have a controlled environment. Normally, you never know what temperature is that, so it will always fluctuates, right? And now we're actually developing a voltage controller as well. Now we're gonna have some sort of voltage changing capability, hopefully soon. It's still on the process. I don't know why, but for example, it cannot work with temperature controller right now if you merge like both voltage capability and temperature. So we're still on the early phase of that. That's why we don't have a picture like this. And then in our lab, we have, I guess, plus 100 FPGAs to perform these operations at the same time to test many DDR4 chips. For example, as you can see here, we have a little bit messy, but labeled everything. Like we have Samsung, SK Hynix, Nanya, Micron, but we're trying to get more and more and test, and some of them are also baked, unfortunately. So we need to buy usually. And as you can see here, in the bottom, now we some sort of achieve higher capability. Now in one FPGA, we can test 2 DRAM modules at the same time. So it gives us roughly 200, we can test 200 modules at the same time. And in this study, this was long before this kind of extension, we tested 256 DDR4 chips from 2 major manufacturers, and it covers different die divisions and chip densities. One of the issues with like testing these DRAM chips, you need to reverse engineer a lot, like because there is no, let's say, known subarray. Let's say this is the DRAM subarray you have. At most, you know that you have how many rows in a DRAM, how many banks you have, and that's it. You don't know the internal logical to physical DRAM row mapping. You don't know subarray level, where are the subarrays located, or you don't even know what are the physical adjacencies, blah, blah. So usually these experiments takes more than months, usually for a single model. We need to like test all the banks, everything with different temperatures, different data patterns, etc. So yeah, I think this study was around 4 months of testing. So now let's focus on the first one, and then we will move progressively. So the key observation is that activating 2 rows in quick succession can simultaneously activate multiple rows in neighboring subarrays. How is that going to happen? So this is 2 subarrays, subarray X and subarray Y, and assume that we have row A and row B. Subarray X has row A and subarray Y has row B. So normally this is roughly the timing that you will do. So you will activate row A. In order to perform a precharge, you need to wait a TRAS, which is around 36 nanoseconds. After you issue precharge, you need to wait for TRP, which is a timing parameter for 14 nanoseconds here, to issue the second activation. So if you obey the timings, now you will activate a single row at a time. You will activate row A in subarray X and row B in subarray Y. And if you violate these timings greatly, now what will happen is that you will activate a row A, you will precharge it, but you're not precharging it really. You will violate the timings, and you will not give enough time the RAM to precharge everything, and you will be activating row B. And as a result, you just not activate row A and row B. You will be activating many rows at the same time. So how is that going to happen again? So we try to reverse engineer the DRAM row decoder circuitry to understand why this is happening. So we test all the rows and all the banks to come up with this hypothesis is that there's a hierarchical DRAM row decoder circuitry. So this is DRAM subarray, right? So whenever you feed these row addresses to DRAM, it needs to decode somehow, and it needs to find the word line that is supposed to activate. And in order to do that, for example, in one reverse engineered model, we see that there's 5 stages of decoding circuitry, each of which is fed by different row addresses. And at the same time, they're decoding different parts of the row decoder circuitry, and they're combining every decoded parts. With in this sense, we find that it's like end operation, and you will try to find the one. Basically, you're ending all the decoder outputs, and then you'll be having only one, let's say, at the end of the circuitry. So I'm gonna use as a high-level example, a tree example. So think about the results, the outputs, the arrows over there is word lines. And think about every level of the row decoder tree is states. And now, as I said, we had 5 decoder stage, right? And each node is a decoder output. You can think of it like that. And actually, since, for example, one stage node's output is actually connected to another stage 1 node, it's another stage 1 node, it's a progressively increasing levels. For example, first stage will have 4, but the second stage will have 4 multiplied by 4, 16, and the other one 16 by 16, blah, blah. It goes like this, as far as we understood. So let's see how this works when you activate a single row. So you'll issue activate row A, And what happens is it will decode row A addresses. It will assert the corresponding signals. And as you can see, there are multiple signals asserted here because of the row decoder circuitries having hierarchical. So, and as a result, we will follow the asserted node path from root to leaf. And as you can see, only the word lines A is, let's say, path is fully asserted. And thus, the row DRAM will assert word line A. And then when we issue precharge, and we will be disabling, deasserting all the intermediate signals here. So how is that going to happen for us? So back-to-back ACT commands with while-waited timings will assert many more signals. So this was row A, right? So if I issue precharge and don't give enough time DRAM to precharge it and issue another activation, what will happen is that these signals will be still asserted. And since I activated another row, now I'll be asserting many more signals. So whenever I do that, now there are new paths, right? As you can see. So now we will be activating many more rows, not just 2. So what we observe is that this changes across DRAM architecture to DRAM architecture. And for the same DRAM architecture means, like, as we refer to the same die division and chip density, the same DRAM chip, you will have the same row decoder circuitry, which is already programmed, right? But if you change the DRAM chip, now it changes again. So for example, some of them you can activate up to 32 rows in the same subrow. In some of them, you can activate up to 60. In some of them 2, some of them 4, and some of them would not let you activate it. For example, what we observe is that for this, I think over the course of testing 400 modules or so, so most of the SK Hynix chips are capable of doing this. They letting us to, for example, when we violate it, we can actually activate many more. But Micron and Samsung chips do not have this much, let's say, flexibility. So whenever you grade to violate something, they will probably, what we hypothesize that they will probably discard the second activation because this is too close. So for example, this is 3 nanoseconds, right? As instead of 14 nanoseconds. So what we hypothesize is that they somehow thinking that this is too, let's say, greatly violated. Now there's something wrong with it, and it will discard it. So we couldn't actually find any Samsung chips yet. And some of the Micron chips are capable of doing up to 16, but yeah, maybe we need to figure out a way to perform this. But we believe that all chips, all tested DDR4 chips, even that we couldn't do, are capable of doing this, because this is a very core thing to the DRAM architecture, to quickly serve the activation command. There are many more, let's say, details in the second paper that I'm going to talk about. This is where we actually reverse engineer the row decoder circuitry. But again, as I said, I believe every chips are capable of doing such operations that we're going to show, even the ones we couldn't find. So what are the key results? So we find that the tested DRAM chips have 2 distinct sets of activation patterns when you go with neighboring subarrays. One is exactly the same number of rows in each subarray is activated. We find that you can activate up to 16 rows in 2 neighboring subarrays, a total of 32. And the other one is twice as many rows in one subarray is activated compared to its neighbor. So while you activate 16 rows in one subarray, you will be activating 32 rows in another subarray. And then this makes it 48 rows. So that was the first observation. And then let's go to the second one, which will be, yes.
This doesn't mean you can now select which rows you can activate. Activate multiple ones, but you don't actually know exactly which ones are being activated.
So what we did is that actually you can know if you figure out the function, right? So if you give the row addresses, you will be activating this rows because this is a fixed function. It's not dynamic. In that sense, you're right. So if I get a module that I don't know, I will be randomly activating some. But if you reverse engineer or you just straight brute force your way, you will be having a mapping. Yeah, this row will be activated this. Basically, this row pair will be activated this much row. Yeah.
But then even after reverse engineering, you only get certain patterns of activation.
Mhm.
The decoder has a certain structure.
Yes.
So this means it's not that the decoder can activate any type of pattern of rows. It can only activate certain type.
At the same time, you know. Yes. So, but the issue is that, for example, for these operations, you don't want to activate, let's say, 2 row groups at the same time in a subarray because of the charge sharing principles, you would like to have just 1 row group activate at a time. So prior work show that what you would like to have mostly is that you will have some sort of dedicated compute rows, and you will be activating them all the time. So whenever you go to the subarray, you will be copying your inputs to there because DRAM activation is destructive. So if you want to still store your inputs, you'll need to copy it to somewhere and then activate that compute rows and then write back to data. So in that sense, you will need to find one, hopefully a reliable one, which is very hard and it's not going to happen, unfortunately. But yeah, that's the case. You're right on that sense.
So in a certain sense, you can kind of locate what is the biggest number of rows I can activate in fashion. This is the rule we could use for copying and then doing operation.
Yes, for row clone is actually arbitrary because for row clone, as I showed, you need to deactivate the word line, right? So if you deactivate it, that means that you're activating a single row at a time still. So in row clone, it works in arbitrarily. Basically, you can activate any 2 row pairs for a row clone operation. But for the multiple row activation, you're right. You have fixated basically places to activate. But still, for example, if I give you the number, as far as I know, for example, if you want to activate 32 rows, right, you have more than 1,000 candidates that you can do, because think about if you have 1,024 rows, now you have row pairs of 1,024 multiplied by 1,023, right? So that's a huge million, basically. You have 1,000,000 pairs. So you can still find, not as the granularity maybe you want, but you can still find very high, let's say, number of candidates for your each activation. Any other questions? Okay. So the key idea is, as I said, for the NOT operation is very simple. We're going to leverage this NOT gate here. So the key idea is to connect the neighboring subarrays through a NOT gate by simultaneously activating or consecutively activating them. So this will be very similar to row clone, but it will be an inter-subarray row clone. So what we are going to do is that we're going to activate source. Source will share its charge and activate it, blah, blah. And then now, for example, if it's A, source bitline will have A, but the destination's bitline will have negated A due to the NOT gate. So if we activate destination, now you will have the negated A in the destination. So let's see how this works in a cell level. So this is, again, these are in different subarrays, source on top, destination in bottom. They both have 0, ground, and bitlines are precharged to VDD over 2. So we will first issue activate, which will connects the source to bitline. And then it will you will wait for the nominal timing again, and it will, since source has had ground, now it will drive the bitline to ground. And then since there's a NOT gate over there, destination's bitline will have VDD. And then we will issue precharge, but then we will issue destination again. Why? We want to keep, we want to connect the destination to bitline, and we don't want to lose the VDD over there, right? So that's why we're violating the timing there. And also we would like to keep the sense amplifier still enabled because we would like to serve that VDD to feed the destination. And as a result, after we wait long enough, as if it's a charge restoration operation, now destination will have the negated value of the source, which is VDD. So in this study, we try to quantify the reliability, which we call success rate. So success rate for a DRAM cell refers to percentage of trials where the correct output of a tested operation is stored in the cell. So for example, for this 4 trials, we have half of them is correctly negated, half of them is not. So the success rate for this cell is 50%. So for this testing, for each DRAM cell, we perform 10,000 trials. So we have two key takeaways from this NOT operation experiments. First is DRAM chips can perform these operations with up to 32 destination rows, and the temperature has a small effect on the reliability of NOT operations. So I'm going to show you the result for the first one only. So in the x-axis, we have the number of destination rows, the rows that we negate, stores the negated source value. And in the x-axis, we have the success rate. So here are the results. The first fundamental observation that we made is that there is at least one DRAM cell, actually many more, that can perform the NOT operation with 100% success rate. And we conclude that you can perform NOT operation with up to 32 destination output operands. But there's a trend that you can directly see. So these white bubbles here, circles, are showing the mean success rate. And as you can see, it decreases greatly when you increase the number of destination nodes. The hypothesis that we have is that this sense amplifier that DRAM has is designed to only serve a single cell at a time, right? So if you obey the DRAM timing parameters, that this sense amplifier will be only restoring one cell's charge. But now we have 32 cells. So DRAM is not, let's say, fully reliably restore the cell of those charges. But as you can see, there's a guard band that sense amplifier has. So until 4, we are almost good. But there, as you can see, there are still some outliers that performs really bad. So this could be due to two things. This could be due to sense amplifiers not being good enough, or this could be due to those rows are not fully activated. So there are some cases that you will be activating the rows, but we believe that some mats you cannot propagate that global word line signal. So now you won't be able to activate. So for example, you can see that oddly 25% has one outlier. So it's like 75% of them are not activated, but 25% of them get the result. So I believe still this shows that they are fundamentally capable, but the issue is they are not designed to do this operation. So we are doing everything outside of the spectrum to show the capability of what DRAM can do. So now let's take a look at the third one, which is, I believe it's an interesting one. So the key idea is to manipulate the bit line voltage to express a wide variety of functions. So for here, let's take, again, we have two subarrays. Let's think that we are precharged to the reference voltage. Normally it's VDD over 2, right? So in the top subarray, we have A and B. In the bottom subarray, we have X and Y. So when we activate them at the same time, these 4 cells, what happens is that actually the top subarrays become the function of the voltage A and B. Actually, the function is average. So the top subarrays voltage becomes the average of A and B, and the bottom subarrays becomes the average voltage of X and Y. And then when sense amplifier kicks in, it will compare the voltages like it usually does. And then it will amplify which higher one to 1, lower one to 0. So we're gonna leverage that or exploit. So let me give you an example for 2 input AND and NAND operations, how we can perform. So let's name the subarrays. So the top subarray is reference subarray, the bottom subarray is compute subarray. So in the top subarray, we store VDD and VDD half in the cells. So we can actually store VDD over 2 thanks to the prior work called frac theorem that you can actually activate the precharge. That cell will always sharing its charge to the bit line, and then you will immediately precharging. So cell won't be able to regain its charge. But if you keep doing that, they will have an equilibrium state because cell will only be able to share its charge until it's VDD over 2 because the bit line is always precharged to VDD over 2. So this is the frac theorem's key idea to store VDD over 2. So in the compute subarray, we will have X and Y. And assume that we violate the timings to perform multiple row activation, and we will activate these 4 cells at the same time. So let me iterate the truth table for you. And as I said, the function is average. So whenever we perform multiple row activation after the charge sharing, the reference subarray bit line will have the average voltage of VDD and VDD over 2, and the bottom subarray bit line will have average voltage of X and Y. So let's iterate the truth table for X and Y. So let's say that VDD is 1, ground is 0, and now let's take a look at the first row, X and Y, both are 0. So the average voltage of VDD and VDD over 2 is 3 VDD over 4, and the average voltage of 0 and 0 is 0. So when sense amplifier, after the let's say successful charge sharing operation, sense amplifier will compare the voltages on the 2-bit lines as it does in normal operations. Since 3 VDD over 4 is higher than ground, now it will amplify the reference subarray bit line to VDD and the compute subarray bit line to ground. So compute subarray will have 0, reference subarray will have 1. So when we go to X is 0, Y is 1, now it's higher than 0, it's VDD over 2, the average voltage on the compute bit line, but still it's lower than 3 VDD over 4. So when sense amplifier compares them, now still the result is the same. Compute subarray will have 0, reference subarray will have 1. And in the other case, it's the same, right? Still, we have the average voltage of VDD over 2, which is lower than 3 VDD over 4, and the compute subarray has 0, and reference subarray has 1. So when both are 1, now the compute subarray bit line has higher voltage than reference subarray's bit line, right? And now when sense amplifier compares it, the compute subarrays will have 1, and the reference subarrays will have 0. And if you take a closer look to this, the compute subarray is the AND operation of X and Y. And the reference subarray is the NAND operation of X and Y. So by carefully initializing this reference subarray, we can actually perform AND input and NAND operations. And this is the same for OR operations. So the key observation, the idea is that, so you should be able to distinguish when both inputs are 1, right? So in this case, you should have something higher than VDD over 2, which is one of them is 1, the other one is 0, something lower than VDD, which both of them are 1. So that's why we set the reference subarray bit line to 3 VDD over 4. So in the OR's case, what you want is that you want to distinguish 0, 0 and 0, 1, right? After 0, 0, you should have 1, all 1. So you need to be able to distinguish 0 to VDD over 2. For that, you need VDD over 4. So in order to perform OR, what you need to do is you need to initialize reference subarray with 0 and VDD over 2, which will give you VDD over 4 as an average bit line. So that was how we perform 2, 4, 8, 16 input and NAND OR and NOR operations. And here are the key takeaways. I'm going to probably show only one of them as a result. So the first one is we can perform these operations up to 16 inputs, and they can perform with a very high reliability, and data patterns slightly affect the reliability of these operations. So let's take a look at the one main result. So here in the x-axis, we have the number of input operands. In the y-axis, we have the success rate. And here will show the operations, different operations. So each different colored box represents a different operation. So as you can see, again, we can find a single or many multiple cells that can perform these operations with 100% success rate. But as you can see, the success rate increases when we go to the higher inputs. So we can actually, now we have a, let's say now fine granularity to control the reference voltage now. So because DRAM is not ideal, it's subject to a process variation. Sometimes you don't want that VDD and VDD over 2. This is a circuit level theory, right? What we show. So, and sometimes if you have more options, so for example, instead of having VDD in one cell, what you can do is VDD over 2, VDD over 2 in 2 cells. So that works sometimes better. Probably the process process variation that some cells are too strong, stronger than others. And as you can see, AND and NAND operation is worse than OR and NOR operations. What we hypothesize here is that this might be due to the sense amplifier bias. So there's a safe threshold that sense amplifier can safely amplify to VDD or ground, right? But there is not so reliable threshold. So below this threshold, sense amplifier can generate random values, which is actually some of the work show that you can generate true random numbers by that. So what we think is that here, and then wants 0 most of the time, or a NOR results in 1 most of the time, right? So what we think is that here, sense amplifier is biased towards the 1. So that's why in not certain cases, OR and NOR performs better than AND and NAND. But since we don't have the parameters or anything that we are working on black box DRAM, we cannot verify that. But that's the best that we can come up with. So that's available on arXiv, the extant version of this paper. You can take a look. As I said, I'll share the slides with you. And this is also open source, so you can use it. You can, if you have the FPGA, the setup that we have. DRAM Mender is also open source, so you can just start testing your DRAM chip if it can perform such operations. So this was the functional complete Boolean logic. Do you have any questions on this one? Or I can move to the second one. Yes.
Do you potentially damage chips?
No. As far as we know, it's been for me 4 years. I've been testing this, but it's still the same. So in the second paper that we show is that's the power because you activate multiple rows, right? But since you're not really activating other banks, it's not really increasing the power. So it's maybe a bit aging, but we don't know the aging as well. But still, they're working as the same before. But yeah. Yes. Every time, whenever we do an experiment, so I show that 10,000 trials for a given temperature, given data pattern, given something, right? So after each experiment, we recalibrate, we check again whether something is wrong. So we run a sanity check basically every time because we don't want to have faulty results there. But until now, we didn't have any issue. If you bake it to 130 degrees DRAM, yes, you have some issues. We tested that, but yeah, until we went for the previous one, we went until 95 degrees, which is also supported until 95 most of the chips. So that was no issue there. So the second one is simultaneous manner of activation in the off-the-shelf DRAM chips, experimental characterization and analysis. This was published in DSN 2024. So here, what we're going to do is that as I said, actually this was coming first chronologically, but some processes this published later. So here we actually reverse engineer the row decoder circuitry, and we were able to activate 32 rows at the same subarray. So in this study, we try to use this 32 row activation to different operations. So by leveraging the simultaneous manner of activation, now you can perform majority of x is greater than 3. You can actually increase the robustness of majority x, which is, I think, a very interesting one. And the third, now you can copy one row's content to multiple rows since you activate many rows at the same time. So for majority x, I believe it's very straightforward. As I explained you, instead of activating 3 rows, now you activate x rows. So this is, for example, if you activate 5 rows, you can perform majority 5. If you activate 7 rows, you can perform majority 7. But as I said, so DRAM chips are, we need X rows activation for majority X, right? But we can only simultaneously activate 2, 4, 8, 16, and 32. And what we do is that, for example, to perform majority X while activating more than X rows, we use some rows neutral. As I showed you, we were doing it VDD over 2, right? So since the cell theoretically has the same voltage level of the bit line when starting the charge sharing, it's actually not contributing compared to the others. So the idea is that if you want to do majority 5, what you do is that you can activate 8 rows. And for example, you will have A, B, 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 A, for example, as an input. And 3 rows, you will put them to VDD over 2. And this works actually pretty well. As the prior paper showed, they use 4 rows for majority 3. And for 8 row activation, you can use majority 5 too, and you can get some sort of reliability. And the second one is, you can actually increase the robustness of majority X operations using this. How? So the key idea is to store multiple copies of the same input operands to increase the robustness, which we call input replication. So this is majority tree, right? So A, B, and B. So when you perform these operations, first, due to the process variation and some other issues that you're activating multiple rows at the same time, the deviation is not that high enough in some bit lines. So the sense amplifier failed to amplify correctly. But the majority's good thing is that majority 6 of ABB is the same as majority 3 ABB, right? So what we are doing here is that actually increasing the deviation. So now, instead of having, let's say, epsilon, now you'll have 2 epsilon almost. It's not the case, but you can think of that. It's increasing the perturbation on the bit line so that now you can have a better perturbation and you will have the correct results. So in this, actually I should have put this in the other one, but so in this study, we test all rows in subarrays. We test multiple timing parameters because another thing is that not every DRAM models have the same timing parameters due to the differences in row decoder circuitry, array design. And we test 80, 60, 70, and 90 temperatures. And for this study, we actually reduced the word line voltage. We had a hacky way of doing things here that they had some sort of riser, DDR4 riser, and they had a shunt transistor there to go in for the word line voltages, and we were able to monitor it and change the voltage there. So what are the key takeaways? First, off-the-shelf DRAM chips are capable of performing mesh 5, 7, and 9, and we can significantly increase the success rate, and voltage and temperature slightly affect the success rate. But I'll focus on the first two. So here, in each subplot, you will see a different majority operation. So while we were actually activating up to 32 rows, but we didn't, as you can see, we stopped at 9. Because if you really go up, you're gonna see it. If you go after 5 or 7, I think it's not really stable because every row, every cell will have a different value. Some of them are trying to pull up, some of them are trying to pull down. You won't get really a reliable result. It's like really 5% of something. So this success rate is different here. The success rate actually shows, for example, if you do 10,000 trials, we call a bit line successful if every 10,000 trials are correct. So it should give a 100% success rate result. So this is, you can think success rate is a reliable bit line. In every case, it generates correct output because we wanted to see how this affects when we do input replication. So we have many data patterns, but we're going to focus on the first one. So this is 32 rows, and as you can see, we can perform the majority 3, 5, 7, and 9 with some sort of reliability, and you see this like an exponential decrease. So after 5, it decreases a lot for 7 and 9. But I think the very interesting result is that the input replication. So if you have 4 rows, you have no input replication. You have A, B, C, and neutral rows. If you have 32 rows, that means that you have 2 neutral rows, and you have 10A, 10B, and 10C to perform majority tree. And on average, the success rate increases 30.81%. And this is the same for all of them. For example, for majority 5, it increases more than 56%. And the final average success rate becomes 68% to 99.68%. So it really increases the success rate by a lot. And yeah, we conclude that storing multiple copies of majority's input operands increases success rate of such operations. And for the last one, it's one row's content, copying one row's content to multiple rows. So I think this is pretty straightforward still. So for example, what we were doing with row clone is that we were activating source to fetch the sense amplifier, and then we will write it back to the destination. So for multi-row copy, what we're going to do is that So now we have multiple destination rows, right? So since we activate multiple rows at the same time. So we will first activate the source to fetch its content to sense amplifier, and then we will violate the timings to activate many more rows. And then it will fetch sense amplifier's content to these multiple destination rows. And the robustness of these operations are actually pretty high. So on average, we observe that on average of 1, 3, 7, 15, and 31 number of destination rows, the average success rate is more than 99.98%. So we conclude that we can copy one row's content to up to 31 rows with a very high success rate. So the paper is also available in archive, and it's artifact evaluated. The core it's evaluated by the artifact chairs and members, and it's reproducible. So you can also go there if you have the FPGA. Now you can just run the code and check whether your DRAM model is capable of doing such operations. So this is this one, and I'm gonna move to the last one. So I have like 10 minutes, I think. 1 minute? 12, okay. Okay, I was scared a bit. So I'm gonna give you the key ideas very quickly, and then if you have any questions, I'll get that in the break. So this is hot hammer. So until now, I showed you what we can do with real DRAM chips as a computational capable thread. So here in this study, we analyzed the read disturbance effects of this processing using DRAM operations. I'm going to give you what read disturbance is and some backgrounds. So the motivation is that we can alleviate the data bottlenecks with these operations, and there are many ways, many processing using DRAM operations that we can perform, but all of them, most of them, are based on activating multiple rows, either in quick succession or simultaneously, either, for example, major tree or row clone. And the issue is that modern DRAM is subject to read disturbance. So repeatedly activating even a single row would induce bit flips in unaccessed rows. So now the problem is, now we are activating multiple rows, not just one row at a time. So what will happen to this read disturbance issues in real DRAM chips? So our goal is to understand and analyze these effects in multiple row activation, and we call this effect pot hammer. We test 316 DDR off-the-shelf DDR4 chips from 4 major manufacturers, and we observe that it exacerbates the DRAM read disturbance significantly, causing up to 158 times reduction in minimum activation count to induce the first bit flip. And it's similar to row hammer bypass system. It employed row hammer mitigation in DDR4 and induces more than 10,000 times more bit flips than row hammer. And we try to adapt the industry's latest solution to read disturbance to account for pot hammer bit flips, and we observe that still a straightforward solution will have an overhead of more than 48% performance overhead. So in this study, we categorize them processing using DRAM operations to 2. One is consecutive multiple row activation. You can think of this as row clone. We are activating one row, and then we are activating another consecutively, but in a quick succession. The other one is simultaneous multiple row activation, as I showed you for majority and NAND or a NOR operation or multiple row copy operation. So for consecutive multiple row activation, what we do is that we evaluate the timing to precharge the activities. And for simultaneous multiple row activation, we evaluate the timing between activate to precharge to activate, right? So what is read disturbance? Let's take a look at that. So unfortunately, even activating a single row disturbs the data integrity of other unaccessed rows. So the prominent example for this is row hammer, and now there are row press and column disturb phenomena for read disturbance. So basically, you're activating a row, which is called aggressor row, and you keep activating, opening and closing. After a certain time, now you will get bit flips in nearby rows. For example, you activate row 2, and now you hammer row 2, and now you have bit flips in row 1 and row 3. And this phenomenon calls row hammer. So the problem is that no prior work investigated such multiple row activations effect on read disturbance, and we try to understand what will happen to this vulnerability with multiple row activation. So we test a bunch of DRAM modules and chips in 4 major manufacturers for this one, and we cover again different die region and chip densities to see the effect of different DRAM architectures. So how do we hammer? How do we perform this operation? Let's take a look at for row clone, which we call comma, right? So what we do is that there are 2 different types of performing row hammer, let's say, the main. One of them is double-sided, in a sense that you're activating aggressors one by one. Here you have 2 aggressors, but you're sandwiching a victim row. You can think of that we are copying one row to another row while sandwiching one in between as a victim. The other one is single-sided. What you have is you have only one DRAM row that you have as an aggressor, and you keep hammering that. It's like one side, right? And this is double-sided in the sense that you have rows and a victim experience bit flips from this double-sided aggressors. So for our case, what we do is that we copy one row to far away row. So basically to imitate single-sided row hammer. So we use a metric called HC first, which is the minimum hammer count required in this first bit, lower is first. And one hammer count is actually, you can think of that one row clone operation, or basically activate one aggressor and then activate another one that is one hammer count. And let's take a look at the result. In the x-axis, you see the manufacturer. On the y-axis, you see the lowest HC first that we observe from their models. So, and the color will indicate whether it's row hammer or comma. So for example, for one manufacturer, SK Hynix, we observe that this row clone operation decreases the lowest HC first by almost 14 times compared to double-sided row hammer. And this also a similar case for many other manufacturers. They're not that affected by it, but as you can see, it's 3 times, 1.5 times, and so on. And we try to see this was the extreme case, right? Lowest HC first. And we try to see what will happen in general case when we consider all victim rows. On the x-axis, you will see DRAM rows sorted by reducing HC first changes, and each line will correspond to a different manufacturer. So for example, P1 to P100 represents 99% of tested victim rows, P50 to P100 represents 50% of tested victim rows, and HC first change, if it's negative, that means that COMRA reduces HC first compared to double-sided row hammer. So for example, if it's minus 50, that means that, for example, row hammer HC first was 100, now COMRA's HC first is 50 for the same row. So as you can see, we observe that more than 99% of tested victim rows experience lower HC first, and there are some extreme cases after P90's point that it almost have, let's say, 10% of the tested victim rows experience more than 50% of HC first change. So that was COMRA. Now let's take a look at simultaneous multiple row activation. So the difference is that now in COMRA, it was very similar to row hammer. We were activating one and closing another to activate another, the other row. But we had lower time in between, right, in COMRA. But in SIMRA, simultaneous multiple row activation, now we are activating multiple rows at the same time. This is basically fundamentally different than what we were doing with row hammer and COMRA. Now, multiple rows are activated simultaneously compared to the others. So here in the x-axis, you will see the simultaneously activated rows. One is row hammer, basically. 2, 4, 8, and 16 is different patterns of simultaneous multiple row activation. On the y-axis, we are going to see the lowest HC first. So the result is that row hammer, the lowest that we observed was around 4,000. Now with SIMRA, that decreases to 26. It's more than 159 times. So double-sided SIMRA decreases the lowest HC first by 159 times. So this looks very bad, as you can see here, but this actually can be avoided by designing your chip, I think, in a way that it will account for that. In the paper, we argue for this. So let me show you the result, but probably I will not have time to go through the mitigations. So, and this trend was again, the extreme case, right, the lowest. So we checked again the same thing we test all the victim rows. As you can see, more than, again, 99% of tested victim rows experience lower HC first, and more than 25% of them experience more than 99% of HC first reduction. So if row hammer HC first is 100, 25% of their rows is 1. So it significantly decreases the majority of rows compared to row hammer. So in this study, we analyzed the effectiveness of existing DRAM row hammer mitigation and adapt the row hammer mitigations to account for path hammer. So I'm gonna quickly skip the first one because current DRAM chips, current row hammer attacks can already bypass this DDR4 mitigation, which is called TRR. And again, with Simra, we can induce many bit flips compared to row hammer when even this mitigation is active. So for the second one, we try to adapt the row hammer mitigations to account for path hammer. But this was shown as an evaluation. But in the paper, what we argue is that, so normally, as I said, you will need a compute rows to perform multiple row activation, right? You will copy the rows from the compute rows. So if they have an isolated part, for example, you will add 2 more isolated rows in between the storage rows and compute rows, they wouldn't get affected. So basically, and since we activated that compute rows, they wouldn't be able to affect the nearby rows if we let's say design the DRAM chips carefully. And you will need to still dealing with the row clone induced bit flips. So to show like how we can adapt the row hammer mitigations, we use PRAC, which is the industry stated solution to row hammer, called per row activation count, which counts the activations, basically, how many times that I activated the row. After certain threshold, I'll do a preventive actions, such as refreshing the nearby rows. So one approach is the naively reducing the threshold to what we observe, for example, 4,000 to 20. Other one is you will be counting differently. For example, for row hammer, you will be counting an activation to 1. For Simra, you will be counting, like increasing the counter by 200, so that you will have a heterogeneous counting. So we use a emulator too, a cycle level DRAM simulator, and we tested 60 multi-program workload mixes. In our cases, we had 4 CPUs, and we had 1 PIM unit that will always issues, let's say, Simra or Tomra operation with a given interval. So the interval is the x-axis, as you can see, for example, 125 means that DRAM performs processing using operation in every 125 nanoseconds, and the y-axis shows the normalized weighted speed up, which is normalized to no row hammer mitigation. So the purple is a naive, that we reduce the threshold, at the VC is weighted counting. As you can see, the VC, the optimized adapted version, grade outperforms it until 2 microseconds, and it doesn't incur that much of latency performance loss. But in the extremes, it increases almost as same as the PRAC naive. So on average, you get 48%. On maximum, you get 98% of performance overhead. So you can think of that there could be some throttling plus these kind of approaches to mitigate such issues. There are a lot more things in the paper that I haven't shown you: temperature, spatial variation, timing, access pattern, etc. What will happen if we combine row hammer with processing using operation? So for example, you will first start with doing row hammer, and then you will switch to row clone operation or Simon operation, which reduces the HC first again. And there are more details on how to mitigate path hammer that we discussed. How can we modify DRAM chips to account for this? But I think that will be more promising than what we have shown here. And the more details on the adaptation, how challenges, and maybe another area efficient solution, and so on. The paper is available in archive, and I guess that concludes the talk. Thank you for bearing with me, and I'll get questions if you have any. Thanks. Yes.
I have a question. I thought one slide you showed in this last presentation, I think it was around slide 110. So it's the
This one.
This one,
Yes. They are old ones. They're very old.
Oh.
They're from 2016 or 17. So due to the DRAM scaling issue, the newer ones have very low thresholds. But these Nanya ones that we had was very old, around 2016 and 17. That's why we don't have that much, that low HC first on them. Thanks.
So it's not the same process, it's a chips for different processes.
We don't know the processes, so they're proprietary. We just know the die revision and chip density, and usually newer die revision they show first generation, second generation. So if you have same chip density and different die revision, that may say something, but in different ones we cannot really compare the different ones. So
this was all same. So this was all like 4 megabit chips, or
so, for example, for SKNs, you have 16 gigabits, Micron, you have again 16, and Samsung, we had 16s. But even, for example, some 8 gigabit, but R dies is better than 16 gigabit A dies. So, in a sense, that lower HC first. So, we really don't know also. What we can say is that for the same manufacturer, for the same die density, if the chip, if the die division advances A to B to C to D, we can make a comment on the scaling. But if, for example, we usually don't compare 8 gigabit to 16 gigabit because they can just double the subarrays or do something else there that we don't know. Yeah. Yes.
So,
Mhm.
Lovely to hear your presentation over. One of the things we've been thinking a lot about is CMOS image sensors.
Mhm.
And CMOS image sensors look like a DRAM.
Mhm.
And
Okay.
they also do multiple activation.
Yes.
They could think
Mhm.
also by any of your reasoning about DRAM to image sensors.
I think it will be very hard because the manufacturing process is so different because DRAM has a different process, manufacturing process, right? So you need to bury the gates, and it has capacitor and transistor, which is very different than CMOS technology. That's why we cannot really easily add what we want to DRAM because it. Really, yeah, they might have that issues as well, but I cannot really comment on that because I haven't. Yeah, I don't know. Thank you. Thanks a lot. Okay, then, is there any other questions? Okay, then we will have a break and we will be here, I guess, in 25 minutes with the presentations. Thanks. Yes. I'm going to introduce you. Hello, everyone. Welcome to the before lunch session, second session. So we will start with Ataberk. I pronounced it correctly.
So
They.
yes.
Okay.
Well,
So
whatever.
he's a senior engineer at Samsung SDS, and his recent work focused on efficient AI serving platform on the Samsung Cloud platform, including top-tier conference publications such as ISCON HPC. He holds a bachelor, master's, and PhD in computer science from the Korea Advanced Institute of Science and Technology.
Thank you. This paper, OmniMP, is an extension of a previous work, PAIAC. I don't know how to pronounce yet. And sorry. Oh, yes. So this short paper is an extension of PI's PIM accelerated inference scheduling engine for transformer-based LLM, which is presented at HPCA 2025. So the basic thesis about PIs is that how to use PIM in AI inference tests. So because the PIM memory region is very limited compared to the total memory space, we had to select which layer, which is a linear or attention layer, to offload to processing in memory, or not to use processing in memory. And suggestions on a new attention layer offloading mechanism that does not implement it in the original Samsung Electro-X version. But in this paper, we extend the PIs as a full implementation of batched GMV kernel, overcoming the hardware native size of 4K rows to 256 columns. And we made an abstraction of all the linear layers and attention layers into batched GMV. So the Python model programmer does not have to consider the size of each weight metric size for using the processing memory. So we have to start from the scratch that for using the LLM inference, the transformer-based LLM inference, we do not consider about the prefill phase because it is computation bound, but we only focus on decoding phase for generating one by one tokens. In this decoding phase, the tasks are memory-centric because operations cannot be batched by GM and like fully connected linear layers in attention layers. As batch sizes goes up, then the size of the GMD operation goes up, and we have to access more memories in attention layers. So this is the core part of the memory-bound task of the decoding phase. So because GPU uses a SRM cache, GPUs are beneficial for GEMM. However, as the number of requests are going down, the processing in memory becomes efficient. So we are only focusing on the request size smaller than 4 for using the processing in memory. So when we leveraging both LLM inference for between GPU and PIM, we can lead to better overall performance for the decoding LLM inference tests. So we use Samsung HBM28 PIM for the LLM inference, and its GMV architecture uses the register file A as an input, and the weight matrices resides in the subarrays, and the GRFB becomes the accumulation output. So this is the way that the Samsung HBM PIM works for GEMB operation. But the processing in memory can only reduce the multiplied output into 32-byte aligned columns. So for the final output, we have to make an additional GPU kernel for reducing the 32-byte output into 2-byte output. So as seen in this picture, the one column has 16 elements of FP16 elements. So as there are 8 by 8 columns, we have to consider 8 rows and 128 elements for the each banks. So we have to consider as a total 1K banks with 496 outputs and 256 inputs to maximize the bank level parallelism. However, most weight matrices are not the multiples of the 4K by 256, and in that case we have to zero pad to fill the other regions of the optimal size. So in that case, the GMV operation performance degrades. So it is super inefficient. So why we have to zero pad? So the partial sum is written in GPU main memory, then we further reduce the partial output into final output by using a separate reduction kernel separate reduction kernel. So so we cannot concatenate the matrix both in row and column wise because the reduction phase eliminates the eliminates. So what we use is the interleaving multiple weight matrices into one GMV operation with interleaving different weight matrices into 32-byte wide transactions. So when we interleaving two different weight matrices in 32-byte transaction-wise, we just multiply in PIM. A transaction-wise addition is performed in PIM. Then we just modify the GPU reduction kernel that does not add partial results from different weight matrices, then can reduce multiple batch GMV operation. So as the processing memory adds the transaction weights, the element sequence within the transactions are aligned. So we can separately reduce the partial output into final output. So with interleaving the weight matrices, with adjusting input vectors and output vectors, we can combine multiple GMVs in one PIM kernel. So we can reduce the overhead data movement and memory allocation for in input wise. As the attention layers are always memory bound with without the consideration of the input size, request size. So we are always offload the attention layer to process the memory, and when the request size is lesser than 4, we also can use the linear layer as a PIM offloading logic. So we made a dynamic scheduling algorithm for how to map the weight matrices into processing memory and scheduling logic to partially offloading the attention layers and fully connecting layers. Evaluations were used with AMD MI100 GPU with custom HBM PIM chips provided by Samsung Electronics. So I am appreciated to provide this access for these devices. We use very small models because it was very size limited for without causing out of memory issues. So we have to reconstruct the input and output vectors for the interleaving the batch GMP. So in this case, we were we had to observe the attention score layers with query multiplying query and key had highest reconstruction overhead of output transactions because the output size is larger compared to input size. And so since the weight matrix is very long and narrow, we have to make the attention score layer produces long output chunks that have to copy between the processing memory region and HBM region. The linear layer, offloading the linear layer is beneficial until batch is 2. When batch is 1, we can both use fully connected layers and attention layers. Then, in this case, with super long output and super short input, with very small batches, how can we do much more better? Or super long input and short output, and how can we do much better performance for in this extreme matrix cases? So we just cut the matrix and move to the next step. Move to the next one. So in both cases, we could just cut the matrix and move them for better occupation in each 4K 256 unit size. So we can reduce the number of page sizes. With using interleaving and cutting the matrices, we could make all of the 6 processing in memory mappings as shown as like in this slide. So we could abstract the batch GMP from LLM layers. So for with the weight number of weights and number of input and output vectors per weight and the weight height and width, we could just map all of the cases that is possible for the optimized PIM processing in memory unit mapping. So the model, the AI designer does not have to consider how to make the linear and attention layers to be PIM aware and friendly cases. So in addition, we could skipping the GMV operations in several cases. Memory allocation requires maximum usage, but we could skip unfilled token spaces. In this case, we could just skipping the number of the PIM GMB iterations. Which makes shorter attention computation. It is beneficial for decoding phase. We used for probability and value multiplication usually, because the input sizes is multiples of 256 compared to the multiples of 4K in output, so which is much more fine-grained control for unimetrics. So we're just skipping, and it makes it more smaller PIM operations. We use the same GPUs and PIM devices. We added some larger models with only benchmarking with one layer for mitigating the OOB cases, but with several iterations, we could characterize the performance of large models. In this result, we can make about 40% faster performance over GPU-only executions. For large batches, the KV concatenation time is reduced very well, and for batch one, the linear layer execution time is also reduced, but in batch 4, we had minimal effectiveness on PIM execution, as we don't have much space for further optimization on linear layers. So PIM can be used for boosting LLM inference, but careful matrix mapping is essential for reducing the number of the PIM unit sizes. Including the manipulating the matrix mapping and skipping the computing could be beneficial for LLM inference. So thank you for my listening. So is there any question about this one?
Any questions?
Okay.
I think the characteristics of as you mentioned,
Yes. We dynamically switches between offloading to PIM and using the GPU by checking the batch size dynamically. So in this case, the linear weights are copied with two different mappings for GPU-friendly mapping and PIM-friendly mapping. When the request then the batches of request comes, our work detects the number of requests dynamically, and when the request number is smaller than 4, we use PIM for acceleration. When the number of requests goes up for 4, we use GPU for the linear layer acceleration. I know, but so this is out of our company scope, that is the electronics scope. So I think they would know that those problems. Or what I think they will do some kind of works to advance and mitigate those of your problems. But as an SDS person, I could not do anything more than that because I cannot make an hardware in my company. Maybe they will hope. I hope. Chop. What? So we cannot cut more than 16 in 16 cuts because, as you can see, in one transaction we can only put at most 16 weight matrices. We just cannot cut more than 16. So maybe it depends on how long the output dimension is, and when the number of batches is larger than 16, we don't have to cut the matrix. So in that case, so in that case we don't have to cut the matrix so I think the output vector manipulation does not seem to be a very large enough for the batch GMV manipulation. So we have to, if we have enough access for the device, I have to check about that. Is that an answer? Okay.
Which precision are you using for
our precision setup is fixed to FP16 because the hardware only supports that. So
for example, if we use the int for a kind of low precision, then I think the memory is
we could not compare the lower precision formats because the MI 100 is very old version, which I think it is produced and launched at 2021. Does not support narrow precision, so it is nowhere to compare the of your question. Okay.
This is based on HBM2, the HBM10.
Yes.
Do you have any versions of HBM2 or 3 that will benefit from the bandwidth much more than HBM2?
Our company has it, but because it is with different GPU and different PIM version mapping, it is not that it is not beneficial for comparing different GPUs with different PIM, HBM version mappings for the comparison and the. as a baseline experiment. So I think it's nonsense.
In the GPU side, you have GPU's memory and also HBM PIM or
the HBM PIM has two ranks. Rank 0 is normal HBM, and the rank 1 is the HBM PIM. Okay, so the chip itself has half of normal HBM and HBM with PIM, so you can switch between them.
Or some HBM to PIMs.
Yes.
Or are those pseudo channels or like? Okay, now I understand.
Yeah.
All of them is for HBM.
Yes, so all HBM PIM4 chips, which are connected to MI100 GPU, for each pseudo channel has two ranks, and what rank 0 is normal HBM, and then rank 1 is HBM PIM. So we can switch between them by manipulating the physical memory addresses. Yeah.
You don't basically don't have a standalone HBM and card or anything. It's just attached to the GPU.
Yes.
Here it says 4 gigabytes to 8 bytes, so it looks like it's 2/3, 1/3.
So, yes, so as the PIM logic region has about half of the subarrays, so the size of the PIM reduces to half. So the configuration of each HBM to PIM consists of 4 gigabyte normal HBM2 plus 2 gigabyte HBM2 PIM with same logic layer. So yeah, the size reduces to half.
Okay, but then this means your rank 0 is bigger than rank 1.
Yes.
Do you get addressing problems?
The addressing problem was fixed by custom AMD GPU kernel driver provided by Samsung Electronics. So we don't have to consider about this. No question. Thank you very much.
So the next one is Chris. Wait. I cannot go there. Yes. Please. I'm gonna introduce. Sound check. Yeah. So sound checking is going to present sound checking an efficient HBM-based PIM architecture for linear complex zero-knowledge groups. He's an undergraduate student at University of Engineering Science program in fourth year, and his main interests are in security, privacy, and open architecture. Feel free to start.
Good morning, and thank you, Ismail, for the introduction, and really happy to be giving this presentation today. So I'll be presenting some PIM. And this is a joint work between University of Toronto and Korea University. I'll also be presenting this work during the main conference on Thursday from 3:30 to 5:10, which is the efficient privacy computing session. I'll be presenting in the order of the background, motivation, and then the subject team architecture, and then the evaluation. So on background. So what is a zero knowledge proof? So a zero knowledge proof is a cryptographic protocol between a prover and a verifier that lets a prover convince the verifier that statement is correct without revealing anything beyond its truthfulness. And it has numerous applications. So it has been mainly deployed in blockchain systems, but there are upcoming applications such as anonymous voting, zero knowledge machine learning, and zero knowledge virtual machines. In particular, ZK-SNARK is a family of zero knowledge proofs that provide non-interactivity, succinctness, and what this enables is that it shifts all the bottleneck from the communication, which is the characteristic of interactive ZKPs, to with non-interactive ZKPs, you don't have that communication bottleneck, so it enables much better hardware acceleration. So zero knowledge proof protocols differ in their underlying algorithmic primitives. So classical ZKPs rely on algorithms such as number theoretic transform or multi-scalar multiplication, but a growing class of protocols are built on the sum-check protocol, which gives a superior linear complexity. And this is in contrast to NTT, so number theoretic transform based protocols, which are n-log n in time complexity. And a lot of recent works in zero knowledge proofs have been utilizing the sum-check algorithm. So you can see in the table that so Groth 16 and Plonk are deployed quite a lot in real world, but they both rely on MSM and NTT, while more recent works have been all using sum-check basically. So correspondingly, it's also been gaining a lot of interest from hardware acceleration. So the first work that really focused on accelerating sum-check was the NoCap paper in Micro 24. And there's been several like accelerator and GPU-based work since. And the most recent work is the work called Gen ZA from ISCA 26. So how does sum-check protocol work? So I'll mainly highlight the data flow of sum-check and ignore all like the cryptographic details. Sum-check runs in rounds over a working set, reducing the size by half each round until it collapses to a single value, following a binary tree reduction pattern. So for each round, we perform per point modular arithmetic across the working set, which there's more detail in the paper, but it's called like extensions. Then you accumulate the working set to compute the sum, and then hash the sum, where the output is known as the challenge element. And this process of hashing the sum is known as the Fiat-Shamir heuristic, which gives you the non-interactivity property. And then once you have the challenge element, which is denoted as R here, you use that R value to interpolate between two elements of the current round, and then you fold them into a single value, shown in the image here. So, and then you repeat this process until you have fully reduced the binary tree. So I'll go over the motivation for our sum-check PIM work. So why accelerate sum-check? So we profiled open source ZKP libraries that use the sum-check protocol, and then we identified that sum-check takes up significant runtime, ranging from 54 to 76%. And this was done on a single-threaded Intel Xeon 6330 on DDR4 memory. And previous works have also identified that sum-check is runtime dominant. So the NoCap paper that I mentioned reports 70% of its accelerator end-to-end runtime, and Hyperplonk, which is a cryptographic like protocol paper that was evaluated on CPU, also reports 61% of its end-to-end runtime. So how to accelerate some check? So as I mentioned, it largely follows a binary tree reduction pattern. And there's two ways of processing this sort of binary tree reductions. So either you can process it in the breadth first direction, or you can process it in the depth first direction. And depth first direction usually gives you much low like cache locality, while the depth first approach or hybrid approach between depth first or breadth first gives you much higher cache utilization. However, as I mentioned before, the depth first, or because of the hash dependency, depth first or hybrid approaches are forbidden. So where if you want to calculate any values of the like lower rounds of the tree, you need to first compute the entire per point modular arithmetic sum and then the hash of the previous round. So what this gives you is that you are only able to perform this in the breadth first direction. So the structural property of some check forces low locality processing. So some check structural property has measurable consequences. So we used a open source GPU kernel that has the some check support, and then we measured the SM occupancy and DRAM throughput over different constraint size. And then we noted that DRAM saturates from 77 at the smallest problem size to 95% at the larger problem size, while the GPU compute remains underutilized at only 25% throughout the entire constraint size. And then we also, so this was over different constraint sizes. And then we also performed memory bound profiling on per round statistics. So what we measured was the latency per round and the L2 miss rate per round. First thing we noticed is that the early rounds dominate runtime. So the first 5 rounds make up 97% of the sum check runtime. And the same early rounds also have very high cache misses. So this aligns with like what you would expect from processing a binary tree reduction in the breadth first direction. So we reached the conclusion that some check is memory bound and dominated by weak locality. So processing in memory is an architectural paradigm that moves the compute to the memory. And many works have demonstrated the effectiveness of PIM architectures for memory bound workloads. We based some check's design on the Samsung's HBM2, which was published in ISCA 2021. So there are a couple challenges of accelerating some check on PIM architectures. There are 3 main challenges that we identified. The first is that we have to, so first, PIM architectures often use a low bit like 16, FP16, like SIMD in their bank units, while in the sum check we need 256-bit modular arithmetic, which is for security reasons. And second, for each round, to process some check, you need 2 levels of interbank communication. So every round you need to perform a global accumulation across all banks. And in later rounds, once the working set size becomes smaller than the number of banks, you would have to perform across banks. And the third thing is, as I'll show in a later slide, folding progressively destroys DRAM locality as working set halves each round. Efficiency per DRAM activation reduces. So to solve the first challenge of large bit width, we exploit the 32-byte burst length of HBM. So HBM, like each read, you get 32 bytes, which also aligns with the 206-bit modular arithmetic requirement. So each of our nearbank processing units have a scalar 206-bit modular arithmetic adder and multiplier. And so we have nearbank processing engines per every bank pair, and bank local computations of per point modular arithmetic and local accumulation are mapped to the nearbank processing engine. Nearbank processing engines can handle bank local computation, but within some check, as I mentioned, per round accumulation and later interbank folding are inherently global. So we handle communication by introducing two units on the logic die, which we name Fiat-Shamir unit and the interbank processing engine. So the Fiat-Shamir unit handles the per round global communication. It has an adder tree, accumulation register, and a hash unit. So within a round, all the nearbank processing engines compute the per point modular arithmetic in parallel. Then the partial sums are streamed down through the TSPs into the FSU's adder tree, which combines into a global accumulation. Then the global sum saved in the accumulation register is fed into the SHA-3 hash unit, which produces the next round challenge. And the challenge is broadcast to each of the banks, so each MVP has the challenge element to use for folding in the next round. So now that like each of the banks now have the challenge element, you can they can all fold each bank's working size in half. And we know that this works as long as each bank has more than one element. So you need at least two to fold. So if you continue this process, eventually every bank falls down to a single remaining element where you now need to fold across banks. And we tackle this problem by introducing the interbank processing engine, which is just data buffer and then modular arithmetic units. So each bank sends its remaining element, which will just be one in this case, to the IBP engine's data buffer. And then the remaining rounds are performed entirely on the IBP. And during this process, we reuse the adder tree and the hash unit in the FSU. So we add some data path to do that. In our paper, we also include an optimization to reduce the required data buffer size by half. And this cuts the logic die area requirement by almost half. There's more detail in the paper. Now to challenge number 3, we note that row locality diminishes with folding. So to illustrate that, so initially we could have fully like a bank densely packed with all active data, and where if you do an activation, you will perform the maximum number of operations per row activation. However, since you're folding and the working set data size reduces by half, by round I, each of the row contains very few active working set data, and the operations performed per row activation diminishes. And once each rows are fully reduced, folding between rows require 2 row activations to fold 2 elements. So this we realize is very inefficient. You could imagine, like for example, in round 1, you could imagine some strategy where you try to combine 2 of the rows into a single row, but that will require you to activate each rows twice per round, which we note that won't be the optimal solution. So the question then becomes, how can we maintain maximum number of operations per row activation while activating each row only once each round? So we achieved this optimal folding using our proposed DRAM-aware folding scheme, which has 2 ideas working together, which are row packing and bank ping pong. With row packing, we pack the folded results from multiple source rows into a single destination row so that the destination row stays dense and operations for activation stays at maximal value. However, if you try to fold within a single bank, you have to write the packed row before you can activate the next source row, resulting in bank conflict. So what we do instead is that we use bank ping ponging, exploiting the 2 bank per PIM unit configuration, where we instead write the folded output to the opposite bank. And since now the source and the destination rows are different, we now move past the problem of bank conflict. And after a round is completed, only one of the 2 banks are populated. So for the next round, we folded from the other direction. So in this example, we went from the even bank to the odd bank. And in the next round, we go from the odd bank to the even bank. And our proposed DRAM-aware folding scheme reduces row activations by 73%. So this doesn't work directly with like the default HBM PIM architecture. We had to change the command scheme a little bit to provide information on like which directions you're folding from. And this we done by using unused bits in the all-bank PIM mode of the HBM PIM. So moving on to the evaluation. For our evaluation, we modified DRAM Sim 3 to evaluate some chip PIM. And as baseline, we select NVIDIA RTX 8000 and Intel Xeon 6330. We run the Suncheck backend provided by Icicle 4.0 library, which includes CUDA kernel and multi-threaded CPU implementations. And we evaluated on constraint sizes from 2 to power of 20 to 2 to power of 25, which are a representative scale of like current state of hardware acceleration. And hardware configurations are summarized in the table here. And here are the performance results of Suncheck PIM. So Suncheck PIM delivers 5.3 times to 13.3 times speed up over the GPU baseline, and 334 to 361 times speed up over CPU baseline. And our proposed DRAM aware folding scheme provides 2 to 4.1 times speed up over the baseline that does not have that optimization. And Suncheck PIM also provides a significant energy reduction over the GPU baseline. We evaluated a 64 to 83% energy reduction versus the GPU, and a 15 to 76 times energy delay product improvement. We have additional evaluations in our paper on area, power, and also sensitivity studies, which we done over HBM generation. So we also did it on HBM3. And then we also do a sensitivity study of 4 PIM die configuration versus 8 PIM die configuration. So to conclude, the Suncheck protocol is a popular and growing ZKP prover algorithm. And our key finding is that unlike previously focused on ZKP algorithm, Suncheck is severely memory bound. We built Suncheck PIM, which includes near-bank processing engine for local field arithmetic, logic die units, the Fiat-Shamir unit, and interbank processing engine for global operations, and a DRAM-aware folding scheme to preserve row locality through folding. And the results is up to 13.3 times speed up over GPU baseline as the first PIM architecture to accelerate Suncheck protocol. Thank you.
Any questions? Is there any result with the temperature and the power consumption in the simulation?
Oh, yeah, I don't know about if there's any like, because this is all based on simulations. I did not have any like temperature based. I don't have any temperature based evaluations.
Is there any assumption include or including such logic units with some assumption with these logic units will consume somewhat energy for and then calculating the maximal power consumption for this.
Right. So I guess we included, or we have logic units on the logic die, but we note that they don't have like too much power based on our like synthesis evaluations. It was a little hard to evaluate like what's like reasonable or not, but I guess what I can say is compared to what's already out there, my work is much less ambitious. Yeah.
Didn't fully understand the necessity of going breadth first, so you cannot go depth first because of some problems.
Yes. So, okay. So to process this element, you will need the entire accumulation of the nodes in the previous round. And that's what I mean by only breadth first is permitted. No, it depends on the. So you see, it depends on this R value here, which is dependent on the sum of the entire. So you cannot.
So this is the hash is on the sum
Of the
everything.
yes.
It's not on the sum. The hash is
No.
not on the sum of the elements.
It's the entire thing.
Sum of everything.
Yes. Yes.
And so it continues like that. So in round one, again, you need the sum of everything.
Mhm.
The overall sum.
Yes. So there are some like compute-centric accelerator works that try to do like depth first or hybrids when you're trying to do the accumulation itself, but fundamentally you cannot process this full sum check binary tree reduction pattern in any depth first or hybrid approach. So that's like not possible due to dependency.
So you described an PIM reduction to so-called sum, but then you have to apply stress function.
Yeah, so that the sum reduction across banks and the hash unit is what we call the Fiat-Shamir unit, which is the cryptographic name of this add and hash thing. So
Okay,
yeah.
so you have a specific circuit.
Yes, and this is on the logic die, so of the base die of the HBM, and these are all the parallel units on top of it.
Gray part is in the logic die.
Yeah, these are logic die.
And then this multiplication addition is not brackets Samsung HBM and MCCSys-7.
No, so we propose like a different like PIM architecture.
Okay.
Yeah, this one. So Samsung HBM PIM, you have like FP16 SIMD, but here we need 260-bit modular arithmetic. So we instead put a scalar 260-bit modular units. So it has some overhead over some, Samsung HBM, I guess somewhat significant overhead, but like the limitation on like the entire die size, which is I think you cannot go over like 1.25 times of the original PIM die, we satisfy that constraint. Yeah.
Thanks a lot.
Yeah, thank you.
So the next speaker will be online, so I'm going to set up that quickly. Tatsuya, are you here?
Hi, Ismail. I'm here.
Can you share your screen?
Okay. Yeah, I'm sharing my screen.
Give me a second. Okay. Is your camera on or off?
Oh, okay.
Give me a second. Okay. You can go ahead now.
Okay, thank you. Thank you very much.
Wait
Okay.
wait a second.
Bye.
What happened?
So the black magic design should be able to play through the speakers.
Oh, but it's
Saves you having to do
it's fine. No, but I can put it like
more
it is.
feedback within the room. That
Ah.
might be a bit too quiet. So if you just go on your computer's output settings, then sound.
Let me do that. Yes, black magic.
Yes, if you just click that.
Yes. Tatsuya, can you try?
Sorry, what? What should I try?
Oh, okay, wait. So maybe I should check. Speaker. Can you speak again?
Yeah. Hi. Do you hear me now?
Okay, now it's good. Yeah, please go ahead.
Thank you. Thank you, Ismail. Okay. Okay, hello everyone. I'm sorry that I cannot attend in person, but I'm very grateful to the organizers and for giving me this opportunity to present our work. My name is Tatsuya Kubo from the University of Tokyo at RIKEN. Today, I will talk about MV-DRAM using real DRAM to accelerate matrix vector multiplication in LLM inference. Let me start with a high-level motivation. In a conventional processor-centric system, the matrix is stored in DRAM. And the processor reads the matrix data from DRAM and performs matrix vector multiplication on the processor side. This data movement is the bottleneck. The processor spends much of its time and energy moving matrix data across the memory interface, especially for the low arithmetic intensive workloads such as large language model inference. Our approach is different. Instead of reading all matrix data out of DRAM, the processor sends careful controlled DRAM commands to the DRAM. These commands cause computation to happen inside the DRAM array itself. Doing the computation inside the DRAM, and the processor then receives only the computation results. In our evaluation, the average matrix vector multiplication throughput reaches about 1.38 times the raw memory bandwidth. So we effectively achieve to go beyond the memory bandwidth limit. This talk has 5 main parts remained. First, I will give background. Second, I will explain the motivation. Third, I will present the rhythm and architecture. Then I will show the implementation and evaluation results. Finally, I will summarize the main key takeaways. We begin with the background. Normally, DRAM is operated according to a strict timing specifications. With these normal timings, only one row is opened at a time, and the data is retained correctly inside the DRAM. However, interestingly, processing using DRAM techniques or PUD intentionally uses commands with non-standard timings. By shortening some timing intervals, we can exploit the analog behavior of DRAM cells and sense amplifiers to perform useful operations. The first primitive is row copy. If we issue commands with a shorter interval than the specification, data from a previously opened row can be copied into another row inside the DRAM array. If we make the timing even shorter, multiple rows can be activated almost simultaneously. The charges from the cells are shared on the bit lines, and the sense amplifiers resolve the results. The value that appears is the majority value of the activated rows. In other words, a DRAM can perform a bitwise majority operation across many columns at once. So let us look at the carry output of a full adder. A full adder has 3 input bits, A, B, and C. For the carry output, the result is 1 when at least 2 of the 3 inputs are 1. This is exactly a majority function. The first step is data allocation. We place the 3 inputs vertically so that each column contains the 3 bits needed for 1 carry computation. The next step is row copy. Many PUD operations are destructive, so before applying majority, we copy the inputs to temporal rows. Now we apply the majority operation to the copied rows. Since the carry function is the majority of A, B, and C, the output row becomes the carry of the full adder output. The key characteristics of PUD is column level parallelism and independence. A PUD operation applies the same function to all active columns, but each column stores and processes its own operands independently. This is why prior PUD designs usually follow a static execution model. They pre-arranges all operands in the DRAM locations in advance, and then replay a fixed sequence of PUD operations. Because the sequence does not depend on the input values, it can be optimized offline. This static model is elegant and really makes use of PUD's high throughput, but requires an assumption. All operands are already in their target DRAM locations before PUD execution. And now I will move to the motivation. The question is, what happens when this assumption does not hold? In real applications, especially large language model inference, not all operands are already in the required DRAM layout. LLM inference includes processor-side operations such as softmax, normalization, and other reductions. These operations are impractical to map onto PUD because they require high precision computation and they offer limited parallelism and involve global data access. So these operations should be executed on processor. And these operations generate new activation vectors. And before every matrix vector multiplication, the processor must write the new input vector into DRAM. In this figure, the matrix can be stored in DRAM in advance because the matrix data is static. But the processor generates the new activation vector dynamically at runtime. So the processor has to write the input to the DRAM at runtime. This can become as expensive as the matrix traffic. This is input writing amplification. As a result, prior PUD methods can degrade end-to-end performance rather than improve it. To address this problem, we propose MVDRAM. MVDRAM accelerates matrix vector multiplication in end-to-end LLM inference. The main idea is to execute full adders inside DRAM without explicitly writing the input vector into DRAM. Instead of treating the input vector as data, that should be written to DRAM. MV DRAM uses it as information for generating DRAM commands. The input values directly controls which PUD operations are issued. At a high level, the processor does three things. First, it checks the current vector values that is stored in the processor. According to the value, the processor issues the further commands to DRAM without writing this vector to DRAM. Second, the processor updates the vector values according to the further commands it issues. And after DRAM computes the results, the processor keeps track of how the vector values should be updated and read the final result. This cooperation between the processor and the DRAM lets us avoid writing the input vector into every column. Why does this work? If we apply the same full-adder transformation to selected rows, each column produces the correct carry and sum for its own operands. At the same time, the processor updates the corresponding vector values. So the DRAM side transformation and the processor side update preserves the invariant equation that is corresponding to the matrix vector multiplication. I will explain the more like the detailed function of MV DRAM. This slide shows the idea from the DRAM layout perspective. A full-adder command takes 3 rows and it generates carry and sum rows by using row copy and majority operation appropriately and based on the vector values. By repeating this process, computation proceeds inside the DRAM while the processor tracks the vector values. So here is a more detailed example. Suppose the processor holds the 5 elements, 1, 1, 1, 2, and 2. Because the vector has 3 ones, so 3 of the values are 1, so it issues a full-adder command on the 3 matching rows. Adding 3 ones gives a sum and a carry, so the vector is updated to 1, 2, and 2. And now 3 of the values are 2, so a full-adder applies again. And the vector becomes 4, 2, and 1. Throughout this process, DRAM computes the carry and sum rows in parallel across all the columns, while the processor only updates these compact vector values on the processor side. The general rule is shown here. If the vector values match, a full-adder can be applied after constant scaling. So the processor only needs to find triples of matching values and issue the corresponding full-adder operations to DRAM. This makes more computation possible. This slide, so let us consider if the processor has the vector of 1, 1, 5, 4, and 4, and because 5 is not multiples of 2, we have the decouples of this value into 1 and 4. By doing this decouple, we can have 3 ones in the vector, so we can apply the full-adders. And by applying the full-adders, the input vector will be updated into 2, 1, 4, 4, and 4. Since the vector has 3 elements of 4, we can apply the full-adders again. And by applying the full-adders, we can finally get the vectors of 2, 1, 8, and 4. And because we have no longer have 3 the same elements, we will stop the procedure and get the final result. So sometimes the vector values can be split, and to make flooders applicable, but this will make the management and scheduling more difficult. This is the main challenge to realize the MVDRAM idea. MVDRAM must schedule and issue PUD operations on the fly. At runtime, it must answer which vector values are ready, and which choices reduce the total number of flood operations. So these decisions must be made just in time and in real time. Therefore, the efficient processor architecture is critical. This point is the unique challenge of MVDRAM approach. This slide shows why command generation latency matters. If the decision time is hidden behind the DRAM execution, it does not increase the total latency. But if command generation takes longer than the DRAM execution window, the extra time directly increases end-to-end latency. So the command generator must be simple, fast, and hardware friendly. And next, I will explain the architecture approach for MVDRAM command generation. To make the management and scheduling simple, we introduce a bucket representation for MVDRAM. First, vector values are decomposed by bit position. In this slide, we have 3 1s and 2 2s, and we prepared 3 types of buckets, which corresponding to a scale 1, scale 2, and scale 4. And scale 1 buckets have 3 items, and the scale 2 bucket have 2 items. This is according to the input vector. If at least one bucket has 3 items, we will let them out and apply the full adders. And the full adder will generate the carry and sum. So we will let them back to the corresponding 2 buckets accordingly. And then in this example, the scale 1 bucket has 1 item, and the scale 2 bucket has 3 items. And because the scale 2 bucket has 3 elements, we can let them out again and apply the full adders, and we will get the carry and the sum again, and bring them back to the corresponding 2 buckets, and then we will get the final result. So we can extend this approach to a more complex example. If the input vector is 1, 1, 5, 4, and 4, and because 5 can be decomposed into 1 and 4, the state of the bucket representation should be like this. And the scale 1 bucket has 3 items. We can let them out and apply the full adders and let them back to the buckets, and do this again, and until we get the final result. So this representation makes the management, the state of the vector simple, so that we can implement like the processor side circuit efficiently, and the processor can make the appropriate DRAM command on the fly and issue the DRAM command to the DRAM efficiently. Now I will describe the overall implementation of MVDRAM. We implement a system on a Xilinx FPGA that is connected to SK Hynix DDR4 DRAM. The FPGA includes a command issuer and output vector processing logic, and a custom memory controller that supports processing using DRAM. The command issuer generates PUD level operations. The custom memory controller translates them into the timed DRAM commands, and the output vector logic handles output vector and updates the final results. A straightforward implementation would use only one DRAM bank at a time, but modern DRAM has many banks, so we should consider the bank level parallelism. Because PUD operations have a relatively long latency, bank level parallelism is important. To address this, we instantiate a multiple command issuer for multiple banks. Each bank can work on its own commands and merge into like the circuit combines these parallel commands and the outputs the streams before the shared memory controller. This design improves the bank utilization while respecting the shared DRAM interface. In the final implementation, full other commands from 32 banks in total are managed and sent to the custom memory controller. Next, I will show the evaluation results. Our experimental setup uses a DDR4 system with 2 channels and 4 DIMMs modules in total. For workloads, we use lambda.cpp and evaluate several LLM models. And we compare the 5 methods. The baseline is the central processor-based method, and we compare the prior PUD methods and our approach on the 2 platforms. One is the modified DRAM, including Ambit and SimDRAM platforms. And we also compared these methods on unmodified commodity DRAM. The result is that the modified DRAM version of our method achieves 1.48 times faster than the processor-based average, based on baseline on average. Even on the unmodified DRAM, we achieve 1.13 times faster. The same is also in the energy efficiency. Our approach achieves 2.74 times more energy efficient compared to the processor-based execution. So we also have like the result sensitivity result to bit width. When the activation bit width increase, the performance will decrease. This is expected because NVDRAM latency scales with the number of full adders, and the number of full adders is determined by the how many ones the activation vector has. Next, we vary the number of generated tokens also, and we can see that as the number of generated tokens increase, the performance gain will increase. In contrast, the number of prompt token increase, the performance gain will decrease. To summarize, we propose MV-DRAM, and the central idea is to avoid writing processor-generated input vectors into every DRAM column. And the evaluation showed that we can actually achieve the performance gain beyond the memory bandwidth bottleneck. So we hope that MV-DRAM provides a path to accelerate AI inference on edge devices scenarios. Yeah, thank you for listening. I'll be happy to take questions.
Thanks a lot. So, do you have any questions? To hear.
That's
not a, that's
yeah.
my Zoom.
Okay, so a simple question, but is the fully adder support the negative numbers?
Yeah. We applied. Yeah. So we also like by doing the inversion, we can extend this method to the negative values, and we support the signed arithmetic also.
Oh, thank you very much.
Thank you.
Other questions? So maybe I'll ask. A great talk, Tatsuya. Thanks a lot.
Thank you.
So first question, I have multiple questions, but the first one, in order to perform NOT, are you writing the negated values of the inputs to the subarray?
Yeah, it is actually. So the commercial DRAM does not support the NOT operation within the same subarray, we store the negative values, invalid values in advance, and do the like the emulate not operation using the primitives. Yes.
Another question, you show results for LLM inference, right?
Yeah. Yes.
So are you performing all the LLM, let's say, kernels there, such as softmax, attentions, etc., or are you just offloading the matrix vector multiplications?
Yeah, thank you. Thank you for your question. We only map the matrix vector multiplication to DRAM and do other computational kernels, including softmax and normalization on the processor side. And actually, so we don't map all of the matrix vector multiplication to DRAM. There are also like the small dimensional kernels. In that case, we map the matrix vector multiplication also to the processor.
Okay, so one last question maybe, what about the reliability?
Yeah, so I would like to say that this is like the work in progress, but we are now carefully doing the evaluation. But I can say that we can expect the computational accuracy is under 1% or 0.1% of normalized mean square errors. I think which is tolerable and which is smaller than the quantization errors. And I hope we can do some like the reasonable computation for AI workloads.
Okay, thanks. Any other? Yes, one more.
Thank you for your question.
So you the coefficients with which you are multiplying, it looked like you're multiplying with integers because you need to decompose these integers into this kind of powers of 2, like 1, 2, 4, and so on. So this means if you get a big coefficient, you might have to decompose it into many pieces. Like if I give you coefficient 255, which is kind of a lot of ones, this would decompose into a sum of many powers of 2.
Thank you for your question. That's very good question. That depends on how many ones the number we require. So like, I mean, if the coefficient is 32, it will have a single one, like in the 32 scale. So like it will require only a single floaters, but the coefficient is in the case of coefficient is 7. The 7 is a small number, but it has 3 ones because it will be represented as a 1 and 1 1 1. So it will involve 3 times of floaters. It will take like the more like the latency than 32 of coefficients. So like, yeah, am I answering your question?
Yes, but then if you also, I mean, the other question was about negative numbers. So if you say you're also supporting negative numbers, so could you decompose the 7 rather than 1 plus 2 plus 4? Could you decompose it into 8 minus 1?
Yeah, yeah, exactly. And that will reduce the total latency. So that can be like the optimization space, and it can help the performance of this approach more. And yeah, I really agree with your like idea.
Right. Thank you.
Thank you very much.
Do we have any other questions to Tatsuya? Okay. Thanks a lot, Tatsuya, for the talk.
Thank you.
It was great.
Thank you. Thank you, Ismail. Then thank you, audience. Thank you very much.
Bye. So I guess this concludes this part. See you after the lunch. Thanks a lot for joining. just gonna send you a PhD student. No, wait. Hello. Yes, this one. Yes, they do. Yeah. Hello, everyone. Welcome back to the third session of this workshop. So, Ataberk, we're going to discuss about FPGA-based frameworks to enable fundamental better computing systems. He's a PhD student in software research group, and it's been some years. And he's going to introduce himself anyway, so please.
Thank you, Ismail. I'll be talking about FPGA-based frameworks to enable fundamental better computing systems as part of the MCCSys tutorial today. And I'm happy to present my some of the PhD work I did to you. So this is me. I'm a PhD student at Software Research Group, and it's my 5th year now. I'm broadly interested in computer architecture, but I've been working on memory systems in many aspects of memory systems. Dynamic random access memory, DRAM, and processing in memory, most of my time in my PhD. As you are probably already well aware, computing is bottlenecked by data, and there are many important workloads that are data intensive, and the amount of data that they generate and the amount of data that we must process keeps increasing over time. And data-centric architectures can solve this data movement bottleneck, and there are many dimensions to a data-centric architecture. But today I'll be talking about processing in memory, or processing using DRAM in particular. I'll start with PyDRAM. This is an FPGA-based framework for end-to-end evaluation of processing in DRAM techniques. My slides are self-contained, so maybe you've seen these background images earlier in the workshop, but please bear with me as I introduce them to you once more. A processor's memory controller in a typical DRAM-based computing system communicates with a DRAM module over what we call a DRAM interface, or DDR interface. A single DRAM chip will have many DRAM banks that share the same common chip interface, I/O interface. Inside the bank, you have many DRAM subarrays, and each subarray has word line drivers and sensor amplifiers. Word line drivers will split DRAM mats from each other inside that subarray. We have many DRAM mats. And finally, inside the DRAM mat, we have DRAM cells laid out into a two-dimensional array of rows and columns. And a row of DRAM cells obviously is referred to as a DRAM row. And this is a sketch of a DRAM cell that stores charge in the capacitor, stores data as charge in the capacitor. We will look at this DRAM array at the scope of a single subarray, because memory controllers typically access cells in the granularity of a cache line or a cache block. We collect multiple DRAM cells to form a cache line in this diagram. And on the bottom, we show a sequence of DRAM commands that we execute to access these DRAM cells. So to access one of the DRAM cells in that first row, we have to activate that row. So we send an activate command. This will copy the data to the sense amplifiers, or the row buffer at the bottom of the array. And once the data is there, we can send read commands to read data out from the DRAM module in cache line granularity. Once we're done accessing this row, if we want to access another DRAM row, we have to pre-charge the bank, and then we can activate that other row and do the same issue the same sequence of DRAM commands to retrieve data from this newly opened row. Now there are what we call timing parameters that define the amount of time you have to wait between issuing pairs of DRAM commands. And one important timing parameter is the activation latency. It determines the amount of time you need to wait between the activate command and the subsequent pre-charge command. And there's pre-charge latency, which is the timing, the delay that we must wait for the opposite sequence of DRAM commands, so pre-charge to activate. And there's also what we call the access latency, which is the amount of time we have to wait between activate and read commands. We must obey these timing parameters as defined in the manufacturer release data sheets if we want DRAM to operate the way we think it will operate. Now, interesting things can happen when we don't, and I will talk, probably Ismail already talked about those, but I'll reiterate later. This is another piece of background that you're well aware of. Processing in memory techniques use the operation principles of memory to perform bulk data movement and computation. And we know that commodity DRAM chips can already perform bulk data copy operations and row granularity to random number generation, physical unclonable functions, and majority operation, and even more. But for the context of my talk, I'll focus on these two, row copy and true random number generation. You've probably seen the key idea of row clone. I'll just reiterate very quickly. So we have, this is a different view of that subarray we were looking at earlier. So we have many DRAM cells and 4 DRAM rows in this picture. We have the source row that we want to copy to the destination row. We can do this in 2 steps. The first step is to copy the source row to the sense amplifiers. And the second step is to simply copy this data back from the sense amplifiers to the destination. We can already perform the first step in real DRAM chips. That's the activate command. But the second one is, as far as official documentation considered, is not supported by real DRAM chips. But we can actually perform it in real DRAM chips by using carefully crafted DRAM command sequences that greatly violate the activate to precharge and precharge to activate timing parameters in an act-pre-act command sequence. If you use the standard DRAM timings, a sequence of act-pre-act commands will sequentially open row S, then precharge the bank, and then open row D for access. If you violate the DRAM timing parameters and issue them in quick succession, issue these commands in quick succession, you will activate row S. Then the precharge command will be ignored sort of by the DRAM chip. So you will be able to write back the data from the sense amplifiers to the destination. So that's how we copy data in real DRAM chips. The other thing I'd like to mention is true random number generation. And the key idea here, at least the true random number generator that we evaluated in this work, the range, is to use or exploit data DRAM access latency failures for true random number generation. I'm going to describe that pictorially here. We're again looking at a different depiction of a subarray. So we have many different depictions of DRAM subarrays in this talk. But here you see many cells that have different sizes and colors. A dark color, smaller cell, indicates that this cell yields a very high chance of failure or a bit failure when we access it with a reduced TRCD time command. That's the activation latency. The latency between the activate command and the read command. The bigger cells, the green cells, yield a very low chance of failure when we access it with reduced latency. The idea is there are some cells that fail with a 50% probability. And if we can find these cells and repeatedly access these cells with reduced latency, then we can generate random numbers. And the mechanism by which we do this is to violate the TRCD timing parameter. And that is already supported by DRAM chips per se. You just have to have a memory controller that supports these operations. Now we've seen some cool processing in memory, processing in DRAM primitives, but there is, in this work, we identified this gap between the application level and the, this is the classic view of the software or the software hardware stack, system stack. We identify a gap between the application and devices electron level, right? I'll describe this in detail, but if you want to support a workload, an application that wants to do bulk data initialization, you can think of this as the call lock function in your C++ library, for example, that allocates data and initializes it with a certain data pattern. It can be zeros, it can be ones, whatever. That's sort of an application. And we also have at the devices level, electrons level, we have this primitive, row clone primitive in the DRAM chips. So how do we bridge this gap per se? We will need at least a memory controller that supports custom timing parameters to violate DRAM timings to issue these act-pre-act command sequences. You need some control logic in your microarchitecture level to control these PIM operations, really control the way that your memory controller operates. You need to expose these commands or the control logic to software so that the software developer can make use of these primitives. And you will also need some supervisor software that has basic support for processing in memory primitives. And this, you can think of it as specialized data allocation for processing in memory operations, like bulk data copy operations. And I'll get to that later. So PyDRAM bridges this gap with customizable hardware and software components to allow users to rapidly implement new processing in memory techniques, processing in DRAM techniques, solve system integration challenges of these techniques, and also analyze their end-to-end implementations. It has 4 key components that I will not go into detail in the interest of time, but I will describe this picture. So we have the 4 key components, some of them hardware, some of them software, and we attach these components to a real computing system based on the RISC-V rocket chip SoC. And this SoC system is also attached to a DDR3 module that can perform real in-DRAM processing operations. This is what it looks like if you look at the whole thing from outside. We have an FPGA-based prototype on a ZC706 FPGA board. Here under the cage here, if you can see my pointer, that's where the DRAM module is that performs the row clone operations in DRAM to random number generation. And the RISC-V system is inside the FPGA. It's implemented in the FPGA. It's a relatively tiny system. It's a features an in-order rocket CPU core with a tiny L1 instruction and data caches and some small TLB. And this is the module identifier for the PIM-enabled micro module. So this is just to reiterate the key idea of row clone. To implement row clone, we just need to add a few lines of Verilog code in our memory controller design and extended state machines with a few lines that perform the act pre-act command sequence with violated timing parameters. But we identify 2 system integration challenges of row clone. So when you support row clone operations in your memory controller, you'll also have to deal with these 2 issues. The first one is memory allocation, and I'll talk about that in detail. And the second one is memory coherency. This second problem stems from the fact that we compute on data that's in DRAM, but we have multiple copies of this data in our processor in the caches. So to mitigate the second issue, per se, we implement CL-flush instruction, the CL-flush instruction, which flushes the cache line that you basically point this primitive to back to DRAM. Now I'm talking about this because when we started this project, the RISC-V rocket core and the whole SoC didn't have support for flush instructions. We implemented this. You can find it in our, I'll point you later to our open source repository. But the basic idea is we implement the CL-flush instruction, and then we use this before we copy data inside the DRAM chip to make sure all the data is up to date in the DRAM chip. I'll talk a bit more about the memory allocation problem now. So these are 4 different allocations of 2 operands, the source and target operands. 3 of these fail, and 1 of them succeed when we try to do row clone with it. If you look at the first one, the problem here is we will be overwriting the target operands row with data that we basically do not know about. And the second one fails because we're trying to copy to a different offset in the second DRAM row. But we already know that row clone operations will move bits from one bit line to another bit to the same one cell in a bit line to another cell in the same bit line, but in a different row. So if you're trying to copy data across bit lines, that's not going to work. And that's to say, basically, your source and target operands must be offset to the beginning of the physical DRAM row. The third allocation fails because you are trying to copy data from one bank to another bank, or from one subarray to another subarray. That's not going to work with row clone fast parallel mode, at least, which copies data inside a single subarray. And the fourth allocation here satisfies all 3 requirements that the prior 3 did not, basically. you have to allocate your operands like this. This is the main memory allocation challenge when it comes to processing using DRAM, at least when you consider row clone operations. In the paper, we described in detail an data allocation routine that we implemented as part of our basic supervisor software. That's the RISC-V proxy kernel. This allows the user to basically attain or like get allocations that represent the fourth version of things here. We informed this piece of software with which physical DRAM role, which physical address corresponds to which physical DRAM role, and which of those rows are in the same subarray. So to figure this out, we have to do some characterization. Basically, we know the physical addresses in our system because it's something we developed from top to bottom. And what we do is, can I copy from this physical row to this other physical row? And you repeat that for all pairs of DRAM rows. And then you can come up with a list of rows that belong in the same subarray. If the copy operations has succeeded, you can consider them to be in the same subarray. Once you have this information, this routine basically will check for empty DRAM rows that are not allocated yet and give you the right virtual addresses for you to use. But again, the details of this is in the paper. We also evaluated a bunch of micro benchmarks and copy/initialization heavy workloads using this FPGA-based infrastructure. And we also were able to run a SPEC 2006 workload that was libquantum. That's initialization. That was the initialization heaviest workload we could identify at that time. And we replaced its calloc functions, which allocates and initializes an array with zeros. We replaced calloc functions with row clone initialization operations. One thing I will mention here is that our DRAM module has 8 kilobyte large rows, so a single copy operation has to be at least 8 kilobytes large for us to do it inside the DRAM chip. For any smaller sized copies, we have to fall back to the existing way of copying things, which is to use load and store instructions. So here we show the throughput improvement you get for 2 micro benchmarks, initialization and copy, for different array sizes over the x-axis. What this shows is you can improve copy and initialization throughput by 120 almost and 90 times. And the numbers are relatively high, primarily because the CPU core itself is a bit weak. If you think about it, this CPU core cannot exploit the full bandwidth that the DRAM chip has available. So here we have a 50 megahertz in-order RISC-V core versus an 800 megahertz DDR3 module. But I'll come back to this as part of my next talk on EasyDRAM. So these results, I'd like you to keep them in mind, but we will come back to this. Now, another interesting result we have is if you consider the overhead of CL flash, cache line flash operations, your benefits reduce significantly. On the x-axis, we have the proportion of dirty cache blocks in the data that we must operate on with row clone operations. Here we have 8 megabyte large arrays that we're either copying or initializing. If 100% of the data is dirty, that means our caches hold, first, our caches always hold all of this 8 megabyte large data. In the 0% dirty case, none of that is dirty, so none of it has to be written back, but we have to execute CL flush instructions to invalidate the destination object. In 100% dirty case, we still execute CL flush instructions, but we must also write back the data because we must update the DRAM chip with the real data. And then you can see the overhead CL flush introduces. It brings down the benefits from around 120x for copy operations to around 1.9x in the worst case, as far as our micro benchmark study goes. We also have data from other workloads. This slide is a bit loaded, but the key takeaway here is that processing using DRAM primitives we enabled in this work get you performance benefits, not only for micro benchmarks, but also for real workloads. Now, that was it for row clone. I'll pause to take questions if you have any. Yes. Just a second. I think you might need the microphone. Or... Okay.
I'm curious, like, what's the reliability? I'm thinking like if you're logging like critical like kernel data, then that's
Yeah, that's a very good question. In this work, we didn't evaluate like the reliability of row clone operations. What I can tell you is the characterization procedure I described, where we copy from every possible row to every other possible row. What we did there is, if this operation succeeds for 1,000 times, we consider that reliable. But I think we need to do more in-depth characterization of these operations, maybe with even more chips than we've tested so far. And for, I guess, multi-row, as far as multi-row copy is considered, you can look at Ismail's other works where he, and you can comment on this, looks at this in more detail than I did in this work. And I'll add that it's quite reliable. Row clone is basically 100%, I think. You don't want to add anything to that? Yeah, I agree with you on the destination operand for sure, 100% agree. The source operand still needs to be flushed.
If it refers to the source operand, then again, it doesn't make so much sense to do the copy in DRAM because if it's source operand, so the source operand is already in cache. So
yeah.
Now you can do very quick operations with this because it's cache, so you don't need to do it.
Yeah, you're right. And if you look at the original Rowhammer, I mixed the workshops at this. If you look at the row clone paper, that's it's described this way. So there are different levels where you can do the copy operation. In the caches, if you find the data there, in the memory controller, by not bringing the data all the way to the cache, and it's more like DMA, sort of copy operations. And also within, like across banks inside the DRAM chip, what I described is only the within subarray copy operations that the original row clone paper describes. An ideal implementation, a better implementation would implement it like the way you suggested, but in this work, we only have support for in-DRAM copy operations. So we, for demonstration purposes, we CL flush the source operands because that's where we can only perform the bulk data copy operations. It's not integrated into the whole across the system. And we don't have invalidate because we only have CL flush. I would use invalidate if I That took me 4 months. Yes. CL flush took me 4 months. I didn't want to spend another month or so. Yeah. There was a terrible bug that I had to fix.
It would be more difficult because when for multiple scenarios with private analog caches that we're sharing all the 30 bits in the same location. Invalidating and I don't know, but it would be pretty difficult and complex operation for
Yeah. So in this, I guess I can make a comment on this. Is another question, right? So just to elaborate on it, in our case, we were lucky because if you look at Rocket Chip, and I might be, again, this happened 4 years ago, so I might not be remembering fully, but they implement something called tiling as a sort of NOC between the requesters and the all the components in the memory hierarchy. And tiling natively supported CL flash, let's say. So the interface already had some support for it. It's just that the ISA didn't expose any instructions to the user. I think they added CL flash instructions much later into the ISA. Their philosophy was no one should need CL flash instructions. So the philosophy, I don't think they stood the test of time. Now there's an extension for CL flash instructions in the RISC-V ISA. But yeah, I mean, even with the interface supporting it, modifying the cache controller logic introduced a bug, and then it took me 2 months to fix it. Maybe cloud today can fix it much easier. I don't know.
Because the operation that you need, the CPU, basically it already supports it, just doesn't expose it. Because what you need is exactly what the CPU does when the cache reaches full capacity and now it needs to evict one of the caches. This evict does exactly what you call it, flushes the cache line back to memory. So this means actually the CPU knows exactly already how to do all of this.
Yeah.
It's the same as eviction, just now you're not evicting because of a capacity issue. Now you're evicting on purpose to get the data into DRAM. And the same for the evaluate. The evaluate is like an eviction where you skip the last step of actually writing the DRAM. The other coherence changes.
Yeah, no, I agree with you. It's just that I had the same mindset going into this, but there were bugs, and we can talk more in detail. But yeah, there are some nuances. Like if your eviction policy is random, then you have to do something to identify which set you want to evict from. You cannot piggyback completely on the existing mechanisms. But yeah, I mean, this is good discussion, but completely outside the topic of what I wanted to discuss. How much time do I have? 35. We start at 35, 45 minutes.
It's fun, we are
20 minutes or so. Okay. So I'll continue with DRange. This is the random number generation use case for PyDRAM, and we're trying to identify cells that fail with 50% chance when we access them with reduced TRCD. So we do that. We test our DRAM chips with reduced TRCD and find a cache block that fails, that has many failing cells. And then you repeatedly access this cell with reduced timing parameters. For the case of, or for the sake of the proof of concept, we have implemented a 1 kilobyte large random number buffer in the PIM operations controller, and expose random numbers to the user with a system call. And here you see some number of lines that I think these numbers are becoming less and less relevant with AI assistants these days. But back then, I think the common substrate PyDRAM built on, you could add this many lines of Verilog and C++ code to implement DRange on top of the row clone use case. And one thing I didn't describe is we modified the memory controller with a periodic number generation routine. Basically, it injected requests into the queues every configurable with configurable delays. It injected requests into the queues that generated the random numbers, and then put those numbers in the buffer. So the user takes numbers from the buffer, and the memory controller periodically generates random numbers by accessing DRAM. And here you see some performance results. You can configure the period of that controller logic I was describing on the x-axis. That's what we show. And the throughput you see on the y-axis. We generate two random numbers at 8.3 megabits per second throughput. And this can go higher if you increase the number of banks you are periodically accessing to generate random numbers. So here we're using only one DRAM bank. And PyDRAM is completely open sourced at this link. We also have an extended version of our journal publication on arXiv. and also describe more details of PyDRAM in this YouTube talk. This is from 3 or 4 years ago when we first published PyDRAM. And that's it for PyDRAM. I'll switch gears into a different frame in infrastructure, unless you have any questions. The next thing is EasyDRAM. It's also related, pretty much related to PyDRAM. It's an FPGA-based infrastructure for fast and accurate end-to-end evaluation of emerging DRAM techniques. It's a bit more general than PyDRAM. What are DRAM techniques? We classify them as techniques that violate standard DRAM timing parameters to improve latency and computing capabilities of DRAM. We looked at some of those that improve the computing capabilities, but you can think of other mechanisms like you can reduce the access latency to a point where you don't observe failures, just to shut off the guard band that the manufacturers add basically and reduce your access latency to DRAM. And we evaluate one technique in this work. There's the system support gap for these techniques that I described earlier. And I'd like to talk about FPGA-based evaluation platforms a bit more to motivate why we go with them instead of simulation or other things you can think of. We think they're a good basis for evaluating DRAM techniques because first you get an interface to real DRAM chips. So whatever reliability characteristics those DRAM chips have, you're exposed to it completely. You cannot cut corners or assume some reliability characteristics. It gives you a relatively short end-to-end execution time for workloads you manage to run on this infrastructure. And it doesn't, the problem is it requires some hardware design expertise because you need to develop your own Verilog code. And we have seen this in the previous work. There's a proportionality issue, let's say, as far as the CPU versus DRAM clock frequencies are involved. Your CPU will operate at a relatively small clock frequency, whereas your DRAM will be operating at a higher clock frequency. And this is a discrepancy you don't see in other systems today. It's the opposite usually. I'll talk about these two problems in more detail because EasyDRAM fixes those issues along with providing this infrastructure to validate DRAM techniques. So yeah, to modify DRAM controllers, implement new techniques, you need to modify your memory controller. That requires deep hardware design expertise, and it poses a barrier to entry for many researchers and many interested people. The second weakness is, as I've described earlier, you have the CPU typically operating at 4 to 6 gigahertz. Your DRAM is 1 to 4 gigahertz, depending on what type of module you have. But if you implement the CPU design in the FPGA, you will get a much lower clock frequency. You might get something higher, but the order of magnitude change is still there. And then your DRAM is still operating the same speed. That causes a discrepancy, and it limits the evaluation accuracy and skews your results towards the DRAM technique side. That's why PyDRAM shows 120x speed up for row clone copy operations. So the problem is FPGA-based platforms are difficult to modify, but they're good to evaluate DRAM techniques on. And they yield inaccurate system performance results when you use them for DRAM technique evaluation. And our goal is to basically fix these two problems. There are two key ideas of PyDRAM. The first one is we implement a programmable memory controller, so you don't need the hardware design expertise to evaluate a new DRAM technique. So you write a C++ program, and that is compiled to run on the memory controller inside the FPGA. And the second technique is what we call time scaling. At the high level, we split the hardware components to different clock emulation domains, and we control the clock of each domain in a way that makes the evaluation platform mimic a real system. And I'll not talk about that second key idea in much detail, but I'll show you some results. This is an overview of EasyDRAM. There are two components. And the first one is the memory controller, programmable memory controller. And this is an example code that does something very simple. This is an example memory controller. So you check if the request queue is empty. You're waiting for a memory request to arrive. Then you process this request to find the DRAM address. The DRAM hierarchy has many components like banks, rows, columns, etc. You're trying to identify that address, and then you issue this request to DRAM. Once you get the response from the controller, you will issue this back to the processor system. So that provides an easy way to perform low-level memory controller operations to the user. And the detailed ISA is available, not ISA, but the function. We provide a library that's very useful for common operations used across many different memory controller implementations that we could identify. And there are more details in the paper. Now, using this programmable memory controller will introduce some challenges, as you might imagine. The C++ memory controller program running in the controller, it's very slow. It executes many instructions to simulate one memory controller clock cycle. So you cannot issue DRAM commands at nanosecond granularity, which we need to do those fancy things like row clone operations or latency violation. And in addition, the processor also experiences lengthier stalls waiting for memory than in a real system. And yeah, just this whole thing limits evaluation accuracy. The solution is described in detail in the paper. It's, I think, too much to go into for this talk. But with this solution, the time scaling, it's called, we validated it with a two-level approach. First, we have an RTL simulation of easy DRAM. We clock this simulation at where the processor system is clocked at 1 gigahertz, and there is no time scaling implemented in this version. And the second system configuration is easy DRAM running on the FPGA with time scaling enabled. So it's running at 100 megahertz, where the real clock speed is 100 megahertz, but the time scaling technique is configured to make it look like it's operating at 1 gigahertz. And these results we get with these two systems across 29 micro benchmarks. In execution time, they're within 0.1% of each other. The second thing is we are looking at what we're seeing here is the latency diagram for 3 different systems. The pink one that looks very bad is easy DRAM without any time scaling. The blue one is for an ARM real system, and easy DRAM with time scaling is calibrated against this one, where you can see that the latency profile more like better represents that of the real system. These are the two things we did to validate time scale. There is some gap still that we can probably, as part of our future work, try to shrink. But this system is already giving you a better evaluation platform than what we had before, which is PyDRAM, and I'll show you some results. This is what easy DRAM looks like. It's on a different FPGA board. It comes out of the box with support for boom cores. Those are the out-of-order cores, slightly more beefy than Rocket cores. And we have a real DDR4 DRAM where we can do row clone operations on. We evaluated easy DRAM with 2 case studies. The first one is in DRAM row copy. The second one is DRAM access latency reduction. So the takeaways from the row clone study is that prior work, which do not faithfully modern processor, report high benefits in favor of DRAM techniques, that's PyDRAM. But thankfully, row clone still improves performance when compared to a modern CPU baseline. That's what we showed as part of easy DRAM's evaluation. And you can see the numbers, some of the numbers here. So easy DRAM without time scaling is the purple bar. That's what the benefits you would get with PyDRAM on the y-axis. Easy DRAM with time scaling is the more realistic system with more humble speedups reported. That's 15x compared to PyDRAM's 100 plus. So that's it for row clone. I'll talk about the access latency reduction use case as well. So here we're looking at what's called solar DRAM, which aims to identify cache lines that can that can withstand the access latency reduction. If you look at your DRAM chips, you will see that some bit lines are weaker in the sense that they fail when you reduce the TRCD or access latency by a little bit. And there are stronger bit lines that, that do not fail if you reduce the access latency. And we need to identify these strong bit lines and then access them with reduced TRCD when a request addresses that strong bit line. And there are some implementation details that I won't go into in the paper, but I'll highlight some of the results. So this is a heat map. You don't need to look at this, understand that, but the qualitative takeaway is that in this DRAM module that we validated, we find that all cache lines reliably operate at an access latency value that's smaller than the manufacturer advertised value of 13.5 nanoseconds. So if you access these cache lines with a 12 nanosecond latency instead of the nominal 13.5, none of them will fail. Some of these cells are, most of these cells are stronger than others. With a TRCD of 9 nanoseconds, 85%-ish of the cells do not have any failures. And some of the cells are weaker, so that's the remaining 15%. Those are going to be failing at 10.5 nanoseconds. And as I mentioned earlier, we identify these cells and then we determine a threshold or TRCD value that we can access, reliable TRCD value that we can access these cells with. If you apply that profile, when you run a workload, these are the workloads we run on the x-axis, these are polybench workloads, you get an end-to-end system performance improvement of 3% on average. And we expect the benefits here to increase with memory intensity. These workloads turned out not to be too memory intensive. So that's easy DRAM. In conclusion, it's a very easy to use programmable memory controller, and it allows you to accurately evaluate DRAM techniques. We hope that it enables more innovative ideas in memory system design to be evaluated more rapidly. The extended version of this paper is also on arXiv, and EasyDRAM is open source. I'll start closing on this note. So there are many potential barriers to adoption of PIM, and these are my PhD supervisor slides. So there's applications and software we need to develop for processing in memory. We need to make it easier to program. There are many challenges in the system, and at various levels of the system hierarchy. There's a need for security, support, and runtime and compilation systems for these different techniques that you see here. I think we can solve these challenges using these two platforms, or those are two very good infrastructures that people should use if they're interested in solving these challenges. I'll talk a little bit more about DRAM Bender. This is an extensible and versatile FPGA-based infrastructure to easily test state-of-the-art DRAM chips. And it's the first publicly available FPGA-based infrastructure that you can use to test DDR4 and HBM2 systems. And this is also easy to program. And the importance of this, I think, is it enables a lot of discovery into the functionalities of real DRAM chips, like you've seen these earlier, and I assume you have seen these bitwise and NAND operations in DRAM chips. And that's functionally complete DRAM. And also we have many other primitives discovered as part of this other work called simultaneous row activation, main row activation. I think DRAM Bender enabled these studies. And DRAM Bender is also completely open source, and it comes out of the box with support for 6 different FPGA-based prototypes. And we have new features coming soon. We have a lab set up in our research group where we can simultaneously test 100, close to 100 DRAM modules. And we've published a paper about this large-scale memory characterization laboratory as part of ICS workshop proceedings, and it's available at that link below. And you can find more details in the original paper we published about DRAM Bender. DRAM Bender is widely used for many, let's say, types of research, and here are some works that have used it in the recent past, and there are other use cases that I highlight here. And I hope that it will continue to enable research. And one thing I want to mention is, this is the case, this is true for all infrastructures I've presented. I think more research drives new DRAM bender features or high DRAM or easy DRAM features. So if you're interested in working on these, I'll be happy to support you. And as you do your work, we will also keep improving these platforms to support newer research ideas. That's all for my talk. Thank you very much for your attention. We can take more questions if you have any.
Any questions? Case, here is your vendor and even this DR5 it's a total of the visual.
Okay, by just putting me on the spot, he's working with us. So he's a very intense user of the DRAM bender characterization infrastructure. DDR5 it's not a fundamental problem. It's more of a lack of the right combination of tools. There are FPGAs available that you could implement support for DDR5-4, but you would have to write your own file layer that actually operates the physical signals almost in the analog domain, right? The FPGAs come with primitives available for you to use that interface, but there is no open source platform that you can readily use to configure an FPGA board with. There's an open source DDR5 but there's no DDR5 FPGA board you can buy and use that PHY to communicate with the module. That's the main problem.
Any other questions? Thank you very much.
Thank you.
Yes. So today we will discuss the two key remaining challenges of processing using DRAM. The first is mapping and algorithm of processing using DRAM. So while massively parallel or arithmetic is theoretically feasible in processing using DRAM, the large number of required DRAM operations makes efficient algorithm mapping very critical. And the second challenge is reliability. So due to its anaerobic nature of DRAM cells, error causing mechanism of processing using DRAM operations must be identified and characterized and should be mitigated. So to address these two challenges, I will present first class. This is proposing an efficient vector scalar comparison algorithm that significantly reduces the required number of DRAM operations for comparisons. And the second is Ghost. This is presented in last week ISCA. This work identifies and reviews new source of errors in processing using DRAM operations and computation results. Okay, so today I will present Clutch first. The title is Clutch High Performance Vector Scalar Comparison Using DRAM via chunk temporal coding. Vector scalar comparison is a fundamental computation primitive that compares each element in a vector against a scalar value. This operation is widely used in data-intensive workloads, including database query processing and machine learning inference. However, due to its low computational intensity, the execution tends to be memory bound, especially for large vectors. Processing using DRAM is a computing paradigm to alleviate this. Alleviating this memory bound bottleneck. The existing processing using DRAM approaches require many processing using DRAM operations for comparison algorithms due to its fundamental bit serial execution model. To address this, we propose Clutch, which introduces the new data representation and algorithm. First, Clutch introduces temporal coding. This temporal coding encodes values so that a vector scalar comparison reduces to a single lookup, dramatically reducing processing using DRAM operation count. Second, a divide and conquer approach decomposes wide operands into smaller chunks, and each chunk compared using a compact look table. This enables a flexible throughput and footprint trade-off. And our evaluation on predicate evaluation and decision tree inference shows that Clutch achieves 12 times higher throughput and 69 times higher energy efficiency over CPU and 2.9 times and 3.0 times over the state-of-the-art with serial processing using DRAM approach. And here is the outline of this talk. And I will start with the background of vector scalar comparison and processing using DRAM. Vector scalar comparison is a fundamental primitive that compares each element in a vector against a single scalar value. As shown in this figure, we have here n-bit scalar value A and vector B, where each element bi is also n bits. For each index I, we compare scalar value A against the ith element of vector B, producing a 1-bit result, yi. However, this operation is a fundamental primitive in data-intensive workloads, including predicate evaluation in databases and decision tree inference in machine learning domain. However, due to its low computational intensity, its execution tends to be main memory bandwidth bound, especially for large vectors. I will give a quick overview of DRAM background. And DRAM is used as the main memory in many computing systems. And a DRAM module consists of multiple DRAM chips, and each chip contains multiple banks, and each bank is composed of multiple subarrays and sense amplifiers. And within each subarray, there is a two-dimensional array of DRAM cells, and each cell stores 1 bit of data as charge in the capacitor. And these cells are organized into loads that are selected using baud lines, and cells in the same columns are connected to a sense amplifier. Let us look at the fundamental challenge in today's computing systems. And today's computing systems are processor-centric, meaning all data must be moved from DRAM to the processor for computation. And this data movement between DRAM and the processor has become a major bottleneck. Specifically, in processor-centric execution, low computational intensity operations, such as the vector scalar comparisons, are main memory bandwidth bound, leaving computing units underutilized. To address this data movement bottleneck, processing using DRAM repurposes DRAM from a storage device to a computation device, and processing using DRAM leverages the analog operational principles of DRAM cells to perform computation directly within DRAM. Let me introduce the two fundamental processing using DRAM primitives. I will start with low copy. Low copy transfers data between loads within the same subarray, enabling efficient bulk data movement inside DRAM. So this figure here shows a DRAM cell array, and where each circle represents a DRAM cell and its 1-bit stored value. Low copy works as follows. We first activate the source load and then activate the destination load in quick succession. Due to the analog operational principles of DRAM cells, the destination load is overwritten with the data from the source load. In this way, low copy efficiently copies an entire row of data from a source load to our destination load and entire within the DRAM array. Next, let me introduce the second primitive, majority sleeve. Majority sleeve activates 3 loads simultaneously, and this causes charge sharing on the bit line, such that each column independently and concurrently computes the majority of the activated cells in that column. For example, as shown in the leftmost column of this figure, if the 3 activated cells store values 1, 0, 1, the result is 1 because the majority is 1. And each column performs majority sleeve concurrently, enabling massive parallelism across all columns in a DRAM bank. Now let me explain how prior processing using DRAM performs arithmetic. Prior processing using DRAM performs arithmetic by vertically aligning the bits of operands within a single column and executing processing using DRAM operations in a bit serial manner from LSB to MSB. This figure illustrates how arithmetic is actually executed on DRAM subarray. Some loads are designated as compute loads, which support simultaneous activation of 3 loads, enabling majority sleeve operation. And initially, the bits of 2 operands are stored vertically in the same column in non-compute loads, and they are also constant loads, which are filled entirely with either zeros or ones. And here, let me walk you through the first step of multiplication between these 2 operands. And first, we use low copy to move the LSB bits of one operand into a compute load. Next, we copy the LSB bit of the other operand into another compute load. And then we copy a constant load filled with zeros into the third compute load. And by executing majority sleeve over these 3 compute loads, we obtain the AND operation of the 2 LSB bits, which correspond to the first partial result of the multiplication. So by repeating this process from the LSB to the MSB in a bit serial manner, processing using DRAM ultimately performs the full arithmetic operations. Now let me move on to the motivation and opportunity for processing using DRAM. In this slide, we discuss why processing using DRAM is particularly promising for vector scalar comparisons. So vector scalar comparison has low computational intensity, which makes processor-centric execution main memory bandwidth bound, as the processor must continuously fetch large amounts of data from DRAM. And this suggests a key opportunity for processing using DRAM. In particular, due to the arithmetic nature of vector scale comparison, processing using DRAM can explicitly reduce off-chip data movement. Now let me walk you through this figure, which compares the two execution models. And in both cases, the end bit vector B is stored in DRAM and the processor holds a scalar value A. The goal is for the processor to obtain the 1-bit comparison result bitmap. In the processor-centric case, the processor must pass the entire n-bit vector B from DRAM, and this involves large off-chip data movement. And the processor then compares each element of B against the scalar A, obtaining the 1-bit bitmap Y. In contrast, processing using DRAM can significantly reduce this off-chip data movement. In processing using DRAM, the elements of vector V are stored vertically across columns in the DRAM subarray. The processor issues processing using DRAM operations based on the scalar value A, performing the vector scalar comparison entirely inside the DRAM array without reading B from DRAM. This is possible because the scalar value A is shared across all elements, allowing the same operation to be applied to every column. For example, using constant rows, the processor can initialize A inside DRAM via row copy operations without any write operations. As a result, the 1-bit comparison result of bitmap Y is produced directly inside DRAM. And to obtain the result, the processor only needs to read the 1-bit bitmap Y rather than the full n-bit vector B. Therefore, processing using DRAM exploits the 1-bit nature of the output bitmap Y to significantly reduce data movement. Furthermore, in many workloads, the output bitmap Y is combined with other bitmaps in downstreaming processing. In such cases, processing using DRAM can use Y directly inside DRAM for subsequent processing using DRAM operations, potentially eliminating even the transfer of this bitmap Y. In summary, while processor-centric execution requires reading at least the full n-bit vector B, processing using DRAM requires at most reading the 1-bit bitmap Y. This reduces the data transfer volume by a factor of n or more. Now let me discuss the limitation of prior bit serial-based processing using DRAM for vector scale comparison. Bit serial-based processing using DRAM processes 1 bit at a time, repeating processing using a DRAM operation from the LSB to the MSB. As a result, bit serial comparison of processing using DRAM requires many processing using DRAM operations, limiting the performance improvements. In processing using DRAM execution, there are two main sources of latency: the processing using DRAM operations themselves and reading the output bitmap Y. In our evaluation, processing using DRAM operations become the major bottleneck, accounting for 76% of total latency in 32-bit comparisons. This large operation count makes it difficult to outperform processor-centric execution, especially when parallelism is limited. Therefore, the key challenge is reducing the number of processing using DRAM operations is critical to unlocking the full performance potential of processing using DRAM for comparison-intensive workloads. So our proposed method CLUTCH directly address this bottleneck by significantly reducing the number of processing using DRAM operations required for comparison algorithms. Now let me give an overview of CLUTCH, which stands for comparison algorithm using lookup table with chunked temporal coding. CLUTCH introduces two key ideas, and the first idea is temporal coding. CLUTCH encodes vector elements using temporal coding so that a vector scalar comparison reduces to a single row lookup. This dramatically reduces the number of processing using DRAM operations. The second idea is chunked divide and conquer approach. To address the large memory footprint of a full width lookup table, CLUTCH decomposes the wide operands into multiple smaller chunks, and each chunk is independently compared using a simple smaller lookup table. significantly reducing the memory footprint. Now let me walk you through the design of clutch, and I will start with the first key idea, the lookup table-based comparison using temporal coding. The key idea is to encode vector elements using temporal coding instead of a binary representation. Let me give you a concrete example. Consider scalar value a equals 4 and a vector b equals 6 to 4. And let us first encode v0 equals 6 in temporal coding. In temporal coding, our value v is represented as v leading ones followed by zeros. So v0 equals 6 is encoded as 6 ones followed by a 0. Now, just like in prior processing using DRAM, we store each temporally coded element of vector b vertically across the columns over DRAM subarray. A key property of temporal coding is that the jth bit of the ith bit of the encoded value represents the truth value of I is less than b. In other words, bit I is 1 if and only if I is less than b. Using this key property, if we look up the row corresponding to the scalar value a, the row directory contains a comparison result bitmap for all elements. In this example, since scalar value a equals 4, we simply look up row 4, and that is we issue a single row copy operation from a row index 4. And the resulting bitmap is produced directly inside DRAM, and this way a vector scalar comparison can be executed with a single processing using DRAM operation. Therefore, the lookup table-based approach significantly reduces processing using DRAM operation count. However, a naive with this lookup table requires 2 to the n rows for n bit values, so this results in a prohibited memory footprint for large bit widths. To address this, clutch introduces the second key idea, the divide and conquer approach. Let me give you a concrete example of the divide and conquer approach using a comparison of a equals 5 and b equals 6. And each square represents a 4-bit binary representation arranged from MSB to LSB. In the divide and conquer approach, we split the full width binary operands into several smaller bit chunks. And in this example, we divide each operand into 2 chunks. Chunk 1 covering the 2 MSB bits, and chunk 0 covering the 2 LSB bits. For operand A, the MSB chunk A1 represents the value 1 in 2 bits, and the LSB chunk A0 also represents the value 1 in 2 bits. And similarly, for operand B, the chunk B1 represents the value 1, and the LSB side chunk B0 represents the value 2. And in clutch's divide and conquer approach, we perform comparison on a per chunk basis. We then merge these per chunk results, per chunk comparison result to obtain the final comparison result. In this example, we compare A1 with B1 and A0 with B0, and use these results to derive the final comparison result over A less than B. But how do we actually conquer? That is, how do we derive the final comparison result from these per chunk results? Now let me explain how we conquer, that is, how we derive the final comparison result from the per chunk results. To derive the full comparison result of A less than B from the 2 per chunk result, we reformulate the comparison expression step by step. First, A less than B is equivalent to the MSB side chunk A1 is less than B1, or the MSB side chunk A1 is less than or equal to B1, and the LSB side chunk A0 is less than B0. Now, since A1 is an integer, the term A1 less than or equal to B1 can be written as A1 minus 1 is less than B1. This is convenient because it allows us to evaluate this term using the same lookup table as A1 less than B1. And surprisingly, this three-term Boolean expression turns out to be equivalent to a single majority Lie operation. This means that the entire merge step can be executed with just a single majority Lie operation. Now let me explain how this divide and conquer approach is combined with temporal coding and executed on processing using DRAM. The vector elements B stored in DRAM are encoding with temporal coding on a per chunk basis, like this. And with this encoding, when stored in DRAM, each chunk forms its own compact lookup table. To derive the final comparison result, we first need the 3 per chunk comparison results, and each of these can be obtained by referring, that is, doing row copy, the appropriate row of the corresponding per chunk table. Then, as shown in the expression above, we apply majority Lie over these 3 results to derive the final comparison result. The example I just showed uses a chunk count of 2. However, the divide and conquer approach can be applied recursively from the LCD side, generalizing to any number of chunks. And by adjusting the number of chunks, a clutch provides a flexible trade-off between latency and memory footprint. And this figure illustrates this trade-off. The x-axis shows the number of processing using DRAM operations, and the y-axis shows the required DRAM loss. And for example, in 32-bit comparison case, using 5 chunks produces 11 times faster than bit serial processing using DRAM with around 400 loads. On the other hand, using 8 chunks produces 66.4 times faster than bit serial processing using DRAM with around 120 loads. Let's move on to our evaluation. And let me briefly describe the evaluation methodology. For the evaluation step, we use a system with 4 16GB DDR4 DIMMs in dual channel configuration with an Intel Core i7. For processing using DRAM, we evaluate 2 different processes using DRAM architectures and modified DRAM, which is modeled after commercial off-the-shelf DRAM chips, and SIM-DRAM, the most representative processing using DRAM architecture. For workloads, we evaluate on a predicate evaluation and addition tree inference. And in this talk, we focus on predicate evaluation. For predicate evaluation, we use 5 queries containing where clauses as shown in this table across 3 operand bit precision, 8-bit and 16-bit and 32-bit. And our main metric are CPU normalized throughput and CPU normalized energy efficiency. For the CPU, we utilize bit-within-V, the state-of-the-art CPU implementation. And throughput is measured on real hardware. For processing using DRAM, we develop our cycle-accurate simulator to obtain precise throughput estimates. For clarity, here we present the result for Q2. This figure shows the result across the CPU and 2 processing using DRAM architecture. The first one is unmodified DRAM, and the second one is SIM-DRAM. And for each processing using DRAM architecture, we show results for both bit serial execution baseline and clutch. The results show the clutch significantly improves performance over both baselines. Specifically, clutch achieves up to 83 times and 50 times on average, and higher throughput over CPU, and up to 4 times and 3.1 times on average over bit serial processing using DRAM. And clutch's advantage is consistent across all 5 queries, and on average, clutch achieves 28 higher throughput over CPU and 2.2 times higher throughput over bit serial baseline processing using DRAM. Next, let me show the energy efficiency result again for Q2. Clutch significantly improves energy efficiency over both baselines, specifically achieving up to around 200 times a better energy efficiency over CPU and up to 4.2 times over bit serial processing using DRAM. And our paper is also available on archive now, and so please feel free to check it out for full details. And for more application evaluation in the paper and more details overhead analysis, including throughput memory footprint trade-off and data conversion overhead in this paper. And let me conclude this talk and this paper. So in this paper, we presented clutch processing using DRAM-oriented algorithms and data representation, and combining temporal coding and divide and conquer approach, and providing a flexible trade-off between throughput and memory footprint. And clutch achieves 12 times higher throughput and 69 times better energy efficiency over CPU execution, and around 3 times over the state-of-the-art bit serial processing using DRAM approach. And clutch, this result demonstrate that DRAM can serve as a high performance and energy efficient computing substrate for comparison intensive workloads. So this is the end of the first paper. So should I take some questions here or move on to the?
Since we have last 5 minutes, you can take questions and start the next session about those.
Okay.
How does that sound?
If you have any question, I'm happy to. Okay. Okay, so let's move on to the second paper, Padgos. And this paper shows the reliability challenges of processing using DRAM. And the full title is Padgos Experimental Analysis of Computation Result Corruption in Processing Using DRAM Operations on Real-Time Chips. Okay, let me give you a quick overview of our work. I will skip, okay. So processing using DRAM is a promising computing paradigm, and processing using DRAM has a key expectation. Ideally, each column's result is determined solely by the activated cells used as operand data. However, no prior work studies how data not intended to participate in processing using DRAM operations, that is, non-operand data, affects processing using DRAM reliability. So we characterize 96 real DDR4 chips to study Padgos interference phenomena where non-operand data collapse processing using DRAM operations. And we find two major results. First, non-activated loads affect timer outputs by up to 10%. A second, concurrently computing columns affect timer outputs by up to 48%. To address Padgos, we propose robust column screening techniques, and our solution provides around 400 times a lower matrix vector multiplication error compared to Padgos and Navier systems. This is the quick summary. Okay, the background, I can skip the background. Okay, so yeah, let me give you a quick overview of the more analog operation of the simultaneous multiple row activation. The simultaneous multiple row activation is a core computational capability of processing using DRAM. And in this figure, each rectangle represents the DRAM cell. And here we have 4 rows and 2 columns. And cells in each column share sense amplifier. And in this figure, processing using DRAM activates 3 rows simultaneously so that each column performs a majority sleep operation. For example, these highlighted cells in red are operands for C0, and the blues ones are operands for C1. And when timer starts, it enables charge sharing across the activated cells in each column through the shared bit line. And then the sense amplifier kicks in and samples the result. As a result, each column performs majority sleep over its own operand data. So interestingly, recent work demonstrates that commodity off-the-shelf DRAM chips can simultaneously activate multiple loads up to 32 loads. I can skip this slide maybe. So now let me move on to the problem of processing using DRAM and goal of our work. And for processing using DRAM to function reliably, there is a key expectation. So each column's computation result, namely each column's Cymer result, depends solely on its own operand data. However, we hypothesize that this key expectation might be challenged by ongoing DRAM density scaling. It is because with rapid DRAM scaling and denser cell arrays, even regular DRAM operations become susceptible to interference from neighboring cells. So therefore, our key research question is, does this key expectation of processing using DRAM hold on real DRAM chips? Unfortunately, the answer is no. So in this work, we are the first to review an interference phenomena that collapses processing using DRAM computations on real DRAM chips, which we call pad ghost. The first source of interference is data stored in non-activated loads. And the second source is the data stored in other columns that concurrently perform computations within under the same timer operations. Due to these two interference from non-operand data, processing using DRAM computations can produce erroneous outputs. So therefore, pad ghost violates the ideal picture of processing using DRAM and threatens the robustness of processing using DRAM systems. Now let me describe our testing infrastructure. And we use DRAM vendor, which provides fine-grained control over DRAM columns. And here in our laboratory, we test a wide variety of DRAM modules. And we test 96 DDR4 chips from SK Hynix, covering 3 different die division and chip density pairs. And we test Cymer with 2 to 32 Cymer rows. And now the question is how to quantify this interference from non-operand data. And our key approach is to vary data not intended to participate in Cymer and measure the resulting change in Cymer outputs. So let us now look at the detailed methodology for interference from non-activated loads. And our main metric is PO1, the fraction of output bits across all columns that equal logic 1 when Cymer is executed with random inputs. And we define control cells as cells whose data pattern is intentionally varied to observe how Cymer outputs change. By varying the data in these cells, we quantify how these control cells affect Cymer outputs. And in order to identify which non-activated loads are affecting Cymer outputs, we compare these 4 configurations. In this figure, the cell array represents the target subarray, the red band represents Cymer rows, and the blue band represents non-activated loads. Non-activated loads that are physically adjacent to the Cymer rows. Among the cells, gray one indicates that they are initialized with fully random data, while purple ones represent control cells whose data pattern we intentionally vary. For example, our baseline configuration 1 base with all rows with fully random data with no control cells. And on the other hand, configuration 2 designates all rows except the Cymer rows as control rows, and 3 and 4 have the different configuration here. And here's the result on real DRAM chips. And first, let us look at the result when all control cells saw all zeros. And the y-axis shows PO1 under each configuration, normalized to the baseline PO1. Recall that PO1 is the fraction of output bits that equal logic 1. So a normalized PO1 of 1.0 means no change from the baseline, and higher normalized PO1 means Cymer outputs contain more logic 1. And the x-axis shows the 3 different non-baseline configurations. Among them, we observe significant deviation from the baseline in 2 configurations, configuration 2 and 3. And in these 2 configurations, PO1 decreases by 2% on average from the baseline. So our key observation is that non-activated loads by a summary outputs to a logic 0 when the loads store logic 0 by 2% on average. And on the other hand, the remaining one configuration shows no significant deviation from the baseline. Notably, only in this configuration, control cells do not include the non-activated adjacent loads. This indicates under the key observation here that interference from non-activated loads is highly localized to physically adjacent loads. So this is the result of the all ones, and we observed exactly the opposite effect. So I can skip. And quick summary of these non-activated loads characterization results is the non-activated adjacent loads by a summary outputs to a logic 0 when storing the loads storing logic 0, and to a logic 1 when storing logic 1. So here is the key takeaway, and we can quickly show the another characterization result, interference from concurrently computing columns. We designate target columns randomly selected one nature of all columns, and main metric is VO1, the fraction of output bits across target columns that equal logic 1 when summary is executed. And we vary the data pattern in these purple cells as control cells. And the result is here. So key takeaway is the columns that concurrently perform computations affect summary output by 6% on average and up to 48%. And this magnitude of interference is way stronger than the interference from non-activated loads. So here is the key takeaway. So concurrent computing columns more strongly affect summary output than adjacent loads. Okay, so in this paper, we proposed some mitigations against this interference from non-parent data. And specifically, we proposed the column screening technique, which identifies reliable columns, and we utilize these columns in the application. So I think we have no time, so we can skip this slide, and I want to show the conclusion. Finally. Okay, so here's the conclusion. So we extensively study the impact of interference from non-parent data, and we characterize 96 DRAM chips, and we find that these two major sources of interference, non-activated loads and concurrently computing columns. And we propose path ghost aware column screening techniques, and our solutions reduce these matrix vector multiplication errors by around 400 times, and this result is obtained on the real DRAM chips. And we hope our work motivates and guides solutions to enable future processing using DRAM systems that are robust. Okay, that is the end of this paper. Thank you.
I'm not sure what you mean by concurrent components. It's row operations combine the entire rows. It's all columns in the row.
They're all columns, but sorry, I can't catch the last part of your question. Sorry, I can't get the last part of your question.
You say concurrently computing columns.
Yeah.
I mean, you're not selecting individual columns. When you select rows, all columns inside these rows will operation.
Okay, so I think I should show the detailed experimental setup. So here is the experimental setup of the interference from concurrent compute columns, and we select one maze of all columns. Here is the target columns we call, and the remaining columns of the activated cells of the remaining columns are control cells. right? So these control cells affect the target column's timer output. That means interference from concurrently computing columns. So am I answering your question or? Okay, sure. Okay, so in this expander setup, we target the some columns across all columns. So here for example, we have 8 columns here and 8 timer outputs we get. However, we target only 2 columns here. And we obtain and observe the only 2 bits of the timer outputs. And the 6 remaining columns are served as the control cells. So the source of interference. Yes, right.
This means you have greatly reduced data you actually.
Yes, in this experiment setup, yes, the answer is yes. My opinion is it is not correct. So I mean this is only the experiment setup. So when we deployed some applications on the real processing using the DRAM systems, we utilize all columns. So we utilize the massive parallelism across all columns, across all bank. But in this experiment, we target only 2 columns here, and we observe the 2 timer outputs from these target columns, and the remaining 6 columns are serving controls columns.
You want to increase stability. So later, if you say later you're not doing this, or you're using all columns. So later, if you're using all columns, then you will have this interference.
I think I can chime in. So here it's just to understand the experiments that these, let's say, neighboring columns affecting the target columns. But if you go to the mitigation part, I think what he's doing is he's first screening the columns, which are getting more like this. So some of them are reliable, even there's an effect, some of them are not. So here it's just basically blacklisting or not using them, but it's not as let's say severe as the experiment. So it's not 1/8 or something. I guess it's 40,000 out of 64,000, something like that, right?
Yeah, right.
So it's more than half, but you're still reducing it, basically. But to begin with, they aren't useful. They were producing incorrect results. Does that answer your question?
Okay, so you characterize it. So later, you actually do the operation to.
Yeah.
It's basically you first secretly characterize, so you understand there's an effect. So we know that was for the characterization. Here you do the experiments first to understand which ones are not reliable, and then you blacklist them, and you work on the other ones. That's one of the options that you can.
Yeah, the key ideas of the column screening is with the sufficiently large random input sets, we can identify the reliable columns, robust, resilient to the interference from the concurrently computing columns. So that is the key idea of column screening.
Okay, but then it is what I was saying before. Like, the parallels operate in order to get a more reliable.
Yeah, exactly.
It's not like 1/8. It's just around 25% or something.
Yeah, I have the data about the yield of the processing using DRAM columns. So the leftmost graph shows the columns pass the column screening. So this result shows about 6% to the 8% of columns across all columns are reliable in this our experiment setup. So as you said, so the reliability, there's a trade-off there between the reliability and the processing using DRAM throughput. Thank you.
Okay, but this would be quite challenging in the actual application. Like, DRAM chip, you would have different problems selected, so that they can actually run in the real application scenario. This would be quite challenging. Because on every memory page, you would have to remember, you have to use different columns.
Yes, exactly. So we have to consider the granularity of the selecting columns. So the one idea is we select the granularity of the cache line or cache block. So this mitigates the overhead of such a system overhead.
Any other questions? Okay, we will come back maybe for the 3:10. So maybe we come at 3:35.
Thank you.
Thanks. Okay, this will be the last session. So we will start with Rakesh. He's going to talk about storage-centric computing, and he's going to talk about the works that he has done. And he's a senior PhD in Safari Research Group. I guess you're going to briefly introduce yourself also. So yeah, please feel free to start.
Okay. Thanks, Ismail. Thanks for the opportunity to present our work that we have been doing for some time now on storage-centric computing. So I'll give a brief introduction. So I've been in Safari research group for the last 5 years as a PhD student. Prior to that, I was working at Samsung Research for a while, and then I got my master's from University of California, Irvine. And if you would like to discuss more on any of these works with me, then you could contact me on this email. So I'll go back to this figure that Ismail was showing in the morning, that about the Apple M1 Ultra system. And a lot of this dark area that we essentially looked at is storage system, and that's basically considered as a passive device which stores data, and then you move the data to the compute logic and perform computations. But this space is so large that we can actually, and the storage system is also a very independent, it has a lot of compute logic inside it, like the SSD controller, which actually can be leveraged to perform computations. So with that, I'll start with one of our works called Flash Cosmos, where we explored how can we perform computations near the data, as close to the data as possible, which is the flash chips which store the data. So it's called Flash Cosmos in flash bulk bitwise operations using inherent computation capability of NAND flash memory. So this work was published at Micro 2022. So I'll give a brief idea about what we are trying to accelerate here. Here we are looking at bulk bitwise operations, which are very common in many applications like genome analysis, web search, databases, graph processing, cryptography. So this workload is typical of a lot of these operations. And the problem is that the data movement in traditional computing systems significantly bottlenecks the performance and energy efficiency. So you move a lot of data from the storage to the host CPU or the GPU to perform these computations. Now, let's look at the different paradigms that are out there, like the conventional systems, which we call as outside storage processing, that move the entire data to the CPUs and GPUs through the memory hierarchy. So you basically go through the main memory from storage and then perform computations. And if you look at the bandwidth of these devices or the interconnects that connect these devices, the storage I/O bandwidth is around 8 gigabytes per second if we consider PCIe Gen 4. And then the main memory bandwidth is much higher. So this storage, external bandwidth of the storage is what is essentially kind of creating the bottleneck in conventional systems. So there are a bunch of near data processing techniques that have been proposed for bitwise operations, starting from SRAM, where we look at compute cache. Then DRAM based main memories, we propose Ambit. Our group has done the work. Then we have Pinatubo for non-volatile memory, and then for NAND flash based storage, we have Parabit, and in storage processing unit, where we essentially use the SSD controller. We have a work for that as well. So our focus in this work was to look at these two paradigms and then see which one can be accelerated. So since these data sets that are for bulk bitwise operations are quite large, they don't fit in the main memory. So we look at these two paradigms. So if you look at in-storage processing, where we perform computations using the compute units within the storage, like embedded cores or the FPGA, we see that so this is a more closer look at what is within the storage. So you have the in-storage compute units and then the NAND flash chips. So basically what we do is we perform computations within the storage units, and then you send the results only the results outside the device. So ISP can mitigate a lot of data movement overhead by reducing the data that you send outside the storage device. But then the bottleneck shifts to the internal communication channels through which we have to move the data. So if you look at the SSD internal bandwidth, it's around 10 gigabytes per second if we consider, let's say, 8 channels with a pretty low frequency. So the SSD internal bandwidth becomes the new bottleneck. Now, in-flash processing is the paradigm where we move computations even closer to the data, which is the flash chips. And here we look at performing computations within the NAND flash chip itself and sending only the results out of the flash chip. So ISP basically mitigates data movement very significantly. But then if you look at the state of the art in IFP, at least at the time of publication, this work's publication, we saw that there is a prior work which performs computations intelligently by controlling the latching circuit of the page buffer. So here you see a very cartoonish picture of the flash chip where we have multiple pages which store the data, and you have the peripheral circuitry which consists of the page buffer and other components. So let's say we store a lot of operands within the flash chip for the bulk bitwise operations. This prior work, basically what it tries to do is to perform sensing of each operand and bring it to the peripheral circuitry. And then that by controlling the latching circuit, we achieve this the bitwise operation. So if there are like 100 operands that needs to be operated on, then we need to perform the reads sequentially. And in a flash based device, the reads are very expensive. So, so the sensing operation is basically what is becoming the bottleneck in this prior work. And this actually causes a lot of energy and performance overheads in flash processing. So there is also another aspect which I need to mention, which is the reliability of this operation. So if we look at in-flash processing or near data processing, the typical way the SSD is designed is that you have the ECC module near the controller. So with in-flash processing, you cannot leverage that because that really causes a lot of data movement. So the limitation with the prior work is that if there are errors in the data that we are operating on, then it basically compounds, and then the result will be erroneous. So what it essentially means that the applications have to be error tolerant to use these kind of techniques. So in this work, we try to address the new bottleneck of IFP, which is the serial sensing of operands, and also to make the IFP more reliable, which is to provide accurate computation results. So our proposal is something like this. So you have a lot of operands that are stored in the flash chip. And then what we do is we perform a simultaneous sensing by activating multiple word lines. And then this actually results in the bitwise AND operation in the page buffer. So we also propose techniques to eliminate raw bit errors in the stored data, which I'll go into a bit more later. So some background on the on NAND flash. So a flash cell stores data by adjusting the amount of charge in the cell. So an array cell stores 1 if it has low charge level, and a programmed cell is 0 if it has high charge level. So when we activate these cells, the array cell operates as a resistor, and the programmed cell operates as an open switch. Now, if we combine or if we connect multiple cells serially, then it forms a NAND string. So you can see a NAND string here connected to a bit line. And let's say we don't want to read a bunch of cells, and we call this non-target cells. And the only cell that we want to read is this one, which is a target cell. Depending on the charge that it has, it either operates as resistor or open switch. The non-target cells operate as resistors anyway because we provide a high pass-through voltage for those cells during read. So when we read the data, the bit line current flows through the NAND string, and the sense amplifier reads the value as 1 if the current goes through the NAND string. Now, if there is a cell which is programmed and it stores the value 0, then it basically operates as an open switch, as I mentioned, and the sense amplifier reads it as a 0 because the current doesn't flow through the NAND string because there is an open switch. So with this, if we look at how the flash block is organized, you have a bunch of bit lines and NAND strings connected to each of these bit lines, and the cells that are connected at the same level are also connected to each other using a word line. So this word line controls a large number of cells, and it provides high bit level parallelism. And if you look at multiple such blocks which actually share the same bit lines, what we see is that the key observation that we made in this work is that cells in the same block are connected serially, and this is very similar to the digital AND logic. And if we look at the cells connected across different blocks, then we see that it's similar to the OR logic because they are connected in parallel. Now, with this insight, we basically try to see how we can perform these bulk bitwise operations. So we propose something called the multi-word line sensing technique, which actually does a single sensing operation across all the operands in a flash chip, and that results in bitwise operations. And to improve the reliability, we use something called the enhanced SLC mode programming, and that eliminates raw bit errors in the stored data. So let's look at what MWS is doing and for the bitwise AND operation. So we use something called an intra-block MWS, which simultaneously activates multiple word lines in the same block, and this results in the bitwise AND of the stored data. So here we have one block with multiple word lines. So what we do is, again, if we want to, let's say, if our operands are in word line 1 and word line 2, we basically consider the other cells as non-target cells. And then depending on the state of those cells, when we perform the read and when we activate these two word lines simultaneously, what we get is the cells which are in the array state, which operate as resistors, only those cells let the current pass through. And as I mentioned, the other NAND strings, the current doesn't pass through because they have open switches. So this means that when all the cells are having the same value, or let's say operate as resistors, then this results in a bitwise AND. So the result will also be read as 1. So again, this is an extension of this, of what I showed before. If you have more word lines, again, the same logic applies. So even if there is one cell which operates as an open switch, the result would be a 0. So that basically is the AND logic. Now, after intra-block MWS, we looked at inter-block MWS. So how can we leverage this MWS operation across blocks? So again, as I mentioned, we looked at the digital OR logic. So if these cells are connected in parallel, or the NAND strings are connected in parallel, so we basically perform the sensing by activating word lines across different blocks. And even if, let's say, you have a cell which operates as an open switch in one of the blocks, the current still passes through because they are connected in parallel. So as you can see in the NAND string connected in bit line 3 and in bit line 2. So this gives us the result of the OR operation. So this is again an extension on multiple blocks. So inter-block MWS basically provides us the bitwise OR operation in different blocks with a single sensing operation. So we also show that in this work that Flash Cosmos can support other bitwise operations like NOT, NAND, NOR, XOR, and XNOR by leveraging the existing features of flash memory, and I invite you to check the paper for more details. So now let's look at reliability. So how do we eliminate the raw bit errors in stored data? So the goal is to, again, provide reliable computation results. The key idea is that if we use a single level cell called SLC mode programming, it trades storage density for more reliable computation. You store much less bits in the cell, and that makes it a bit reliable. But then SLC also performs more precise programming of the cells, or we actually extend this logic to perform more precise programming. And this also increases the latency of the programming operation. So our goal is to maximize the reliability margin between the different states of the cell. So in an SLC mode, you can check in the paper, but I'll give a brief overview. Like SLC mode has two states, a program state and an array state. Now, if we increase the voltage margin between these two states, then it becomes more reliable, because the read operation, even if there are disturbances or retention issues, it will still provide us accurate results. So Flash Cosmos enables reliable in-flash computation by trading storage density and programming latency. And these overheads affect only the data used for in-flash computation. So we have seen in the recent years that more and more works have leveraged this ESP programming method for near data processing techniques. So yeah, it basically provides reliable computation. Now, if you look at the evaluation of this work, so what we try to do is to use real device characterization to validate the feasibility and reliability of Flash Cosmos. We use 160 48 word line TLC flash cells and tested more than 3.5 million word lines, and under worst case operating conditions. Like we use the worst case data patterns, and we also made the flash cells reach around 10 kPe cycles and under 1 year retention time. So for system level evaluation to check the performance and energy, we used the state of the art SSD simulator MQSIM, and we used 3 real world applications: bitmap indices, image segmentation, and k-click star listing. So we also compared it with the outside storage processing, which is where we model the multi-core CPU, in storage processing, where we model an in storage hardware accelerator, and the state of the art in flash processing scheme. So our real device characterization showed that both intra-block and inter-block MWS operations require no changes to the flash cell, to the commodity in the commodity flash chips. And both these operations, there are some limitations that I will not go into. In case of intra-block, which is how many operands we can activate within a block, we can do up to 48 word lines at a time. And in case of inter-block, we can only do 4 at a time because of the power considerations. So this results in a small increase in sensing latency, which is less than 10%. And enhanced SLC mode programming provides significantly better results in terms of reliability. So if you look at our system level evaluation, here the main insight that we get is, because of reducing the data movement, we achieve a lot of speed up over the current systems, and also we get energy benefits. And these benefits actually increase if we have more operands, and we can actually simultaneously sense all these operands at the same time. So we have more details in the paper that I will not go into. How we actually provide some detail, a lot of details on how we can enable this at the system level. What are the different commands that we propose to activate this, and so on. So this is the link to the paper. So in summary, Flash Cosmos is the first work that enables in-flash multi-operand bulk bitwise operations with a single sensing operation and high reliability. It provides performance benefits and energy efficiency as well. And all these benefits come with very low cost and requires no changes to the flash cell arrays. So that's the first work that I wanted to quickly discuss. Any questions on this? Yes.
I don't know, like, source code for my memory, sorry. So
So we can actually use the multi-word line sensing technique for those cells as well. But the main challenge would be reliability, because with cell technologies, you end up cramping a lot of data, or the bit voltages are so close to each other that reliability cannot be guaranteed in that case. But there are some recent works which actually explore that, which I can discuss with you offline as well. Yeah. Yeah, so there with multiple bits, when you store multiple bits in a cell, basically what you need to do is you need to read the data, read the cell multiple times to actually get the data which is stored in a single, let's say, page in the word line. So if you have 3 pages in a word line, then you need to read it multiple times. So you can still keep it in the Boolean domain. But again, it comes with its own overheads. Yeah. So how are we doing on time? Maybe. Okay. So then maybe so there is another work that I'll probably skip, which actually takes this approach of performing computations within the flash chips to the next level, and does arithmetic operations as well. And also this work focuses on security aspects of performing computations. Maybe I'll just quickly give some background on this. We look at string matching as an operation that we can accelerate in this work, where we look at databases and bioinformatics, and many of these workloads have string matching in them. Now, if we look at the traditional system where we have a storage device in a server that is connected remotely, the user has to send a query to the server, and basically when the server does the matching of the query and the data. Now, and then sends the result back. Now, performing this computation on plain text can actually lead to data leakage, which is not very good. So recently we have been exploring more about homomorphic encryption, which actually enables performing computations when the data is encrypted. Now, so here with homomorphic encryption, we can actually encrypt the query, and it goes through the network as encrypted data. Then we also encrypt the database, and then we can actually perform computations on the database, and then get the results back, and the user can decrypt it. So there are multiple ways to do this. We have something called Boolean approach, which actually provides very let's say granular way of doing computations, but it comes with high memory footprint, high computation cost, but it supports flexible query size. There is arithmetic approach, which actually has low memory footprint and low computation cost, but it supports limited query size. So I'll not go into the details of how this is done, but basically when we encrypt, let's say a chunk of data which is around 128 bytes using homomorphic encryption, the end result becomes around 8 kilobytes, which is around 64 times increase in the size of the data. Now, we looked at what operations are being performed in the arithmetic approach, and we saw that 98% of the execution time is basically consumed by the homomorphic multiplication. So this is 100 times slower than the homomorphic addition on a CPU system. So our goal in this work was to basically convert all these homomorphic multiplication operations into homomorphic addition, and that gives us significant energy and performance benefits. And of course, we are looking at in-flash processing for that. So I'll basically not go into the details of this. So what we do is we efficiently pack data so that we are not operating on single bits at a time. And that also the way, based on the way we pack the data, we see that from 64x increase in the data size, we get only 4 times increase in the data size. And then we also look at how we can convert the multiplication into addition operations. So the addition operation is basically an element-wise operation in addition in homomorphic addition domain. So we get an encrypted result when we perform addition of 2 operands. So once we decrypt it, if the result of the string match is a set of ones, then it means that the match is found. So what we do here is we actually we have encrypted the data, but when we are sending the query, we invert the query and then encrypt it and then send it to the remote server for doing the comparison. And when we get the result, we actually see that the decrypted value is a bunch of ones, which means that the match is found. However, how do we find out that the match has happened? Because this data is lying in the server. So what we do is we prepare a match value, which is a bunch of ones, encrypt it, and then send it to the remote server for comparison. And based on where exactly it matches, we generate the index and send it back to the client. So this is the part which maybe I should focus on, which is how we perform this computation. So we use bit serial addition to avoid carry propagation across different bit lines. So what we do is if we have data the data is typically stored in the horizontal layout in the flash cells, in the flash array. But what we do is we perform vertical data layout. We store it in the vertical data layout in the flash memory. And we perform a series of operations that I'll not go into, which gives us the full adder implementation within the flash chips. So basically the controller or the host sends the data, the query from the controller to the flash chips, and we perform a series of operations that gives us the full adder implementation. So what we have done now is we perform the additions in the flash memory. Now we need to generate the final index where the match has happened and send it to the host. So to do that, we actually use the general purpose cores that are present within the SSD. These are ARM Cortex cores that are present. So we leverage them to identify the final match. So I'll skip some of these because again, because of reducing a lot of data, not sending data to the CPU, we get a significant performance benefit. Here we show for different query sizes, what is the speed up that we achieved. Yeah, let me go there. So we compare it against a bunch of techniques where we perform computations in the DRAM and the DRAM within the SSD and also in flash processing. And we see that in flash processing provides much higher benefits than the other places where we can perform computations. And this is by reducing the data movement. So again, we see energy benefits as well. So yeah, basically this work is one of in the series of in-flash processing works. This proposes more complex operations and also looking at the security of the data. So I'll skip these and maybe more. Yeah, you can find the link to the paper, the extended version on archive using this QR code. So after this, I'll try to if there are any burning questions, then I can take that. Yes. So I'll go into this. So what we did was we again kind of separated 2 aspects. One is like we looked at our data packing scheme, which is how we chunk the data. And that was done on a real system, real hardware, like evaluated on a real system. But again, if you look at in-flash processing and in-storage processing techniques, we can't really use the real system because of the lack of any device like that. So we had to leverage to our simulator to do that. Yes. I agree. Yeah. So again, in this work also we'll leverage this SLC mode of the flash cell, and we also increase the voltage margin. So we are still able to not have reliable computation results, but again the capacity is much less because we use 1 bit per cell instead of 3 or 4 bits per cell, right? So I agree with you. And also looking at the whole broader HE domain, as you said, it's more, let's say, noise prone. So we have some techniques that we use in the paper. I'll not go into. Maybe if you read the paper, you will get more details. Okay. Okay. So I'll quickly move to another level of how we can leverage these compute possibilities within the storage system, and maybe look at adoption issues of these techniques. So this is a work which was recently presented at HPCA 2026. It's called Conduit, where we propose a programmer transparent near data processing framework for leveraging these multiple compute resources in the SSD domain. So I'll give a bit of background. Again, this is something that many of you know. We have the host and the SSD which communicates over the PCIe protocol, and we have the SSD controller, which is basically the brains of the device. It has a lot of, it has many embedded cores, which are typically ARM Cortex cores. We have tiny cores called flash controllers, which communicate with the flash chip via flash channels. And we also have a DRAM within the SSD, which actually is, we have been using it to only store recently accessed data, to kind of avoid going through the back end, and then leverage it to get lower access latencies. And also we have an address translation logic within the flash chip, within the SSD, that needs to be stored in the DRAM. So so we have again discussed a lot about in-flash processing, but there is also a large body of literature on in-storage processing, where we actually leverage this embedded cores in the SSD controller for computations. So we have many ISP works where, like Biscuit, GenStore, and Rise, for example, which show that complex tasks like filtering, aggregation, encryption, and search can be accelerated using these cores. There are some works which also use FPGAs near the SSD controller. Yeah, so those are ISP as well. Now, there is also this DRAM that I mentioned, which actually can be leveraged for computations. And Ismail has mentioned a lot about how we can perform bulk bitwise operations and complex operations using using DRAM, which is processing using DRAM. And these are based on intrinsic operational principles of the DRAM. So we have a bunch of works from our group which show that bulk bitwise and complex arithmetic operations can be done within the DRAM. And then we have in-flash processing, which I mentioned just now, where we exploit the flash chip structure and perform computation. So we have some techniques that I did not discuss here, like Aries flash, which again control the latching circuit and perform more complex operations. Then Flash Cosmos does it in a different way, where we sense the data simultaneously and get bulk bitwise operations in the flash chip. So if we look at the trade-offs of these different paradigms that actually an SSD can support, we see that ISP can support a large set of operations. It is more general purpose than the other paradigms, but the embedded cores are quite wimpy and they provide limited performance. Now, processing using DRAM is it actually performs computations in a very highly parallel manner within the DRAM chips. But in the context of an SSD, it requires transferring large amounts of data from the flash chips to the DRAM via bandwidth limited channels. In-flash processing eliminates data movement significantly, and it provides high computation parallelism. But the paradigm is evolving still, and it has limited operation set. So we try to ask these questions. Is a single paradigm good for all the workloads? Which is the most suitable NDP paradigm for each computation? And do we need to combine these NDP paradigms to gain some performance and energy benefits? So we conducted a case study on combining the NDP paradigms, and we examined, so what we did was we examined the performance bottlenecks by hand mapping parts of the application to these computation resources. So we evaluated the host CPU, in-storage processing, in-flash processing, and combining ISP and IFP. Now, the workloads that we evaluated are basically hybrid workloads, which involve both computation and data movement, like aggregation and sorting. Then we have IO intensive workloads, which are dominated by data movement, like databases, bitmap indices, and many more. So we have more details in the paper. I'll not get into that, but the key results that we saw in this case study is that we show the overall execution time here normalized to the host CPU. So in case of hybrid workloads, the combination of IFP and ISP gives us 40% more performance improvement than, let's say, performing the computations on IFP alone. And this is by significantly reducing the data movement and also mapping computations to the more suitable computation resource. So you can actually leverage the ISP to do more complex operations, IFP to do, let's say, bitwise operations and reduce the data movement. Now, if you look at IO intensive workloads, the insight was not the same. So what we found was performing computations in IFP alone actually gives us more benefit than combining it. So a naive combination of these computation resources doesn't give the benefit because of the data movement that we intentionally introduce. So some of the key takeaways that from this study are like no single computation resource consistently performs well across different workloads. The performance bottlenecks are also workload dependent and they vary across different execution phases of the same workload. And offloading to multiple computation resources within the SSD provides benefits, but only when we do it judiciously. So if we then looked at the prior SSD-based NDP techniques, some of which I mentioned, like Flash Cosmos and the other works. So they map computations only to one or two paradigms, and they fail to exploit the full computational potential of SSD. They lack generality across a wide range of workloads, and they are not programmer transparent. These are some issues that have been kind of affecting the adoption of NDP within the SSD. So then we looked at offloading techniques that are proposed for main memory, they basically perform partitioning and mapping of application code segments between the host and the NDP units near main memory. So we classify them into two categories. One is bandwidth-based offloading. So what these works do is they look at the bandwidth utilization of these NDP units and the host and decide where the computation has to be offloaded, whether it has to be done in the host or in the NDP units. Then some works look at data movement offloading, data movement based offloading. They try to reduce the data movement as much as possible between these NDP units and the host and make decisions based on that. So we took these offloading models and then tried to adapt it to an SSD. And if you look at the results of these prior approaches or the speed up that they provide, we looked at an ideal approach, which is basically trying to offload to the best compute unit possible. And also there are no resource constraints in terms of like resource utilization is always the resource is always available, and the data movement overhead is also 0. So compared to this, an ideal approach, which actually doesn't exist, we see that the best performing prior model, which is the DM offloading, falls short by 2.5 times because of its narrow offloading model. So it only looks at data movement, and this sometimes can cause significant resource utilization issues. So if you try to reduce data movement and offload everything to a single resource, then it can cause queuing delays and so on, and resource contention. So our goal in this work was to enable a programmer transparent NDP that effectively utilizes all these computation resources, makes workload and system aware offloading decisions, and improves performance and energy efficiency. So we propose Conduit, which is a general purpose programmer transparent framework that dynamically offloads computations at instruction granularity to these computation resources. I'll give a very brief overview of what are the key steps in this work. So we have a compile time pre-processing step where we identify offloadable code regions in multiple applications and then transform them into wide vector operations. We have a runtime offloading step where we take these vectorized instructions and then basically decide which is the most suitable compute unit for execution of these operations. So let's look at compile time pre-processing. So we take an application code. This is an offline step, so it basically doesn't affect the latency of the framework. So then we run a custom compiler pass to identify offloadable code regions. We perform loop auto vectorization to transform scalar instructions into wide vector operations, and we set some flags to match the SSD's internal parallelism. Then we also leverage partial vectorization so that partially vectorizable code can still benefit from parallel execution as well. Then we extract some lightweight metadata during this process, such as operation type, operand width, and so on, for each vector operation, and store them in the intermediate representation. Why we do that is basically we don't want to spend a lot of time in the runtime to get these details when we are deciding where to offload the operation. And it also preserves the programmer transparency. Then we generate an executable that can be run on the SSD, on the cores that are present in the SSD, and then transfer them to the SSD. Now, in the runtime offloading step, what we do is we basically leverage one of the SSD controller cores to perform this offloading, runtime offloading. And the reason we do this is because the controller's cores have real-time knowledge of the current state of the resources. So like resource utilization, contention, and so on. So what we do is we map each vectorized instruction in the ARM executables to the most suitable computation resource using a cost function. And our cost function looks like this. So we consider various factors from application and the current system conditions. So we look at data movement latency, for example, which, so if the operands are present in one of the computation resource and we need to move it to another resource because that's the more ideal one to execute, what is the cost of performing the data movement? Then if you look at, we also look at expected computation latency. So we also need to, because these resources are heterogeneous and they have different execution models, the latency of computation also differs. So we need to consider this in the cost as well. Then we have the data dependence delay, which means that if the operations are being queued up to perform in a particular resource, what is the delay for operand availability and the resource queuing delay. So how many instructions are there in the resource currently pending, which needs to be executed first. So we consider these factors and then decide the total execution latency per resource. So we then compare the total execution latencies of all the resources and decide which one is more suitable based on the one which provides the minimum latency. And that's our offloading target. So then once we decide the offloading target, what we need to do is to perform instruction transformation, because those vectorized instructions cannot be directly run on these compute resources. So what we do is we basically leverage the ISA from some of the prior works that have proposed them and then try to convert or transform the instruction to the ISA of the native resource, and then offload the instruction to the compute resource. So we do that for each of these compute resources that are there. So we look at many more aspects of the design, like data coherence, because we have heterogeneous resources and the data can be present anywhere, and we may have consistency issues. So how do we solve that? Then we also have some data mapping constraints for each of these computation resources. So as I mentioned in Flash Cosmos, we need to place the data in a single flash chip in a block to perform bitwise AND operation. So those kind of constraints are also need to be considered. Then how do we manage the regular IO operations and the computation mode? Then there can be failures and many other aspects that we show in the paper. So I invite you to check the paper for more details. So in terms of evaluation, we build a event-driven SSD simulator that's based on MQSIM. That's a state-of-the-art SSD simulator. We look at 6 data-intensive workloads, including LLM training and inference, and then compare with different policies. I'll quickly show some performance numbers. So conduit, which is shown in green, provides a significantly higher speed up by making these holistic offloading decisions. So it considers a lot of factors when making this offloading decision. And it also provides 62% of the offloading, ideal offloading policies performance without making any of these unrealistic assumptions it makes. You see energy benefits as well. Looking at the way offloading decisions themselves, like what is the percentage of instructions that have been offloaded to each of these computation resources, we see that ideal and conduit make very similar offloading decisions. So that is also a proof that we are sometimes doing the right thing. So in terms of overhead analysis, we have some storage overhead to store the cost function features and the instruction transformation mapping. And we have some runtime overhead to perform this instruction transformation and to decide where to offload. And that's less than 4 microseconds, so which is not significant. And we don't have any area overhead than what the prior works already introduced. So we have more details in the paper. I quickly, this is show this QR code if you are interested to check the paper. So in summary, this is the first work that looks at general purpose programmer transparent NDP framework that enables fine-grained computation offloading across multiple SSD resources. We provide significant performance and energy benefits across different workloads, and it also has low latency and storage overheads. So that concludes this work. Any questions on this? Yes. Yes.
What makes the differences in performance improvements for the different benchmarks?
So you're asking about the different policies and in different benchmarks. So some of these, okay, let me quickly go into some backup slides to show like what are the characteristics of these benchmarks. Yeah, so this basically shows like what kind of operations are there and the latency of these operations for some of these workloads. And you can see that LLM inference and training have more matrix multiplication operations that have higher latency or more complexity. And some of these other workloads like XOR filter and stencil computations for in Heat 3D and Jacobi are slightly in the medium latency domain. But AES is more bulk bitwise and simple arithmetic operations. So they are low latency operations. So what makes the difference across these workloads is, again, some of these policies that we evaluate, they try to offload it. Again, they make offloading decisions on limited factors, right? So they some try to look at the bandwidth utilization only, and some look at data movement overheads. So in which case we are, they try to exploit more, or let's say a single computation resource for more of these operations. So instead, what we are saying is that we need to look at many factors that affect the computations, and that's making the improvement possible.
Any other questions? Let's thank this video.
Okay, thank you.
Okay. Okay, now so the next one is Onur, Professor Onur Mutlu. Should I introduce? No. Okay, thanks. Do I need to wear this or no? You don't, it's capturing. Okay, okay, good. Okay, I think I get the pleasure of giving the closing talk at our workshop. This is the 7th instance of memory-centric computing systems. But before this workshop, we had the tutorials for real PIM, real processing in memory systems. And if you, and they're all online. So is everything okay there? They're all online, basically. You can find the evolution of processing in memory. The first one we had, no, I have this one. The first one we had was in S+ in 2023 in HPCA. So it's good to see the community growing, and we have a lot more work in this area right now. If you go to conference like ISCA, for example, we have 3-4 sessions on processing in near memory. I'd like to give you an overview of my perspective of this, because I think this is something that we should be doing. We should become much more memory-centric in our approaches. And if you were actually at the talk that I gave at Next Excel in the afternoon, it's going to be very similar. But feel free, I may cover different things depending on the audience. Okay, this is a summary of what I intend to cover. Basically, today, computing has a huge memory problem, and huge is an understatement. People have written papers saying that computing is an energy problem. They're correct. And we're wasting a lot of energy in how we do computation. But most of that energy is wasted because of memory, because we're accessing memory, we're moving data, and that's the major cause of the energy that we have in our computing systems. I'm going to put some numbers over there. But it's not only about energy, it's really about performance. Memory is responsible for most of the performance waste or bottlenecks. It's responsible for a lot of the robustness problems. Like if you send the computing systems out into the space, memory is the first one to really fail. That's why you protect it heavily, and you send
one of the oldest possible technologies in terms of memory out into space. And there are lots of things that can fail in memory, basically. So robustness problems. We're going to talk about non-space problems also. Monetary cost, memory is responsible for a lot of that, and people may be feeling that more and more right now because memory costs are increasing, right? Memory prices are increasing. I think that's a good thing, frankly, because I think this is showing that memory is getting its own place separate from the processor. So far, processor costs have been too high, in my view, because we're very processor-centric, right? If we become more memory-centric, memory will do everything, including computation, and its cost is supposed to increase. Yes, you need to power it more. Yes, you need to cool it more, but that's the price that you pay for being memory-centric, because you're going to gain a lot of advantages out of that also. And also hardware real estate. Most of the hardware that we build today is really memory, and who knows what else. So this problem is becoming worse with more data-intensive workloads, and essentially all workloads we have are becoming more data-intensive. And I think certainly we can do business as usual, which is really designing the systems we design them today, building processor-centric system, keep moving the data far away from where it's ingested, where it's stored, and optimize the system as much as possible. People are doing that, and people are making a lot of money out of that, no question about that. That's business as usual, basically, right? But maybe there's a much better business that can happen if we can actually move to a more memory-centric design, where memory autonomously manages itself to solve some of the technology scaling problems we have, and also memory performs computation to solve some of the application and system level scaling problems that we have. I'm going to talk about both of these, basically. We're going to look at the technology level issues where memory is not scaling very well, but if you actually enable memory controllers to become more intelligent and enable memory to manage itself, you can design a much more capable system. And this requires memory to actually do computation also. And if you can actually use the computation capabilities that you integrate into memory to design better applications and better systems as well. So these are the two things that I'm going to focus on. We're going to go into a bit more detail. Okay, so let's jump into it. Today, computing is bottlenecked by data. Important workloads, AI, for example, that everybody is hyped out about, genomics, HPC, a lot of things are bottlenecked by data in the end. These require rapid and efficient processing of large amounts of data. Data is increasing on top of this. In fact, it's exploding in some domains. That's what also enabled AI, right? The availability of huge amounts of training data plus the availability of reasonably fast compute. And we want to do more sophisticated analyses on more data, essentially. So you've probably seen a version of this graph at some point. Essentially, this shows that memory model requirements of recent transformer-based models have been increasing exponentially. Compute requirements are also increasing exponentially. Essentially, in the last 4 years or so, in the last few years or so, there has been 4 orders of magnitude increase in memory requirements in these models. And clearly, people are pushing the boundaries of these models. It is good to push the boundaries, but are these models being executed on efficient hardware? That's probably a no. And this picture I borrow from Cerebras Systems. These guys are building wafer scale systems, this big chips, and they're building it for a good reason. They want to put a lot of computation in a single chip so that they don't move the data out, and they want to put a lot of memory in a single chip, and they show good results according to them. I didn't test their chips, so I don't watch for them. But I think the good news is they're exploring different architectures. The downside is it's still a processor-centric approach, even though they try to put everything in one chip. They're not doing really, they're still doing data movements between SRAM and compute units. And who knows what happens when you go out. Also this wafer scale chip is very hard to build with huge amounts of memory, like terabytes and terabytes. They don't have terabytes of SRAM. So it's good that people are exploring different things, but we should be exploring even more aggressive things, as we will discuss. So that was AI. There's also other applications that are important, like genomics, databases. We will talk about some of these. This is an area where genomic data is essentially exploding. We have this other workshop that's concurrent here, architectures for health. And there's a lot of discussion that's happening on how do we accelerate genomics, for example. These are very synergistic workshops, I would say. Okay, so the problem is data is exploding, but we're still moving data a lot. Data access is a major performance energy bottleneck. And when we get the data, we ingest it through sensors, and then we put it into storage, and then we put it into memory, and then we put it into caches, and then we put it into registers, And eventually, the data can be processed from the registers by a compute unit. Essentially, we move the data a lot back and forth as we process it. This causes a lot of energy waste because of data movement, and that's costly. It goes through costly interconnects, costly structures. This also causes a lot of performance loss because data movement takes time, essentially. I put this in parentheses, performance loss, because we realize the performance loss due to data movement a whole lot. Because we understand that bottleneck, and we actually try to build systems that try to hide the latency or reduce the latency of data movement from a processor-centric perspective. For example, processors have many levels of caching, many levels of multi-threading, both software and hardware, many types of prefetchers, again, hardware and software, many levels of out-of-order execution, again, hardware and software. So we complicate our systems a lot to overcome the data movement as much as possible. Unfortunately, this is not a good solution to the problem, because when these mechanisms that I mentioned work, they work okay, but when they don't work, and most of the time they don't work fully, you're actually increasing the energy that you consume because you've added a lot of hardware that you need to go through to access memory. For example, we have some work on how to make sure you don't access the caches so that you can get to the data in memory, right? If you're going to miss the cache anyway, you don't want to access the cache hierarchy, right? And this got the best paper award at Micro, for example. So there could be ways of not using the caches if the caches are useless. And most of the caches are useless, actually. If you take a snapshot of the caches in a system today, more than 85% of the data over there is useless. In fact, it's dead on arrival. It arrives, you use it in the processor, but you're not going to reuse it. Okay, it's good to think about this, basically. We're building these systems that are extremely complicated, extremely good, but we're in this vicious cycle where we keep wasting energy while not getting necessarily high performance in many applications. Okay, so basically the basic problem is we're very processor-centric. Everything we design assumes that the data needs to go to a central unit somewhere to be processed, and this comes at great system cost. Now I'm going to review some of the system cost that we have. This is a picture that I drew in 2008 when I was an assistant professor writing an NSF proposal, which got funded by NSF, which is good. I hope people get their NSF proposals funded still. I hope we'll get over that hump also, so that science gets valued in the world and in this country. Well, not in this country, in the country that I'm from, let's say. But basically, this picture shows that you have a bunch of cores, processing units, red things over there. Today, they're more heterogeneous. That was also a part of our proposal. If you look at this, that's not the biggest part of the hardware cost. The hardware cost is really in structures that store and move data, caches, interconnects, other caches, other interconnects, memory controllers, main memory, other interconnects, and storage. So if you do the calculation, more than 95% of a single node today consists of structures that move and store data. It's good to think about this a little bit because we're designing these systems. They're very imbalanced if you think about it. And the question is that hardware really being useful? So I'd like to take the picture of the viewpoint of someone, let's say, who doesn't have a lot of baggage. Let's say they don't buy into the processor-centric paradigm. And it's a good example is a kid, a 10-year-old kid. Pick any random 10-year-old kid, give them the right context, give them this picture, tell them you're dedicating more than 95% of your resources on X. Is that your bottleneck, or should that be your bottleneck? And I'm guessing that that kid will say that should not be your bottleneck because you're dedicating almost all your resources. Unfortunately, that is still our bottleneck. So maybe we should be rethinking our systems like these kids who don't have a lot of baggage. Okay, that was hardware real estate. Let's take a look at performance. This is data from Google from ISCA 2015, where they analyzed microarchitecturally essentially all of their data center workloads execute on top cutting-edge processors in their data center. And they show that most of the time, the processor is waiting for data. These reds are essentially mostly the time spent waiting for data. The green part is what the processor is designed to be doing, when it's just finishing instructions. So on these workloads, and essentially many workloads, as you can see over here, the processor is doing what's supposed to be doing only 10 to 20% of the time. Again, take the hat of this 10-year-old kid. give them this picture, and say, I'm designing this processor. The sole performance task of this processor, the design point of this processor, is to finish instructions as fast as possible. It's doing what it's supposed to do only 10% of the time. Is this a good design? The kid would be honest with you and they would say, go design something else. That's what we should be doing, and that's what this talk is about. We should be really designing something else. Okay, so that was performance. Let's take a look at energy. Energy is much worse, basically. The kids are going to go crazy with the energy numbers. This is data from Bill Daly, a little bit outdated, but the relatives remain. Essentially, a complicated arithmetic operation costs 20 picojoules. A DRAM, a memory read and write, costs 16 nanojoules. That's 800x difference. Okay, things have improved a little bit. If you actually optimize things, a memory access consumes 150 to 200x more energy than a complicated arithmetic operation. But less than that, going less than that is very difficult. Then the question becomes, do we really want to move data from memory to the processor essentially to do some energy simple operation? Of course, it's not dogma. You can optimize this. And it's an optimization problem in the end. The real question is, when do you want to move data from memory to the processor such that you can amortize the energy differential, energy cost of moving data? And you can do these calculations. There are people who did these calculations. Wenmei Hu has a very nice, Professor Wenmei Hu from Illinois, who's at NVIDIA right now, has a very nice talk and slide that essentially show that you need to reuse the data hundreds, thousands of times to actually overcome this energy differential. And most applications today that they don't have that levels of reuse. And clearly there's been a lot of work over the history of computation to exploit locality. Compilers, for example, or humans, let's say, they try to extract locality so that caches work better and better, but thousands of times of data use, even hundreds, even tens in some applications is very difficult to get. Okay. And today we want to actually make computation even cheaper. We don't want expensive arithmetic operations. People are seeing that in machine learning, of course. We want to make the additions less complicated, data types less complicated, low bit width operations. If you look at a 32-bit integer addition and compare it to DRAM access, the differential becomes 6400x. And if you reduce the bit width of the computation to 4 bits, 2 bits, 1 bit, ideally, I think going forward, because we don't want to waste energy, right? That differential increases. And we're not even talking about storage yet. If you actually add storage over here, multiply that 6400x by at least another 10x. So 64,000x, let's assume that number. It's actually larger. And give that number to a kid. And say, I have this energy differential, and I want to save energy, because energy is important for me. But I'm moving data. The kid will go crazy, and they will tell you, what are you doing? Maybe do something else, right? Okay, so we would like to do something else, basically. But let me give you some system-level results as to the effects of these energy numbers and performance numbers. These are studies that we did with Google. This is one study that we did during my last sabbatical when I was at Google, along with my PhD student who was an intern over there, together with a lot of Google folks, as you can see. Here we analyzed the workloads that they had in their mobile systems, like Google Pixel phone, Google Chrome. Some workloads include YouTube, video encoding and decoding, TensorFlow inference at that time, small models, relatively small models, because we were talking about 2016, 17 at the time. And we wanted to look at the energy and performance impact of data movement on the systems that are designed on real workloads, on average use cases. These are not the worst case use cases, on average. And I think we underestimated some of that because average was maybe underestimated. But in the end, if you look at this, we found out that more than 60% of the total system energy is spent on moving data from the memory to the processor and back and forth. That's a big number, actually, if you think about it. We're not even considering storage, right? We're considering memory resident workloads. In real systems, you actually go into the storage also, and then you waste even more energy. Okay, so we recently repeated the study with accelerators like HTPU, where you have a systolic array-based accelerator to accelerate machine learning models. And we used Google's proprietary machine learning models that are executed on Pixel phones. And we found out that in large machine learning models, this is pre-LLMs, pre-transformers, in large machine learning models, more than 90% of the total system energy is spent on memory. And I'll give you one example. We're going to get back to this at some point later when we talk about processing near memory. But you can see that LSTMs and transducers, most of the energy in the baseline is really spent on the off-chip interconnect and DRAM. And if you do processing near memory, you reduce it significantly. Okay, we're going to get to that. So basically, we have a fundamental problem. We're moving data a lot because processing is performed far away from the data. And we need a paradigm shift to change this. We need to enable computation mechanisms with minimal data movement. We want to compute where it makes sense. And there are many places where computation makes sense, as I will show you in the next slide. We want to make computing architectures much more data-centric. And this is where computation can be done. Today, we're restricting ourselves to a very small fraction of this expensive chiplet-based system. Most of the system cannot do computation, even though it's called a processor chip, computing chip, right? Most of it is really memory. And that memory is there to serve the functional units, right? That memory is not capable of computation. And then you go out, most of your data is really stored in DRAM, that's your working memory, main memory. It cannot do computation. And then there's a huge storage that you have. It's usually darkness. Even this picture shows that how processor-centric we are, right? Memory is dark, processor is the king, let's say, right? So we want to do computation there, and we want to do computation inside the sensors as we ingest data. And I'm missing probably a lot of other components here, network interface controllers, etc. Basically, we want to do computation everywhere. We don't want to eliminate the computation that we do today. There are cases where actually executing something on a very high power processor makes sense, as you will see later on, but we want to augment everything. So, and we are able to actually do this because we are very good at designing accelerators today. On the compute-centric domain, we have so many accelerators today, right? We just want to build accelerators on the memory side as well. So this accelerator is sitting on the right side of the memory bus, no pun intended. There are multiple rights over here. And that accelerator has access to a very large amount of memory at high bandwidth and low latency and low energy, as opposed to all of the other accelerators that's sitting on the wrong side of the memory bus. Okay, so this is easier said than done because this requires you to think differently. If you can do computation in the memory, and we're going to focus a lot in memory and a little bit on storage, very little though. Now you need to be able to query memory, ask the question, memory, can you execute this function or this instruction or this application for me? And the memory says yes and returns the result. This requires you to implement computation mechanisms inside the memory and storage devices. We're going to talk about different ways of doing that. This requires changing the design of the processor and the memory controllers, and maybe rethinking the design of the processors. If you actually have computation on the memory side, do you really need very powerful processors? And I will show you that you don't necessarily. Like many levels of caching goes away, mostly. You still need some caching, but you don't need like this N levels of caching, which is really common today. How do you design the software and hardware interfaces to enable this sort of computation? How do you design the system software, compilers, and languages such that this is easier for the masses? How do you rethink your algorithms? Because now the computation capability on the memory side changes how you do computation. That's going to be important. And my favorite over here is the theoretical foundations of computing. And I don't see many people working on it. I encourage people to work on it whenever I talk to theoreticians. Hopefully they will be doing some impactful work in this direction also. Basically, the problem is the way we quantify algorithmic complexity today is by counting operations. We care only about the order of number of operations, right? That's big O notation, big data notation. We don't have a data-centric or memory-centric theory of computing. What I said so far shows that maybe that doesn't matter as much as we make it out to be. So we need to really develop a more data-centric theory of computation going into the future. And I think this is going to be impactful research for the theoretician who does it. Anyway, we need to revisit the entire stack in the end. I'm going to show you some examples of this soon. But I should also say that this is not a new idea. There are smart people who walk this earth, and they basically said, we want to do processing near memory. And this is one of the papers in 1960s that proposes putting logic near memory. This is Harold Stone paper from 1970. So there have been works in this area over decades. They have not been commercialized as things are being commercialized today. I believe there should be more commercialization. Why do we revisit this today? Basically, today we have nowhere to escape, I think. In the 1960s, 70s, 80s, 90s, 2000s, even 2010s, we didn't have as much of a push from the applications and systems. Today, we have a huge demand from applications and systems. So applications are squeezing us to do something else. I've shown you a lot of results. And today, we have new metrics that we didn't care much about, like sustainability. Even energy was not as important for most of the, let's say, evolution of computing, as important. So we need mechanisms that improve all metrics at the same time. We don't want to trade off between, oh, I get this much performance, but I expend this much energy. We should be thinking, I get this much performance and I reduce energy at the same time. And this sort of techniques happen if you reduce data movement, basically. So we need to improve all metrics, including reducing hardware costs. And stripping the processor to be simple is going to be an important one for sustainability, in my opinion. But also at the technology level, device level, memory technology scaling has gone well for many decades. But today we're having a lot of difficulties, at least on the DRAM side. For example, we have issues like row hammers, scaling issues that require intelligence or computation capability inside the memory controllers or DRAM chip. And people are actually adding this to the DRAM chips today, memory controllers today. I'm going to talk about that first. This is essentially computation memory. People are already doing this for memory technology scaling reasons. And if you actually add computation to memory so that you can scale memory better into the future, why not add more? Right? Why not use that computation for something else, which is application acceleration? So, and also there's emerging technologies that we're thinking about that can enable new functions in memory. So today, I think we have a lot of opportunity and a lot of need. Let me start with the technology scaling part, because I think this is at the low level. We're going to jump up to the high level later on, and we're going to see how we're squeezed, hopefully. So we have built a lot of infrastructure. These are FPGA-based infrastructures to understand scaling problems with memory technologies. This is DRAM infrastructure. We also have worked on flash infrastructures, but I'm not going to talk about flash today. Maybe a little bit, very briefly at the end. So this infrastructure, essentially you have an FPGA, you have a soft memory controller, and this memory controller can violate timing parameters, we can also test different temperatures, we can change the voltage, etc., to understand what's going on in memory. Now, we did a lot of studies in memory. This is our HBM testing infrastructure, and this is our lab at ETH, where we have 120 plus setups. Ismail knows us really well over here because he has worked on those setups. And we want to expand this more so that we can do better testing and better understanding of what goes on in memory. If you visit us, we'd be happy to show you. We can play with it a little bit, maybe. And this is a paper that we wrote that appears at this ICS proceedings for the Remulator and DRAM vendor workshop, which happened this morning. If you're interested in learning more about this infrastructure, you can read this short paper. So we have many versions of these infrastructures. This is the version at Carnegie Mellon, and this was the original version at the top, at the bottom left, bottom right over here. That was our first infrastructure. We open source these infrastructures, so anyone who may want to use them, we're happy to help. It's DRAM vendor is the latest version, and we just ran the tutorial, the third version of this tutorial downstairs. So why did we build this infrastructure? We wanted to understand technology scaling issues, and one of the issues that we did a lot of analysis on is row hammer. How many people know about row hammer here? Okay, not everyone. So I'm going to go through this relatively quickly. I can give longer talks about this, but I'm not going to do that. Basically, this is a real scaling problem that affects all DRAM chips and all computing systems. Essentially, by keeping on accessing a memory row many times, you induce bit flips in real memory. This is silent data corruption. This should not be happening. Perfectly legally, you can do these, induce these bit flips. And I'm going to show you an example. Basically, you have two-dimensional arrays of cells and DRAM and many rows. Whenever you activate one row, you can access data after activation. And then you can close that row so that you can access something else. But if you keep repeatedly accessing your row, intentionally or unintentionally, enough times before the cells get refreshed, you can induce bit flips in some vulnerable cells that belong to some other adjacent rows. This happens because cells are too small and too close to each other. As a result, accessing one row causes electrical interference in adjacent rows. And every time you access the row, you're depleting the charge in some vulnerable adjacent cells. And if you do these accesses enough times, you can corrupt the cell such that you cannot read the correct value that you stored there again. Now, those rows may belong to some other application. They may belong to the operating system. They may belong to your own application. You don't want data corruption regardless. Okay, that's the idea. So we actually did a lot of studies, showed that all DRAM chips are vulnerable. And the issue is, as the cells become smaller and closer to each other, which is really necessary for capacity, which has enabled essentially a lot of what we have today in AI, for example, this problem becomes worse. We have shown over the course of 10 years, the number of activations to induce a bit flip has reduced by more than 100x. So it's easy to do these, generate these bit flips. This is our original Rohammer paper. And we basically said that this is a security problem in addition to being a safety problem, robustness problem. And these good folks from Google Project Zero were the first ones to design an attack using these bit flips. So they replicate our results and they design attacks. I'm not going to talk about these, but there's an exciting line of research in the security community that builds on Rohammer and these bit flips, where many folks have shown different and interesting and creative ways of taking over a system or reading data that you don't have access to, corrupting important data, like rendering machine learning inference useless because you may get a bit flip in the wrong weight, and you can induce that maliciously or non-maliciously, erroneously, and then you can get a safety problem, for example. You can steal secret data like cryptography keys or ML model parameters. Basically, the fact that you can induce a bit flip in a particular location in DRAM very predictably causes all of these security problems. And you can imagine other problems like safety, etc. So you can read more about Rohammer. We've written a lot of papers on this topic, including some retrospectives. But this is not the only problem. Basically, there are a bunch of scaling issues in DRAM that are scary, I think, at the same time. This is something we discovered about 10 years after Rohammer. It's called row press. I'll give you the basic idea very quickly because it's relatively easy to, I think, understand. In Rohammer, the goal is to activate a row or open and close or access a row as frequently as possible. In row press, the goal is not like that. Basically, you open the row, activate the row, you keep it open for some time, maybe access different cache blocks in the row in DRAM, and then close it at some point. And the fact that you keep the row open, activated for some time, induces a different kind of read disturbance, electrical interference, than Rohammer that makes things even worse. It becomes easier to induce these bit flips. You don't need as many activations, which means that if you want to solve this problem, you need to have a different solution, or you need to adapt the existing solutions. So this is another example of read disturbance. It's also very common, just like Rohammer. It's not dependent on manufacturer, for example. It's not dependent on a particular design. It's really a fundamental technology scaling problem that you have in the way we design DRAM today. So you can see that this, I guess, Samsung, Micron, or Samsung, Hynix, and Micron, they're all vulnerable in a very similar way, as you can see over here. Okay, so how do we solve this problem? I can keep going on and giving you a lot of these read disturbance issues. The question is, why am I telling you this? Because all of these issues, to solve properly, require some computation capability, either inside the DRAM chips or close to the DRAM chips. So you need to do processing near memory, basically, to solve this. Essentially, you need to design intelligent controllers. Of course, you may say, okay, I want a different type of DRAM. And people are investigating that. Today, they're not available. They will be available at some point down the road. The question is, of course, are they going to be vulnerable to similar issues or some different issues? I personally believe that any memory technology, if it's scaled to very small sizes, will have effects like this. So you cannot escape from read disturbance. It exists in SRAM, it exists in hard disk, it exists badly in flash, and you have intelligent controllers to manage all of those memories. DRAM is kind of special. We've never had intelligent controllers, but we need intelligent controllers right now, as I will see. As I will show you. So we've written papers on this intelligent controllers, designing memory together with the system. You can read about those. And more recently, we've written a paper at IMW International Memory Workshop, which Ismail is a co-author of, that gives the name of this talk, basically. So the good news is, there have been a lot of intelligent controllers designed in academia, and industry has finally picked it up. This is a paper from SK Hynix, a major DRAM manufacturer. About 10 years after our original paper, they basically wrote a paper at ISSCC, the major circuits conference, and they described their solution to Rohammer. And essentially, it's an intelligent memory controller that's based on many of the ideas that were developed previously. And the ideas, I'll give you the idea, it's relatively easy to understand. Next to each row in DRAM, you have a counter. And this counter is incremented whenever you activate one row, that row. And if you keep repeatedly activating the counter gets incremented. At some point, if the counter becomes greater than some threshold, the DRAM chip internally takes some mitigating action, like refreshing adjacent rows. So it's essentially computation inside memory. If you think about it, it's like memory tagging. Every row has a tag, a counter, and that tag gets manipulated internally by the DRAM, and eventually you take some mitigating action based on the tag. You can imagine adding a lot of interesting security mechanisms using those memory tags, for example, per row. I like this, actually. It's good. It's good to think about this way. Now, the good news is this is a solution in the right direction, I think. People are putting intelligent controllers inside the DRAM chips. And this has become standardized in DDR5. Going forward in DDR6 and other memories, it's going to be there, some sort of solution, hopefully a better version of it, because this has some shortcomings also, as I will tell you very briefly. But the solution direction is good, in my opinion. So the question is, are solutions really good? You don't need a 10-year-old kid to tell you that this is a bad solution, the problem it's purporting to solve. So we need to re-examine or examine the solutions that are proposed. And we actually examined it to be able to, for example, safely configure this solution. You need to be very careful. And also, when you design a solution like an intelligent controller, for example, if you want to increment the counters, it takes time. And the way JEDEC designed these intelligent controllers required increasing some timing parameters, which made memory performance worse. So we have some solutions that also. So if you actually want to design a good solution, you need to have even more intelligence in the controller. That's my point. You need to have even more computation capability in the controller. And I think this is going to happen over and over more over the next number of years. I should also say that this sort of solution is not something DRAM manufacturers wanted to do. We've argued that they needed to do, not necessarily in the DRAM chip, but in the memory controller also potentially, or both. We will talk about that also, for many years. And eventually they had to do it because it was difficult for them to solve the problem in some other way. It's very difficult to have software solutions. So they did it. So if you went to a DRAM manufacturer 10 years ago and asked them to put computation capability inside the DRAM chip for this purpose, they would kick you out of the room politely. But now they're doing it, which is good, basically. This is a good opportunity for doing more computation in DRAM also. So the question is always, can we do better? Before going into more things, I should say that we need to fix some things in the memory processor interface. We have a huge imbalance today because we're very processor-centric. Processor dominates the interface, right? Processor and memory cannot do anything by itself. So DRAM chip cannot even maintain itself, basically. So it has to be told by the memory controller, for example, my computer is refreshing its DRAM, but the memory is not initiating those refreshes. The processor chip is telling the memory, refresh yourself, refresh yourself, refresh yourself, refresh yourself, every 7.8 microseconds. At high temperature, it's even worse. I think this needs to change because if DRAM chip cannot do things on its own, we cannot easily put a lot of things inside the DRAM, and we are actually limiting innovation. So DRAM manufacturers may want to do some changes inside DRAM for computation or for roll hammer protection or for refresh. But to be able to enable that change, today's systems require memory controllers to change and also the interface to change. And this is a horrible process because imagine convincing 400 companies in JEDEC to change that interface. It's a very political process. It's very bad for technical innovation and advancement, basically. So to fix this problem, I think we also need a more memory-centric interface. And the idea we have in this work is very simple. The DRAM chip has some autonomy, relatively small. And the idea is to enable the DRAM chip to say no. If the memory controller wants to activate one region, for example, access one region, the DRAM chip is doing something inside that region. The DRAM chip says, sorry, memory controller, try again later. And you can design an interface that's quite predictable to make sure that this doesn't cause denial of service, etc. So it's possible to design a nice interface that enables high performance also. So basically, we need better partitioning of the work between DRAM chip and the memory controller so that we can enable innovation. And I think this is also very useful for processing in memory. You can read our paper to see some optimizations that we enable with this autonomous DRAM management by itself. And this is a paper if you're interested. I think there needs to be more work in this area that makes the interface between processor and memory more flexible. This is going to be important for enabling in-memory computation even more. So if you want to learn more about this, you can look at my Micro 2025 keynote talk. I cover some other issues over here that I'm not going to cover in this talk. So the interesting thing is there's more to come. DRAM is a technology that is essentially our dominant memory technology right today. And there's still a whole lot we are learning about DRAM today. That's been around for 60 years. But we've scaled it to such smaller levels that has enabled so much capacity. We're learning new things. And I think I'll give you some other examples over here. Aging, for example. People are talking about going to space, living there, building data centers. All good. But we need to really understand what happens to hardware when it ages, when it's exposed to radiation. I'm not talking about hardware that was designed like 30 years ago. That's what people do when they go to space today. They take the old hardware and they make it radiation immune, etc. We really want cutting edge hardware if you want to live in space. How do we actually enable cutting edge hardware to work in space? I think there's more work to do in this area. We also discover new issues like variable read disturbance. Here, there's a lot of quantum-like effects that start appearing when you reduce the size of the circuits to be so small. And one example is variable read disturbance. The idea that some cells become, the vulnerability of a cell to a row hammer, for example, changes randomly and unpredictably. So if you really want to protect when bit flip happens, you really need an intelligent controller that adapts to these changes. And that requires the controller to be even more intelligent than what is designed today, more flexible, and discovering issues like this online. So we always argue for basically more patchable memory controllers that can do online profiling, ideally programmable memory controllers. And I'm happy to talk about that separately. We have also discovered new issues. This is Ismail's work from last micro that are a little bit more scary than row hammer in the sense that they affect thousands of rows. So column disturb is the fact that when you activate a row, you're really causing perturbation of thousands of bit lines that those cells are connected to. These are the blue cells, basically. This is a picture. Essentially, millions of cells can be affected that belong to like thousands of rows. Those are the blue cells. So essentially, you disturb millions of cells, thousands of rows. This is not as big of a problem as row hammer today, but the technology scaling results from our real chips in our infrastructure show that this is going to become a much bigger problem over time. So you need solutions to prevent this from becoming a huge problem like row hammer. The solutions that you need to design to prevent column disturb are actually very different from how you solve row hammer. We have a paper at ISCA called Column Keeper that solves this problem. But again, we need to develop more solutions. So Ismail has done work to show that. Did you talk about this? Okay, punt hammer. I'm not going to talk about that. So you need to actually investigate if you're doing processing using memory, how do you actually make sure that row hammer doesn't hurt your results, right? And there's more recent work that Daichi presented at ISCA, where we showed that data that is not involved in computation actually affects your computation results. So you need to actually be careful when technology scales to smaller node sizes. And I will not talk about this, but this is also a fascinating result where we showed that data that you've written previously to DRAM, not the last write that you do, but the previous write that you've done to a DRAM cell affects the read disturbance vulnerability and also computation capability of DRAM chips. This is fascinating. That's why we call it deja vu. So there's a memory effect that stays in memory. So these are things that are really interesting, and you can see that these are all discovered in 2025, 2026. And this is going to get worse. I think there will be more things. And if you're actually a designer who is designing a memory chip that you want to make robust, you really need a controller that can discover these issues in the field. So there needs to be even more intelligence inside the memory controller, in my opinion, because we don't want these issues to be discovered, let alone exploited by someone else in the field, right? You may say, okay, this is DRAM, this is old stuff, let's talk about new stuff. Unfortunately, I have bad news for you. There are two things here. One is DRAM's future is always DRAM. This is a joke, of course, but not fully a joke also. Basically, DRAM is very strong today, and people are going to push the boundaries of DRAM. They're going to change it. There will be different 3D type of DRAM technologies that are coming up. DRAM is going to evolve. Other technologies are very important to examine, I think. They're not ready yet, unfortunately. And we have looked at, for example, myself, phase change memory, STT-MRAM, etc. And whenever these memory technologies scale to smaller node sizes, their cells become small, their cells become close to each other, they will have similar issues. So there are similar write disturbance, read disturbance issues on emerging technologies. And sometimes these memories actually are even worse. They have wear out problems like flash, right? Whenever you write to a cell, you hurt the cell a little bit, and eventually you may not be able to read from the cell. Right? So you need to handle the wear out problems, and that requires an intelligent controller from the get-go. So in my opinion, for scaling the technology to smaller dimensions, we definitely need intelligent controllers, and we cannot escape from that, regardless of the technology. That's why we keep building our lab so that we can discover some of these issues earlier than potential attackers can discover them, let's say. Okay, I'm going to go over some of these things. There's a vibrant research going on. Even in the small subsection of read disturbance, you can see some papers. These are not our papers, but many people, for example, Unix Security had 7 papers on row hammer in 2025. More recently, SNP had a bunch of papers on how to induce these bit flips in GPUs and take over a GPU, or render machine learning inference useless on a GPU. And I think this is good that people are doing this sort of security research. It's a bit fascinating that the distance between the original Rowhammer paper, 2014, and these works, the first GPU paper, is 12 years. This shows that, like, if I were someone who wanted to take over other people's systems, and if I had a lot of money, I could probably do it in less than 12 years. It's good to think about that. Okay, and there are a bunch of papers at DRAMSec, for example. I will mention one of the things over here. This is at ISCA. Again, there were a bunch of papers at ISCA, which is the major architecture conference last week. And industry is also developing these intelligent memory controllers. And not just inside DRAM, but this is a paper from Microsoft in their Cobalt CPU. They basically didn't trust the manufacturer's solutions. They said, we're going to implement our own Rowhammer solution inside the memory controller of the Cobalt CPU. And this is actually an intelligent memory controller that has a combination of mechanisms. It's a nice paper to read. So these large companies are also building their own memory controllers, which is a good thing, I think. Okay, if you're interested in more of these, we have this DRAM and emulator workshop, which the third of which we had this morning. We'd be happy to get more contributions from the community. If you're working in these areas, we'd be happy to support you. If you want to build a lab like ours, we'd be happy to support you also. Okay, let me jump into application acceleration. So far, I've talked about adding computation capability inside DRAM so that we can scale the memory technology into the future nicely. What about accelerating applications? I'm going to talk about two things, but I'm going to give you a choice right now because we don't have a lot of time. What time are we supposed to end? 5:30? Okay. Then I'm definitely going to give you a choice. Basically, I think there are two ways of doing processing in memory. I call everything processing in memory because old people in 1960s called it logic in memory. And I think we should not mess up the terminology. A lot of people actually have very different terminologies for this. I think we should have a clean terminology. Let's call it logic in memory, processing in memory. I think there are two fundamental types only. There's also the location and technology. I'm not going to talk about location and technology. In terms of type of computation, there's processing near memory and processing using memory. You could call it logic near memory, logic using memory. That's also fine. You can replace processing with logic, I think. So what's the difference? Logic, memory. Today, there are two completely different design processes for logic and memory. And sometimes fabrication processes, right? They're complete different fabrication, DRAM, for example, and CMOS logic. Processing near memory says, design logic as you design today, design memory as you design today, but put the logic closer and closer and closer so that the data doesn't move as much. For example, you can put the logic computation capability inside the memory controllers, inside the DRAM chip in a logic layer underneath the DRAM chip. You can put it inside the DRAM chip next to each bank. You can put it in the sense amplifiers. You can put it in next to each cell in subarray, next to each subarray, if you can afford to do those changes. That way you move the data as little as possible. That's processing near memory. It's very similar to how we do things, except you do the integration of logic and memory much better. They're still designed separately though. Processing using memory is fundamentally different. Logic, memory, forget about logic. Assume it doesn't exist. There is this memory, and all memory has some fundamental analog computation capability that enables it to do computation in addition to storage. Essentially use the memory to do computation, discover these functionalities, or identify these functionalities. So clearly this is harder to do because you're not adding logic. What you can do using memory is restricted to the type of memory technology you have and the type of operations it can support. But it could be very powerful because you're really not adding logic. You're not even moving data at this point. You're really using the memory cells in situ to do computation. So in the end, there are trade-offs associated with processing near memory. You can do much more complicated operations because you're adding logic, but you're still moving data a little bit more. Processing using memory, maybe you're limited in terms of types of operations, but you have massive parallelism. Every single cell can be computing, as I will show you in a little bit. In the end, I think we need to combine both. Processing near memory is easier to make reliable because we know how to make logic reliable. Processing using memory, it's fundamentally analog in nature, although if you actually are using the existing infrastructure in DRAM, for example, that analog computation is a very limited amount of time. It quickly gets amplified using the sense amplifier, which is an analog to digital converter in the end. So there are a lot of interesting questions here. And also the 1960s papers that I showed you are processing near memory papers. Processing using memory is a relatively recent development, like people in memristors and DRAM, they're all in 2010s, for example, although it has similarities to analog computation clearly. Okay, now I will ask you the question, which one do you want to cover? Since we don't have a lot of time, we can cover one more than the other. So I'm going to take a vote. Who wants?
I think we did much more in the workshop.
Okay. Yeah, you were at the workshop though. Okay, I'm going to still take a vote. Who wants processing near memory? Okay, who wants processing using memory? Okay, we're going to do near because I believe Ismail covered a lot of using memory earlier, so that's good. Okay, I'm going to cover this a little bit more then. Maybe I'll go into a little bit more detail also. So I'm going to not talk about processing using memory. Does that sound good? Since we already covered a lot in this tutorial. So essentially, processing near memory says you put logic near memory. And there are many different ways of doing that. For example, if you have 3D stacking, which I'm going to talk a little bit more detail, you have a logic layer, and you can put computation mechanisms, units in the logic layer. You can put it in the sense amplifiers. Micron had this automata processing, which was relatively forward-looking. Essentially, you can do deterministic finite automata computation in the sense amplifiers. You can put it inside the DRAM chip, like these bottom four, Alibaba, Samsung, SK Hynix, UpMem did. Essentially, Samsung and SK Hynix added multiply and accumulate units next to each bank so that you can accelerate matrix multiplication, mainly designed for accelerating machine learning workloads. Alibaba added some, it's a 3D stacking mechanism, their HBM chip. They actually added some computation units to improve recommendation inference. UpMem added a much more general purpose processor where next to each bank, you have a multi-threaded processor, which is actually programmed using some C version of C. They have their own compiler, etc. But it's essentially a full processor that can execute a lot of things. They were not very powerful in terms of multiplication. They didn't want to add multiplication units, so you cannot do multiplication beyond 8-bit integers. So they were a bit crippled in the sense that they were not designed for machine learning. Their goal was not machine learning. That's one of the reasons they actually were bought, I think. They were trying to move to machine learning, but it didn't work out. But it's a very good prototype in the sense that you could buy it, and it was commercially available. We worked with them a lot, and we actually wrote a lot of papers understanding the capabilities and downsides of these UpMem systems. I'm happy to talk about that. I don't have slides in this, at least in this part, but there's a lot of interesting things over here. The most important thing is it's real. You could buy it, and if people are interested in doing studies, we still have 3 UpMem machines. I don't think you can get them anymore, but we're happy to provide. They're getting a bit older right now. Okay, there are also other things like this you can do. This is Samsung and Meta. You have a bunch of DRAM chips on this board, and you have an FPGA. They call buffer. This is called AXTIM. And they designed this for, again, similar to Alibaba, to improve recommendation inference. So for recommendation systems. And the idea is not to move the data far away into the processor. Again, and you can also customize the computation in that reconfigurable logic that you have in the FPGA. So you can see that these are all recent industry prototypes. And there's more actually. There's one work from Anchor, which is a Chinese company that was founded by a Google engineer. And these guys design actually relatively low cost things. But one thing they designed recently is earbuds. And in these earbuds, they do some processing, some machine learning analyses. And they actually incorporated, according to them, again, I didn't use these, but according to them, they incorporated processing using memory, using NOR flash, which is very interesting, I think. So I think it's good to think about these. So these things are happening. I think there's also a recent announcement by Qualcomm, which Ismail can tell you more about because I didn't read the details, but it did look like they were doing processing near memory also with their announcement. Now, is it in the market yet? I don't know. But there's a lot happening in industry right now. Yes?
Where would you put TensorFlow?
TensorFlow. I think TensorFlow is compute-centric. Sorry. I mean, as far as I know, they're designing RISC processors, right? But maybe they do something near their memory controllers that I don't know, right? That's the part I don't know. Sure. But I'm happy to learn, you know? Yes.
Can you buy any of those systems for experimentation?
So, okay, very good. you used to be able to buy UpMem until they were acquired by Qualcomm. If you want experimentation, we can give you access. We worked a lot with UpMem to understand their systems, because actually they came to us because we had a lot of work on processing near memory, in memory, and we created benchmark suites, etc. We're happy to provide access if you're interested, but you cannot buy it anymore. I'm sure you can buy the earbuds from Anchor and they would be happy to supply them. I don't know if you can do experimentation on that system. And I don't know about this Qualcomm's new system, right? But you can design your own DRAM vendor or PyDRAM setup to abuse existing DRAM to do experimentation, like along the lines Ismail presented and I presented in the other workshop. Yes. Yeah, go ahead.
Curiosity question.
Yeah.
Rapidus, Exina, Rebellions,
yeah.
all the things that are coming up,
yeah.
Each of them just has $50, $80, $100 million just because they can. You are not paying attention, or it's just too much to do, or they are doing more of the same in some parts.
You mean why are they not in this picture? That's what you're asking. I think some of them are doing processing near memory, sure. Yeah, CXL based, etc. But I don't want to put everything in this picture also. It's very difficult. So there are many, I think they basically go into experimental chips and startups over here that are not yet commercially available.
That's why I highlighted.
Yeah.
$60 million.
But they don't have products that I can test maybe. Maybe you can buy it. Yeah, I think it's good to, yeah. Yeah. I mean, it's not that Samsung or SK Hynix have products I can test, but they've actually published results with their products. So assuming that we believe them, they have some products or prototypes internally, right? But I don't think some of the other places have published something. And these guys have published in real major venues. Sure. Yes, please.
As my using experience on top,
Okay. I'd like to talk with you more. Are you coming to the dinner today? Yeah. Okay, sure. I think I've learned not to trust the manufacturers. I think they're good people, but sometimes they may not have the right motivation, let's say. Okay. Jokes aside, I think they have built some things, like this is SK Hynix. I think some of the startups that you mentioned are doing similar things to this. We don't know exactly, but SK Hynix publishes papers also where they show that you can offload computation to an FPGA near memory. It's not exactly what we envisioned, but this is a real system that they built to be near memory, more near memory. Samsung also has maybe a little bit less reliable publications. I don't know. You can take a look at it. I'm going to give you several things that we have done. This is one of our early works on processing near memory. And we always believed in 3D stacking, because I think once you can stack things in a 3D manner, you can get the best of memory as well as best of logic, right? That's what we really want to do. Of course, you'll have thermal issues, etc. you cannot get away from. But if you can put very high quality logic next to very high quality memory, then you can customize computation inside the logic, and you can have very high bandwidth, low latency, low energy access to memory. And clearly, there are TSV type of technologies that enable this. There's hybrid bonding. Essentially, the bandwidth you get and the latency you get and the energy you get depends on how thin you can make these wires that go vertically, right? Hybrid bonding gives you a huge advantage. I think going forward, monolithic 3D, where you have vias connecting these layers, gives you even more, but there are fabrication challenges. But let's assume that you have something like good TSVs and you have a good logic layer. That's what we assumed basically when we were starting this 3D stacking work in 2012 or so. And the question we asked was, how do we design an accelerator for an important application? And we picked graph analytics. We should have picked machine learning probably. But again, the results with machine learning are going to be very similar, as I will show you later on. And the idea was to incorporate a lot of cores in the logic layer, massively parallel, you can think of it that way. And these cores have access to memory on top of them. They own the memory on top of them. They're connected to each other in the logic layer with a fast network. And the idea is to push the computation to the core that owns the memory. So if you want to update a graph node, for example, you send the value to the core that actually owns the memory that needs to be updated. That's the idea. So we program these using remote function call-based programming in a way that's very similar to how distributed systems are programmed. We could have done more optimizations, but that's what we did essentially. And you partition the graph across the cores inside logic. Of course, a single 3D stacked memory plus logic chip is not going to accommodate your big graphs. So you really need to build a distributed system of these 3D stacked memory plus logic chips. And that distributed system can scale. Of course, your interconnect becomes really important. Ideally, you want to do the partitioning such that partitioning data movement is local, and also computation shipment is local to the logic layer, a single cube, if you will. You want to minimize getting off chip. And ideally, you want to also minimize movements within this chip, although that's not as bad because this is within a single logic layer. So we do some graph partitioning to maximize locality, etc. But in the end, you have to go off chip at some point, and that's going to be your scalability limiter. So we have in-order cores, simple cores. These are actually quite general purpose. You could execute anything. You could add acceleration mechanisms that later people added. So the key is you have communications via remote function calls, and we have some prefetching mechanisms because you have ample bandwidth to these available to these cores. I can go into more detail, but I'll let you read the paper. This is like also 10 years old, actually 11 years old right now. Basically, we compare this to existing systems at the time, including hybrid memory cube, which is essentially similar to high bandwidth memory, but maybe it was designed with some implementation issues, let's say. Although I do like their interface much better than HBM today. I think we need to have more flexible interfaces like HMC tried to do. Basically, if you look at the systems that we compared to, they're all limited. They all have the processor memory dichotomy, right? And they're all limited by the bandwidth. Here we have 512 in-order cores, which is similar to this system. And they don't look like any of the system because computation memory is integrated together and you have a distributed system of this near memory computing chips. And at the time, 11 years ago, actually the paper was done in 2014-13, that number of years ago, these 512 cores had access to 8 terabytes per second. Today, this is still a high number, but it's a relatively low number because things have improved over the course of 12 years. Today, the number is much higher. Okay, so we redesigned several graph processing algorithms, and we showed that using porting them to our simulator that simulates the system can get you a significant performance improvements, about 14x. And also it reduces energy at the same time. So you can improve performance and reduce energy at the same time, assuming you have these components, right? Which is, in my opinion, today, not that difficult to do. Because today we have HBM3. We're going to have a very nice logic layer soon in HBM4, hopefully. So you essentially will have access to this. You just need to build a system out of it, like envisioned, let's say, some number of years ago. And also later works improved our results. They basically customized some things, reduced the overheads, did better graph partitioning, etc. The numbers actually went up to 100x around, and also 100x energy reduction. So pretty good if you optimize for graph processing. We still optimize for machine learning, perhaps. And this is the paper, if you're interested. And we have a one-page version of it that summarizes the key principles, etc. So you can actually do more. In this work, I like this work. What we did was basically we changed the instruction set architecture to be more set-centric. So if you have the sets as a data type, you can enable many applications. Essentially, you can do set intersection, set union, and these are fundamental data types in your instruction set architecture. You can express your graph algorithms in a set-based manner, and you can also, your hardware can operate in a set-based manner. So this is actually very useful, like bitwise operations that you have in sets. They can be accelerated using processing near memory cheaply, and also processing using memory, like Ismail talked about earlier, also very cheap. So I like this approach. I think we should be doing more of that. And I think machine learning applications are more amenable to set-centric acceleration as well. In this paper, we showed very good results with processing near memory as well as processing using memory. I don't have slides, but you can take a look. I'm going to talk about what we did with Google that I use as part of the motivation. This is, we analyze essentially on Google Edge TPU, the commercial models that Google used to use at the time on Google Pixel phones. These are some of the models. Unfortunately, they're proprietary. They didn't allow us to release their commercial models. Anyway, they're similar to fundamentals are similar to all of these in all of these anyway. What matters is data, of course, right, to train these things. So we try to understand the variation in these models in terms of how much memory they need and how much arithmetic intensity they have. And if you look at these models, there's a huge variation, meaning that a single accelerator that's compute-centric is not going to get you the best result. So for example, LSTMs are very memory intensive, transducers also. Their memory footprints for each layer is huge, and their arithmetic intensity is well below 1, which means that it's better to actually put them near memory. Some of the other layers from CNNs, for example, convolutional neural networks, they have very little memory footprint for given layers, and they have huge arithmetic intensity. So here you really want a compute-centric approach, clearly. And then you can actually do more analyses. And again, there's significant variation in terms of layer characteristics also across different layers. So the idea is, as opposed to designing a single monolithic edge TPU, a single systolic array that's processor-centric, we basically said we should be designing a heterogeneous set of accelerators. Some of them need to be processor-centric because some layers have huge computation requirements, but not that much memory requirements. You can reduce the size of the buffers in this accelerator and make a smaller version of the HTPU for those. But some of them need to be data-centric, meaning that you can put smaller systolic arrays underneath memory layers in the logic layer of a 3D stacked DRAM. And these layers benefit from that sort of computation. And we actually have different data flows for different types of families of layers. You can read the paper for more detail. Then the question becomes, how do you decide what goes where? And then you need a runtime scheduler. It could be static, it could be dynamic. Dynamic is better, of course, as long as you can maintain the overheads low, which decides which layer goes to what type of accelerator. And we use 3 over here, but this could be generalized to more clearly. We use 3 so that we can minimize the cost as much as possible. So basically, you need to identify layer families. You need to do some sort of profiling so that you can decide what goes where. I'm not going to talk about that. But in the end, if you design what we designed, which is not optimal by any means, because we're not actually maximizing the parallelism across accelerators also, we just wanted to have a proof of concept. You can reduce energy consumption by about 3x on average in these models. I believe the potential is even more. It can also improve throughput, and you can also improve latency, as we show in the paper, compared to existing HTPUs, and also existing HTPUs augmented with high bandwidth memory. I don't show over here, but in the end, you reduce the overall area you spend in accelerators. So because you reduce the compute-centric HTPU very significantly, and if you add up the areas that you spend on the 3 accelerators, it's much lower, maybe 30% lower if I remember correctly, than the HTPU that Google used at the time. Of course, this is a weird comparison because we have 3 different accelerators. Complexity we have increased, of course, compared to HTPU, but we gain benefits in terms of energy and performance and overall hardware cost. So I think these principles are quite general in the end. And the principle is identify what kind of accelerator you should use to accelerate computation and ship the piece of computation to the right accelerator. More recently, we studied LLMs, and I think this principle applies over here. This is a paper that we published on last ASPLOS. And the idea is, if you look at large language models, there are some pieces, like fully connected layers, that are extremely compute intensive. Very similar to what I showed you earlier for some of the compute-centric layers. They should be executed on a beefy GPU or TPU with not a huge memory system, because they don't require that much memory capacity. So you can design a customized GPU or TPU for them, and that's what we did over here. That's called this these high performance processing units. And then there are some parts of the fully connected layers still that are not as compute intensive. They're more memory intensive. They don't require huge capacity memory, but they require some more capacity. And they require reasonable computation intensity, but clearly not as much as you need for the compute intensive fully connected layers. So you can use something like UpMem, well, with good multiplication, sorry, maybe HBM-PIM, a better version of it, not the advertised version, with a lot of compute units next to each bank. Because computation, you still require some computation, but you're still dominated by memory. And then there are some other layers like the KV cache, for example, attention layers that require huge amounts of memory, And they don't require as much computation, and they require a lot of memory bandwidth. So you can design a different near memory computing system that can do this over here, assuming that these are your building blocks. Of course, there are different ways of building the system, but this is what we did in this particular work. The principles, I think, remain the same compared to what I just showed you earlier. It's adapted to LLMs. And in the end, you need a mechanism that decides what goes where. And we designed, again, a scheduler that decides what should be executed where. And if you do that, you get significant speed-ups and energy efficiency. These numbers may look low, but this is compared to the best prior LLM decoding system, which is actually a processing in memory system. It's the attack accelerator, attention accelerator, basically. So I think there's more work in this area. If you look at ISCA, for example, I think there are many versions of these 3D stack accelerators. There are some interesting work that combine DRAM and flash in a stacked manner so that you can do this. There's also more work coming up in high bandwidth flash, for example. I think there's a lot of interesting space that's to be explored in this area. But I frankly believe the principles will remain the same. You just need to identify what type of accelerator, hopefully build a good accelerator, and distribute the computation. Okay, we also designed this accelerator, which is actually very interesting. We were a bit aggressive. We wanted to get rid of these highly intensive compute units. And we exploited the CXL interface and its communication primitives. Essentially, we offload computation to many CXL devices that can operate in parallel. Matrix operations are performed in near bank units in these PIM devices, GDDR6 PIM, for example. And all other operations are performed in the processing near memory units that can be more capable and powerful. They can do like random logic operations, etc. And if you design the system and if you actually have communication mechanisms that are nice across the CXL devices, you can get a system that's higher throughput, lower hardware cost, and lower money cost, let's say, compared to existing GPU-based LLM inference systems. And you can read the paper for more detail. You can also build on it because it's fully open sourced if you're interested. So these are some things that I think we should be doing going into the future. We should not take like GPUs as granted, because there's a huge design space that people have not explored. And that design space can be, I think that design space is enabled by processing near memory in the end. These are near memory approaches. I'm not talking about processing using memory yet, but you've seen enough in this workshop on processing using memory. That's also interesting. We're not doing processing using memory in any of these, except for the CISA paper where we did set-centric acceleration on processing using memory, also in addition to near memory. We have a lot of other works that I'm not going to talk about, mobile workloads. I will mention that we had a genomics, architecture for health workshop, and some of the earlier applications that we examined, that we're currently examining, are DNA sequencing, for example. And here you're doing essentially text operations, string matching, approximate string matching. You're not doing complicated multiplications. And these are actually even better fit for processing near memory or processing using memory, because your logic doesn't need to be complicated. Right? So these are actually, I think, nice. You can read the papers. And I think in some of these applications, the data set sizes are huge, that even doing things in memory doesn't make sense. So we have the storage system, and storage system actually stores a whole lot of the genomic data. We don't want to move the data out of the storage also, and we have designed mechanisms, near memory, near storage computation mechanisms that can do filtering some of the simple operations in genomics, such that you don't burden the accelerators or the CPUs. And this results in significant performance and energy improvements. And so in some of the genomic analyses, the data set sizes are huge, like hundreds of terabytes. For example, if I take a sample over here to identify what's going on, essentially I get a sample through a sequencer, and I try to match the huge database of all of the known species. I need to compare to all of those species. And this is a huge database search in the end, an approximate string matching search. And that requires actually huge memories, and it doesn't make sense to bring data into DRAM at that point. And we have designed, this is called the metagenomic analysis, essentially. Metagenomic analysis can be accelerated even better with in-storage processing. And in more recent works, we actually are looking at different algorithms for analyzing genomes. And here we have both processing near memory as well as processing using memory. And I'll let you read that because we don't have time to discuss this. So in the end, I think you can combine both processing using memory and near memory mechanisms to get an overall good system. And clearly machine learning can be accelerated also, so we have some works in that area, but I will not bore you more. I don't know if Ismail mentioned this work, but we keep building this paper. It's a bit out of date right now. The first time we wrote in 2022, we updated in 2025. It's already 100 pages or so, almost. And it gives a good coverage of a lot of the work that's going on in academia and industry, including real products at the time. But we need to update this. And if you have any suggestions, let us know. Okay, as I promised, I'm not going to talk about processing using memory, but I can do a very quick skip to the conclusion. Feel free to ask questions in the meantime, if there are more questions. So there's a lot of work that I think Ismail talked about. Maybe he didn't talk about flash memory. Oh, you did talk about flash memory, right? Okay. Yes, please.
Let's say that you can build you can design your own architecture with your own.
Yeah.
How would you distribute them? How would you manage different machines to operate?
Yeah. No, no.
But I mean,
Yeah.
it's another question.
Yeah.
You mentioned earlier that this program was the same project today, but things are not going well, let's theoretically. We should be doing things in one way. Okay, I might.
Yeah. Yeah.
How do you see the world from your positive one, and how reach that world?
Yeah. So I think we need to explore multiple avenues, because in the end, there's no single answer. I think RISC-V ecosystem is great. If we can exploit that for near memory computation or in memory computation, that's very good. And that's something we're working on also. I skipped some of these parts, but we use the RISC-V processors in the FPGA, and we modify them so that you can offload computation to DRAM, for example. Our PyDRAM prototype that I mentioned in the other workshop is an example of this. So certainly RISC-V ecosystem is good, but we should also explore, in my opinion, other avenues also. Because RISC-V is a particular ISA, right? So we're very open. So if you have suggestions, I'm happy to talk also. Yeah. Yeah. Yes.
So throughout the talk today, actually switch was accessing processing memory, whatever power. And the first question is, do you think that the processing memory will worsen the memory?
Yeah. So that's a very good question. I think the short answer is yes. Like Ismail showed that, especially processing using memory will likely worsen row hammer problems, because you're actually opening multiple rows, for example, to do computation, and that causes more disturbance around the cells. And that needs to be solved. I think if you do processing near memory, it could also worsen because you have faster access to memory. But I think there needs to be mechanisms to prevent row hammer in place to make sure that doesn't happen. So if you do processing near memory, I think row hammer will become worse, but it's easier to solve. If you do processing using memory, I think row hammer will become worse and a bit harder to solve.
Second question is, when you talk about processing memory, it's actually it's a forward space. Maybe the average power of the sometimes it's kind of that the incentives is power is actually
Yeah.
So what if you because the process memory actually increases the incentives because
yeah. Yeah. Yeah, that's a good question. I think there needs to be more work on quantifying the exact power, instantaneous power increase. I think Ismail has some power numbers, but we need to do more. In the end, I think if you enable, let's say the worst case, right? You enable lots of banks to do computation. I think you will need to deal with the power requirements. I agree. because I think there's no pain, no gain, right? Right now we build this power infrastructure for the processor. It's expensive, but we do build it. And I think we do need to build it on the memory side also, if we're memory centric. You can, of course, have mechanisms that reduce the instantaneous power impact, right? You may not want to enable everything concurrently. You may want to limit some of the parallelism. So these mechanisms will curb some of the instantaneous power consumption. But if you really want to maximize the parallelism, you will need to build it. Yeah, sure, thanks. Okay, should I talk about adoption or no? I think this is better. Let's ask questions. Let's do questions.
You mentioned that once the problems are big enough, one chip will not be that 3D stack or
yeah.
Chips. So then you need communication between them. CXL actually has also what's called the queue of coherence. But then in the case of a 3D stack, they also need to talk to each other. So what is your? Are you afraid that maybe we have too many chips? We don't have 256 socket systems because coherency traffic is up too much bandwidth. So what is your view on that?
Yeah, that's why coherence is here, as you can see. Yeah, basically, I think coherence, the way we design it today, is not scalable. That's true for even multi-core, right? If you have so many chips, we cannot scale it. It's just too much power. We need to look at new ways of doing coherence. And people have proposed mechanisms, right? You don't want coherence across the entire system. You may limit the coherence domains, etc. And I think all of those things need to be applied to systems. Basically, all of those mechanisms that we have designed to scale processor-centric systems in terms of coherence apply here also. And I agree with you that CXL provides some mechanisms. We need to provide even more mechanisms, enabling a flexible interface that enables better communication across devices is great. Now, if the CXL requires coherence across everything, yeah, maybe that's good. That needs to change, right? I think maybe the CXL should not dictate a particular implementation much, and it should really provide the principles, a framework for how to enable coherence across devices and give freedom to the implementers. That's why I don't want to say yes or no. You know, I think it depends. Yes.
You get NUMA behavior, right? The bandwidth on a single chip is still much right? The bandwidth on a single chip is still much higher than going to the next chip.
Yeah.
So this will be still something the user needs to be aware of, data placement and so on.
Yeah.
Obviously, it will still cost me much more getting data from the next chip.
Yeah, exactly. There's no question about that. I think that's why the data mapping is also here, you know. Yeah, and that data mapping needs to be done. It is true whenever you have a distributed system or NUMA type of system. In this case, I think if you minimize the data moment as much as possible, hopefully you're in a better shape. But I think there will be cases, that's why we do the graph partitioning, for example, right? Essentially to minimize the data moment. Unfortunately, there's no perfect way of partitioning the graph, especially if you need to communicate. If you don't have enough space within a single node. My hope is that people also need to think a little bit differently, right? What we have looked at is stacking only DRAM. Now, if you can also stack flash, and if you have a whole lot more capacity, and if you can somehow stage data within a single stack, maybe you don't need to go out of the chip as much. So the problem is really how much capacity can you put in a single node? It'll never be enough, no question about that. But the bigger that you can put without going outside is likely the better. Okay, one more question. We're not done yet, apparently. Yeah. Yeah, that's a good question. I mean, there's not a whole lot of work. There's some work on data-centric computation theory. If you search for it, or if you email me, I'll try to send it to you. Not in the way I envision it. I think basically like if you think about how theory of computation is developed, people try to quantify the complexity of algorithms, right? And they did a great job in terms of computation complexity. I think we need something similar in terms of data moments. Like how can we quantify the data moments? It's a bit tougher, but it's potentially doable. How much data you're touching? Maybe it starts with capacity and then goes to how much data you move. Again, I don't have, I have some lead points, but I don't have really, otherwise I would do it. Basically, it's some theoretician who is very inclined with practical matters should take a look at this. And I think this is another bridge that we need to have, like theory and practice sometimes work really well in computing, but in these really, let's say, forward-looking topics for which hardware doesn't exist, it's hard to get theoreticians to be working on them. It needs to be a very forward-looking theoretician that says, oh, okay, I'm going to quantify the data moment. I'm going to provide a nice theoretical framework for doing that. It will not be perfect, so they may need to make some assumptions, but that's a very good start. Right? You're welcome. Okay, I think we're done then. Thanks.